Coming up in our catalog of engineering catastrophes, a Dallas skyscraper with a dazzling design flaw.
On an 80-degree day, it's going to be like 110 degrees in the garden. It's already too hot here in the summer.
Historic Amsterdam is rocked when construction goes off the rails.
I heard just cracks, cracks.
An architectural error turns a Paris landmark into a blot on the landscape.
You go to Paris to see the iconic buildings, not to have them crash down on you.
And a small engineering oversight undermines an entire street.
And I could hear this rumbling. At that point, I realized the ground was moving.
With big builds, even the smallest mistake can be a huge disaster. From miscalculations to misunderstandings, these are the massive engineering mistakes that only an expert can hope to fix. When complex constructions push the limits, it's not always easy to get it right first time. Some problems are hard to detect, while others are clear as day. For this story, we're off to the deep south and Texas, and a design flaw the locals just can't ignore.
It's a 360-degree problem every day, every year.
The structure might be elegant and energy efficient, but the shining glass brings problems too.
It's like a disco ball. No matter where you are, there's light streaming into you.
This is disturbing.
Dallas, Texas, shining light of the Lone Star State. The Big D is one of the fastest growing cities in the U.S.
Texas is the oil capital of the USA, and its most famous city, Dallas, is hot, very hot.
With an average of 232 sunny days a year, summer temperatures can soar to 36 degrees centigrade. In 2013, the doors opened on the city's latest residential high-rise, the 42-story glass-clad Museum Tower. The shining facade was chosen for two reasons. Andy Scott later consulted on the tower's glass.
At the time, the choices of glass were made because they were beneficial for heat control and so forth inside the building, and were made for aesthetic reasons because it was beautiful and would look, beautiful from the distance.
It might look spectacular, but as Andy hinted, so much glass in a sun-baked city creates one very obvious problem: heat control. As the sun beats down on the huge wall of glass, the interior risks becoming a hothouse. This was no surprise, so engineers installed almost 25,000 square meters of special reflective glass to keep the heat out and reduce energy costs for residents. But midway through construction, local residents were in for a shock. The reflectivity wasn't just saving energy bills for the tower, as journalist Tim Rogers explains.
They want the glass to be reflective because it makes their job easier at Museum Tower. They don't have to spend as much money cooling the place, and they get to brag about how they're a LEED certified building, which is all well and fine. But that reflectivity has to go somewhere.
As gallery owner Petty Parker discovered to her horror, with her premises located directly opposite Museum Tower, halfway through construction, she noticed the startling effect the building was having.
Well, the first day we noticed the glare. First of all, it was an enormous glare coming not only from the building, but into our building and into our place, and unfortunately into our artwork. So that was alarming.
This is the last place you want a super shiny building. It's one of the sunniest places in the United States.
Usually it stays, the glare stays above about the 20th floor. It does go through to some of our paintings. We've moved a couple just to make sure. And so it's not your normal, oh, well, I can live with it glare.
The problem started right back in the design phase, when the decision was taken to build a skyscraper with an elliptical shape.
I found out that it's a 360-degree problem, not just one for us. So more neighbors noticed it, more and more people were noticing it.
Most skyscrapers are flat, so sun rays are reflected off in one direction. Not so Museum Tower. Consultant Charles Clift explains.
The geometry on the Museum Tower is complex. It's not only curved in plan section, it's also curved along its vertical axis. So the sunlight, no matter what time of day or what time of year, there is sunlight reflecting in lots of different directions. We have said it's like a disco ball. No matter where you are around the disco ball, there's light bouncing off and streaming into you.
With more than 2,000 panes of glass, each at a different angle, the effect is powerful. But the design is not ideal for its neighbors. Engineers have been constructing glass-fronted skyscrapers for decades, but as architects strive to create even more innovative designs, what might seem like a distinctive feature could turn out to be a major flaw.
The Walkie-talkie in London is concave, like a satellite dish. It goes in, and so it focused the sun's rays into one burning point.
The Museum Tower has the opposite problem. It's convex like a ball, scattering the sun's rays, dazzling everyone around it.
It's not only an issue for residents in neighboring buildings. Museum Tower curves inward at its base, so the glare is also reflecting down to ground level, having a knock-on effect on an art gallery at the foot of the building, the Nasher Sculpture Center. Fulvio Serra is the designer and builder of the gallery's unique roof system.
Well, everything is special here. The architecture is custom designed. I would like to say that the roof basically is a sculpture in a museum of sculptures. It's modern art.
The Nasher Sculpture Center opened its doors in 2003, 4 years before Museum Tower was even proposed. Its glass roof, made of hundreds of thousands of tiny aluminum shells, was designed to create perfectly even light in the gallery, no matter where the sun is.
When the gallery roof was designed, they had no idea that a building was going to go up right next to it, which would become a light source all its own.
What should have been an artistic space filled with an even, diffuse light now suffers from secondary glare.
The holes that you see in the roof are allowing the light to get inside and to create an uniform light inside. When you see that the light can pass through the holes, like in that case, you see that the whole ambience is transformed.
Restoring the roof to its former glory would mean modifying every aluminum shell, not only labor-intensive, but hugely expensive.
Well, for arts lovers, I think it's a huge issue because the roof has been made utterly obsolete. So there are certain artwork that they can't even put inside the museum.
It's not just the interior that's affected. Next to the gallery is an 8,000 square meter sculpture garden, which has suffered under the same intense glare from the tower. Landscape architect Jeff Bruce was brought in to examine the root of the problem.
As you can see right now, I've got a bit of a shadow from the sunlight on this side of my face. But also on the other side, I've got a reflection of light that's coming off the museum tower in that location there.
This is really like having two suns shining down on everything.
Although the light is naturally coming this way, we can begin to see how it's bouncing off the tower and entering the garden.
But on an 80-degree day, it's going to be like 110 degrees in the garden. And that's not a pleasant experience. It's already too hot here, in the summer. We don't need help from another building reflecting light.
The double blast of sunlight from the tower has a negative impact on plant life and makes the gallery's garden areas so warm they're unusable by the general public.
Reflectivity isn't just about aesthetics. In many buildings, it's about keeping their green credentials by keeping their energy bills down.
If you can reflect the energy, the solar heat back out from getting into the building, that's sort of your first blunt force to reduce your energy consumption.
This concept was clearly a driving factor when it came to choosing materials for Museum Tower.
So this was the product that they chose for Museum Tower. 44% of solar radiation is reflected off of this building. That's what gives it that very bright, shiny, sort of light dancing quality.
This choice of glass was well intended, but there might have been a more neighbor-friendly option.
If you don't want that much reflectivity, you could pick this product. Reflectivity is only 16%, so it would have only 1/3 of the solar radiation reflecting off of this product compared to what was selected for Museum Tower.
One possible solution to Museum Tower's glare would be to replace the glass on the entire building with the less reflective option. However, there is one predictable hurdle standing in the way.
Money. It all comes down to money, right? I mean, both sides did their own studies to try and figure out what could be done about this, and people told me that it could be $20 million.
Total glass replacement, total curtain wall replacement on the museum tower, attaching, instead of just the glass, attaching a shutter and shade system to the museum tower.
One of the best solutions that I saw was a scrim, something that would go on the outside of the building.
Film was really going to be the best solution. At first, the film would last approximately 5 years. By the time we were done at the end of the study, the film was up to 7 years. Now I'm sure the film can last up to 10 years.
But of course, then the people who are buying these very expensive condos are going to say, wait a minute, I bought this condo for the view, and now you're going to put something that, you know, obstructs that view? It's just a stalemate.
Sometimes buildings are built that are gorgeous and beautiful and wonderful, but you have to look at the effect it has on the community.
Engineers should always consider the environment, but it shouldn't come at the expense of existing businesses and residents.
Until a solid solution can be agreed on, Museum Tower's neighbors will simply have to avert their eyes and hope for the best. Engineers are constantly exploring new and radical ways to get the job done. But sometimes, even groundbreaking projects can turn out to be design disasters. For this story, we're off to the Netherlands, where an engineering challenge shook a city to its very foundations.
I heard cracks, cracks.
These houses have stood here for centuries.
The police and the firemen are standing in front of your door and getting your husband and your 3 kids out.
This is a nightmare scenario for a picture-perfect city.
Visited by 18 million tourists a year, Amsterdam is known for its artistic heritage, elaborate canal network, and narrow houses that have remained untouched, if a little bit uneven, for centuries. But in September 2008, cracks began to appear in homes in the VL Stra district at an alarming rate. Architect and landlord Volbert Vroom had just finished dinner when he received a disturbing phone call from his very worried tenant.
He said, I cannot open my door. It's just, I see cracks. I said, well, what's going on? And then I walked just, because I lived just around the corner, I walked and saw all those blue flashlights, you know, police, firemen walking around. I thought, oh my goodness, it's happening.
Amsterdam resident Helena van Gelder was also caught in the middle of this housing crisis.
Helena, you had to come because there is something going wrong with the neighborhood, with the house in the next street. But okay, so I went just around the corner and I saw that the house of my neighbor was getting bad. It was sinking. And then another neighbor from the other street ran into me and said, Helena, the police and the firemen are standing in front of your door and getting your husband and your 3 kids out. Your house is going.
The houses are built on 400-year-old wooden piles, driven up to 20 meters down into a sandy bed. Dramatic subsidence on this scale is every resident's worst nightmare. Sudden movement or failure in the piles could easily lead to the collapse of a building.
I ran to my office and I could still open the front door. I heard just cracks, cracks. It was like the building was crying for pain. It was like, you know, it was sound everywhere.
That building is telling you, get out. The whole neighborhood is heading underground.
It was obvious the cause of the problem lay beneath the residents' feet, with a new infrastructure project the most likely suspect.
Amsterdam's famous for its bikes and canals, but there's a much faster way to get around the city, underground.
Amsterdam's metro system was nowhere near as big as other cities. It was just 26 miles long. Berlin's is more than 3 times the size, and Paris has more than 5 times the track.
In 2002, 5 years before the collapse, construction began on a new metro line with over 6 kilometers of tunnels running under the very heart of the city. Paul Janssen was the engineer in charge of boring the tunnels.
The new part is the north-south line, which connects northern part of Amsterdam with the southern parts. There is a big difference in boring a tunnel in our surface, our soil, compared to, let's say, the soil in England or Paris or the Alps.
The trouble is, the ground beneath Amsterdam is made up of peat, sand, and water. The bedrock lies nearly 400 meters below the surface and is unreachable for building foundations. Instead, buildings sit on piles driven to depths between 12 and 21 meters, which complicates the construction of any underground railway. And there's another problem: water.
Water was the making of Amsterdam, but it's also been its nemesis for centuries. The water table is so high in the city that building anything underground is never going to be easy.
Almost everything about Amsterdam is a potential construction nightmare. Sitting around 2 meters below sea level, with more canals than Venice, an extensive system of sea dikes, dams, and floodgates keep the city from completely flooding. So a project of this type was always going to be incredibly ambitious.
Building a metro system is going to be difficult anywhere, but if you add in Amsterdam's sodden soil, you've got one tricky engineering task.
It's a bit like trying to dig a hole in wet sand at the beach. As soon as you've dug it, the water just goes straight back in again.
Building of the metro system was a twofold challenge. First, find a way to contain Amsterdam's soggy soil as each section of the metro line was constructed. Then, avoid the intricate network of 11 million wooden piles holding up the houses in the city's historic center. Engineers came up with an ingenious plan.
The new metro line would follow the route of the city roads. If it didn't go underneath the houses, there's no risk of disturbing them. At least that was the theory.
Digging tunnels that only followed Amsterdam's elaborate and ancient road network was going to be restrictive.
So we had to avoid the piles of the houses and the buildings, but at some occasions we actually had to bore through the pile foundation.
Tunneling under the houses could potentially jeopardize the ancient city above. However, the engineers had a system in mind that would make it all possible. To minimize disruption above ground, before building each section of tunnel, concrete and steel walls were constructed on either side. These would separate the growing tunnel from the highly sensitive piles supporting the nearby houses. With a steel and concrete roof to support the road above, tunneling could safely continue. This is known as the box system. But in June 2008, as it reached construction of one of the underground stations, the project came to a dramatic halt. Michael Jonker, a spokesman for the Metro, explains.
Well, what happened at Vijzelgracht was that during the excavation of the station, the diaphragm wall started to leak water. But the water took sand with it, and the sand was just the thing where the houses were based on.
Tunneling only just below Amsterdam's historic buildings, the unique box construction specifically designed to protect these homes appeared to be destroying them.
In theory, the box system was an ingenious way of reducing the impact on the surrounding area, but it took just one leak in the concrete walls to cause utter chaos.
About 10 houses, they weren't livable anymore. So we had to restore that, but of course it was a big shock to the neighborhood, especially because it happened twice.
With work on the metro line back underway, in September there was a second dramatic failure in the box system.
Water and sand leaked into this construction zone, upsetting the delicate water table and those piles beneath the houses.
If water and sand leak into the tunnel, there's only one way for those houses to go. Down.
The construction team immediately stopped work and focused on securing the leak to protect the surrounding buildings. But for the historic houses above ground, it was already too late. They started to sink at an alarming rate.
So it was 25 centimeters, that's about 10 inches. We went down in 2 hours' time.
Then it happened again, and of course that was the moment that the city lost all the trust in the confidence in the project.
The cause for the failure remains unclear. It could be an undetected flaw in the box's foundations, a result of using new technology, or simply additional pressure placed upon the system while working so deep underground.
So a special commission had to find out, is it okay to continue this process? And they concluded, yes, it is okay, but mind your risks, take your measures, and improve your communication with the city.
Now, engineers are keeping a constant eye out for any settling. Using state-of-the-art laser sensors, Jaap Flink is managing this cutting-edge monitoring operation.
These are the instruments we used. We had 93 of them on the facades of every building. This instrument, through the lens you see here, attached to the front, sends out a laser to the mirror we have here.
The machine is placed on the front of a building, with the mirror attached to a house on the opposite side of the street. The machine detects even the tiniest movements, down to millimeters.
It sends out a laser. It's being reflected towards the machine, and the machine calculates the distance every time it measures this particular mirror. And by measuring it time and time again, you will be able to see if the building is moving.
The monitoring system is an ingenious way of making sure engineers are never caught out again. As the houses have stopped moving for now, the metro project has been able to move forward.
Without an instrument like this and the accuracy it has, within the typical Amsterdam conditions like soft soil, wooden piles, historic buildings, we wouldn't be able to build a metro line underneath this historic city.
After a series of delays, Amsterdam's new metro finally opened in July 2018. Above ground, engineers even managed to return the damaged buildings to their original condition. But this construction catastrophe wasn't cheap, costing over $1 million to shore up the houses with new concrete piles.
It's completely restored. You don't see any traces anymore. They also have lifted the whole building again up to the original before they crash. They have done a very, very good job.
The design problems mean the project will come in 5 years late and more than $1.5 billion over budget.
Even with the best laid plans, some places are never going to be ideal for certain building projects. But when talented engineers put their heads together, they can achieve the seemingly impossible.
In the pursuit of architectural perfection, the limits of engineering know-how can be stretched to breaking point. And when the elements and egos collide, the results can be catastrophic. Now to France, for a megastructure mess-up on a truly monumental scale.
This particular arch wasn't so triumphant.
Et le risque était d'avoir des plaques de 80 kg qui tombent de 100 mètres de haut.
You go to Paris to see the iconic buildings, not to have them crash down on you.
Paris, France, a city that's renowned for its art, culture, gastronomy, and of course, its architecture.
When you think of Paris, you think of the Eiffel Tower, the Louvre, the Arc de Triomphe, but there is another landmark that's more modern, but just as iconic.
Seen as a modern interpretation of the Arc de Triomphe, the radical Grande Arche de la Défense is a monument to the 20th century. In 1982, a great national design competition was launched by French President François Mitterrand. Danish architect Johan Otto von Spreckelsen won the commission with his design chosen for its strength and simplicity. Standing more than 100 meters high, the Grand Arch is a cube within a cube, designed to make an impact in the three-dimensional world. Robert Leon chaired the committee in selecting the winning design.
We call it La Grande Arche. It's sort of a crown on the business district. And also from Paris, I think it's nice to look at it. It's the horizontal line in a landscape where you have only vertical.
Mitterrand wanted a landmark building to honor his presidency. Rather than celebrate France's military victories, La Grande Arche stands as a monument to humanitarian ideals. An arch with 4 equal sides, this ambitious structure houses government offices within the 2 legs, while the roof section serves as an exhibition center and museum. It's an iconic feature on a significant route laid down in the 18th century.
We are on the historical axis of Paris, which comes from le Louvre, la Place de l'Étoile, l'Arc de Triomphe, and over to here and goes on west.
Work on the Grand Arch began in 1985. Constructed around a concrete and steel frame, the monument is topped by a vast 10,000 square meter roof, supported by concrete beams. The exterior walls are covered by 2,800 opaque glass panels and 350,000 gray and white marble sheets, engineered to be thin, light, and reflective. Von Spreckelsen specifically chose polished white Carrara marble to clad the east and west facades. Selected for its purity and reflectivity, the white Italian marble would catch the sun as it passed from sunrise to sunset. But von Spreckelsen's use of marble didn't come without controversy. Critics warned that it wasn't suitable for the Parisian climate, as historian Bernard Tullier explains.
Dès l'origine, l'architecte qui était danois n'utilisait jamais le marbre à l'extérieur dans son pays, c'est sûr. Et donc il pensait que la latitude française, l'Île-de-France, permettait d'utiliser le marbre. Ça flattait sans doute le président de se dire, dans mes grands travaux que je vais entreprendre dans ma présidence, je vais avoir une grande arche en marbre.
What is it they say about pride coming before a fall?
After various disputes, von Spreckelsen left the project. Sadly, he died in 1987, 2 years before his iconic design was completed. Work on the arch continued to meet the construction deadline of July 14, 1989, a date set to coincide with the bicentennial of the French Revolution.
1989 was the 200th anniversary of the French Revolution, with one important day, Bastille Day, 14th of July, and different monuments, this was one of them, had to be completed on that day.
Completed in just 4 years, the engineers had met their deadline, and the building was officially inaugurated the next day.
And the 15th of July was held here, a G7 summit with the heads of state from all over the world, President Bush, Mrs. Thatcher, and many others. So it was a very brilliant start for this building.
But while the Grand Arch was certainly an iconic structure, unlike its neighbor, the Arc de Triomphe, this newcomer was not designed to withstand the test of time. In fact, this monument to the modern age was about to take a dramatic fall from grace. In 2010, only 21 years after its unveiling, the controversial white Carrara marble tiles were showing signs of fatigue, leaving the Grand Arch in urgent need of repair. Stone has long been used in the construction of buildings and monuments, and known for its durability. These giant lumps famously stand up to the ravages of time. But von Spreckelsen's decision to use Italian marble was in fact the building's downfall. The thin marble cladding was no match for the Parisian climate.
C'était clair, le marbre n'était pas un matériau durable. Le marbre est poreux, donc l'eau, le brouillard, l'humidité rentrent dans le marbre et ensuite, avec le gel, il fait éclater le marbre. Donc, et à cette hauteur-là, un élément éclaté, ça représente un danger.
The white marble which covered the east and west of the arch developed serious defects. Cut into tiles about 4 centimeters thick, the marble panels absorbed water and began to bulge with changes in temperature, threatening to fall off their mounts in a process called granular debonding. Etienne Boss was the construction director for the remedial work on the Grand Arch.
En hiver, pendant les périodes de gel, le marbre se déforme et la décohésion granulaire a la particularité de faire que la déformation est définitive et s'amplifie tous les ans et de façon aléatoire. Donc les plaques de marbre, qui étaient des plaques de marbre minces de 4 cm, se déformaient de façon convexe ou concave, de façon indifférente, ce qui donnait une façade avec des vagues. Le vrai problème, c'est que les accroches de ce marbre se cassaient avec la déformation des plaques et le risque était d'avoir des plaques de 80 kg qui tombent de 100 mètres de haut.
This iconic building was in the limelight of Paris, not a great place for engineers to slip up.
Can you imagine being hit by a falling marble slab? It's unthinkable.
Mitterrand's vision had become an embarrassment, and in 2012, with 60 loose panels identified, the decision was made to replace the marble before any panels fell off.
A survey of the arch found that 1 in 6 of the tiles was loose. A solution had to be found.
Pour la rénovation et de la Grande Arche, on avait deux obligations. Respecter l'œuvre de Otto von Spreckelsen, l'architecte d'origine, et d'assurer au ministère la pérennité de ce qu'on allait faire.
Granite, known for its durability, was chosen as a suitable and sustainable replacement, with properties deemed to be risk-free and fit for purpose in the Parisian climate. To respect architect von Spreckelsen's vision, contractors sourced Bethel white granite from the US.
Replacing the marble with granite has cost the French public 200 million euros.
Work began in 2015. Contractors treated the surface of the granite so that it reflects light in a way that closely resembles the controversial Carrara marble, without the risks of failure.
Donc nous avions l'obligation de transmettre un bâtiment avec une assurance qu'on ne reviendrait pas dans 25 ans modifier ce que nous avions fait. Le granit, ça fait des siècles qu'on l'utilise, comme le marbre, mais les techniques modernes d'utiliser des parements de façade peu épais fonctionnent avec des granites et ne fonctionnent pas avec des marbres.
Granite was the best solution to this problem. The architect's vision had to be compromised slightly, albeit 20 years later, in order for it to survive to the 21st century.
While they may have found a satisfactory solution for form and function, the choice of replacement stone is not popular with everyone.
De substitution, je dirais, avec toute la dénégation que je peux mettre dans ce mot de substitution. C'était du marbre translucide, lisse, au toucher. Ici, la lumière ne joue plus avec le granit. La lumière ne joue plus avec l'aspect terne du granit.
It's very clean, very neat, and I'm very confident it will help the monument to last over centuries.
While engineering egos may have been bruised, in years to come, the Grand Arch will be seen as a monumental success and stand proud as an architectural icon of the Parisian skyline.
It's not only grand structures that suffer from dramatic engineering failure. Humble residential buildings can be hit just as hard, especially when the power of Mother Nature is underestimated. This next construction calamity takes us to England and a town shaken by what was thought to be an earthquake.
The UK is not known for its earthquakes. This was clearly something else.
I could hear this rumbling, and my natural instinct was to go out. At that point, I realized the ground was moving.
A minor engineering mistake caused a full-on catastrophe.
Ripon's residents were almost swallowed whole.
Ripon in Yorkshire, an ancient cathedral city, as steady as they come. In November 2016, residents of Magdalene's Road were safely tucked up in their 140-year-old houses. But late that evening, the peace was shattered. Ben Bramley was watching television.
Last night, about 10:30, a little bit drowsy, I've been watching the snooker, and my partner came and made me aware that there was a bit of a commotion.
Ben's neighbor, Francis O'Neill, had already gone to bed.
I think it was about 1:45, and I could hear this rumbling, and my natural instinct was to go out and went down what I thought were my steps down into the garden. At that point, I realized that the ground was moving. I luckily managed to pull myself back up.
A sinkhole the size of a school bus had swallowed their back gardens.
I guess it didn't really dawn on me at first how serious it was. It was only when I went around the back of the house and got a different perspective, a different angle, that you could see the depth, and it was right up within 10, 15 feet of our back door.
With the properties in serious danger of falling, firefighters gave the residents just 15 minutes to pack their bags and leave. The collapse shocked the city, and yet, this wasn't the first sinkhole in the area. Dr. Anthony Cooper has been studying Ripon's unstable history for over 30 years.
Well, sinkholes in Ripon have been recorded for over 100 years. The Reverend Toot wrote a paper in about 1868. The survey geologist that came here wrote another paper in about 1870. And they documented a lot of sinkholes. Compared with elsewhere in the country, there are more sinkholes in Ripon than there are in a lot of places.
And it's not just sinkholes.
Several houses that were built along the road here had to be taken down due to subsidence. The ones further on the right have got a big sag. These ones on the right are tilted backwards. There's one there that's been demolished.
This is not a coincidence. There is definitely some kind of pattern here, and all the evidence is pointing towards Ripon's geology. There is definitely something going on beneath their feet.
Ripon's problem is that it sits above deposits of the chalky mineral gypsum.
This is gypsum, fibrous gypsum, porphyroblastic gypsum with big crystals in, and a bit of muddy gypsum. And if I put this in the river, it would only last about a week before it dissolved away completely.
For thousands of years, rainwater has been dissolving the pockets of gypsum around Ripon, gradually creating caves deep underground. As the caves grow, their ceilings collapse, forming sinkholes. 140 years ago, where these gypsum deposits lie was anyone's guess, on top of which, in Victorian times, building regulations were lax, with shallow foundations less than a meter deep. Builders would never have known if there was a dangerous seam of gypsum hidden below.
That's the big thing with sinkholes. They are hidden underground. The first time you sort of know that they exist is when they're sucking your garden into them.
Magdalene's Road sits on a seam of gypsum, but the sinkhole here was very localized, with no evidence of other caves nearby. It seems Mother Nature might not be entirely to blame.
The area has a history of leaking drains and blocked up drains, and it's a bit of a chicken and egg situation. Does the sinkhole collapse slightly and break the drain, or does the drain leak and wash material down that then causes the sinkhole?
Worn with age or damaged by tree roots, a cracked drain pipe will leak water into the surrounding subsoil. If the leak is close to a building's foundations, it can have a devastating effect. With the damp soil unable to hold the weight of the building, the walls begin to sink into the softer ground, causing cracks to appear.
A water leak above ground is bad enough, but if you've got one underground in a sinkhole area, well, that is going to be a disaster.
Whatever the cause, local officials in Ripon keep a close eye on any suspicious movement. Since the Magdalenes Road incident, nearby residents noticed a dip in their local park. Dave Morgan, a geophysicist from the British Geological Survey, has come to investigate.
I'm going to be taking readings here every 10 meters along what I assume is solid ground at the beginning of the line, through the center of the feature here. Now I'm standing in the bottom of it. So the assumption is that there's weaker ground under here, possibly a void at greater depth, and the ground is slowly sinking into it.
Dave is essentially performing an X-ray to find out if this is just a dip in the land or whether an underground cavern is forming.
I think it's important to do these tests because we can identify areas which are likely to undergo collapse, and the civil engineering companies can mitigate that, and they can put the correct foundations in for new buildings to ensure that they're safe.
Dave's using an additional piece of kit in his testing, a graviton.
A graviton measures the strength of gravity in the ground beneath it. The less dense the ground, the lower the reading, and vice versa.
24 hours later, Dave is back at headquarters with the results of the tests.
What I have on the screen now is a display of the survey we did last December and the one we did yesterday. We have an area of dark blue here on both surveys, and that corresponds with the weakened area. On either side of it, we see lots of warm colours, the oranges, reds and purples, corresponding with the stronger rocks either side. So our interpretation is that that is a weaker zone which is falling in.
The darker blue circle clearly shows a vulnerable area. But has it gotten any worse since the last survey?
There are subtle changes, and I've noticed smaller areas in the yellow colours close to the surface here are not so apparent on yesterday's survey. So we might conclude from that some of the rocks near the surface have weakened to some degree. So it does indicate that things are changing.
Dave will continue to monitor the area for signs of movement, but it's too late for Magdalenes Road. With the suspected leak fixed, it was time to plug the hole.
The engineers have put in a large plug of concrete to remediate the ground.
The best solution was to fill the sinkhole with reinforced concrete. Seems simple enough, but it actually took months.
With engineering mishaps, sometimes the solution needs to be simple and robust. But when it comes to sinkholes, the real key is knowing exactly what lies beneath.
So the residents of beautiful Ripon are safe for now. I just hope those underground caverns stay exactly where they should be, underground.
Construction calamities come in all shapes and sizes. So long as we keep building, there will always be more blunders to fix. Coming up in our quest for the world's most incredible engineering disasters. A skyscraper dropping bolts from the blue.
These bolts are huge. They're the size roughly of a human arm.
A wrecked freeway that became a highway to hell.
It looked like after an earthquake, and we don't have earthquakes around here.
A Greek village that's slipping and sliding.
It looks like a war zone. Like, what happened here?
And roads in Oregon that are driving residents insane.
It's literally falling apart here.
With big builds, even the smallest mistake can be a huge disaster. From miscalculations to misunderstandings. These are the massive engineering mistakes that only an expert can hope to fix. When construction goes wrong, there's a chance engineers might sense a calamity looming.
There was such a critical problem with the building that if it hadn't been discovered, could have made for a major catastrophe in the city. It's kind of mind-boggling.
But sometimes, microscopic problems can fail without warning. Like this story in the UK, a skyscraper with an unexpected engineering issue.
I wouldn't have thought that something like this would have been happening in London.
This spectacular structure was coming apart at the seams.
It's usually the stock market crashing down that spooks the city.
This was literally a bolt from the blue.
London, England dates back to Roman times. The city is steeped in architectural history, but that doesn't mean it's rooted to the past. The skyline is ever-changing, with new and revolutionary structures slotting into place beside established historical landmarks.
The London skyline is known for its statement architecture, the London Eye, the Shard, the Walkie-talkie, but there's one that's bound in infamy, the cheese grater.
The building's distinctive wedge-shaped profile is designed to protect the views of historic landmarks, including St. Paul's Cathedral. Journalist Robin Wilson knows the structure well.
The Leadenhall, also known as the cheese grater, has got its unusual name from its shape. As you can see, they're rather similar. Striking, bold shapes, starting with a kind of large base at the bottom and then sort of tapering off. Also at the side of the building, you can see they've got quite similar teeth.
The 52-story tower has a tapered glass facade on one side, with steel bracings and a ladder frame to anchor the building to the ground. Many tall buildings use a concrete core to provide stability, but the cheese grater is supported by an external steel superstructure called a megaframe. This exoskeleton is the tallest of its kind in the world. The steel beams are connected by nodes that transfer forces of around 6,000 tons, with the whole frame connected by almost 3,000 megabolts. Crucially, these bolted joints are completely rigid. When it opened in July 2014, the pioneering construction wowed the world. But within months, it was clear that something was wrong.
In 2014, 2 bolts broke and parts of those bolts fell from the Leadenhall building. One made it to the ground, the other one was actually caught within the skyscraper itself. 3 months later, another bolt broke, so January 2015. These bolts are huge. They're the size roughly of a human arm.
Can you imagine a bolt the size of my arm falling from the skyscraper onto a crowded street below? It's absolutely amazing that nobody was hurt.
If a megabolt from the cheese grater hit a pedestrian, the outcome could have been catastrophic. Ballistics expert Sharon Flegger-Taylor conducts an experiment to recreate the impact a falling megabolt could have on a person at street level.
Today we are replicating a bolt of 38.4 kilograms with the dimensions of 75 millimeters by 1,000 millimeters, falling from various heights.
Instead of megabolts, Sharon fires bullets at different speeds to replicate the physical forces involved.
So the kinetic energy produced by the bolt is a certain amount, 34-ish kilojoules. We can actually change the velocity and the weight of a bullet head to ensure that it produces the same amount of kilojoules.
The lab is set up like a shooting range, with a 50 caliber rifled gun barrel aimed at the target.
This particular bullet has been loaded to produce velocities the same as the bolt will have fallen from the 3rd floor of a skyscraper.
First, Sharon will demonstrate what could have happened when a bolt fell from the 3rd floor. A watermelon will take the place of a pedestrian.
As you can see, the bullet has passed all the way through the watermelon, however, hasn't caused what we would say catastrophic injuries to it. The bullet has passed through and gone through the paper. If this hit you on the hand or the leg, you stand a fairly good chance of seeing the next day.
If it missed your head, that might be a lucky escape. But what if a bolt had fallen from the top of the 52-story cheese grater? The same experiment, but how will the melon fare against a much higher velocity shot?
Fatal.
With such devastating potential, engineers had to find a solution to the megabolt problem. First, they needed to know why the bolts had failed. When inspected, they discovered the fallen bolts had undergone a process known as hydrogen embrittlement. Put simply, it's a process in which hydrogen atoms diffuse into a metal structure. The atoms slowly recombine to form hydrogen molecules in gas form that create pressure inside the metal. Ultimately, the metal becomes brittle.
The easiest way to think about it is the metallic atoms are like marbles, and the hydrogen atoms are like grains of sand. The grains of sand can fit in between the marbles, and if too many grains of sand get in there, they start to push the marbles apart.
With brittle megabolts in such a rigid structure, there was a risk that more might plummet to the ground. Engineers needed a fix, and fast.
Because hydrogen embrittlement develops over time, it's very difficult to test whether or not the bolts will be susceptible to it before they're put in place.
What's more, it's a phenomenon rarely found in big-budget projects.
As far as I'm aware, other buildings, certainly of this size, haven't had issues around hydrogen embrittlement.
But when it happens, reversing it is difficult, as engineer Peter Desnierk explains.
When it comes to hydrogen embrittlement, if we know it is a process that is present in our elements, we can try to regain its original properties by heating them up to very high temperatures, allowing the hydrogen to escape from the materials. Unfortunately, in existing buildings, when the building has been erected, it's much harder to actually heat the elements in the construction to such a high temperature. So quite often the only solution we have is to actually remove the elements and replace them by elements with the proper properties.
The integrity of almost 3,000 megabolts was now uncertain, so engineers had only one choice.
With a potentially lethal situation like this, there was only one solution, and that was replace all the bolts.
So at the end of the investigation, one of the subcontractors on the job actually replaced all the 3,000 bolts on the scheme at great cost. The CEO at the time actually said that it could cost them up to £6 million.
To ensure that hydrogen embrittlement wouldn't be a problem in the future, the new bolts were treated with a cutting-edge process called thermal diffusion, coating them with a protective anti-corrosion layer.
buildings of the future would probably still be built with our nowadays materials such as concrete, steel, wood, glass, and so on. But at the same time, new materials are being developed, such as composite materials, where we have carbon fibers strengthening our structures. Some people are also looking at nanotubes, so actually playing on the molecular level to optimize the strength of materials and see whether we can use them on a much larger scale in actual buildings.
With the cheese grater, the engineers' swift response averted the danger. But this won't stop architects pushing the boundaries of engineering and design. With the advent of new technology and materials, new lessons will be learned along the way. Engineering catastrophes can reveal themselves while construction is still underway. But other disasters lie dormant underground, a hidden danger just waiting to fail. For this story, we head to Germany and a construction catastrophe that's causing carnage for a once sleepy town.
Das ist ein massives Problem.
Ja, also schlafen ist auch nachts nicht. Aber leider ist es nicht ruhig geworden.
This cutting-edge engineering project has turned into a bottleneck blunder.
This is a road to nowhere.
The autobahn, Germany's famous highway, the lifeblood of this fast-moving country's infrastructure. First created in the 1930s, the network now has almost 13,000 kilometers of road, and it's still growing. In 2005, a new 280-kilometer stretch of autobahn was opened, connecting inland Germany with the north coast.
You can see why they'd add a new stretch of road here. It really sped things up for all the tourists heading from Germany's cities to the coast.
As well as cutting travel time, the road's other goal was to bypass rural villages, easing congestion. Journalist Lutz Reuter explains why this new highway was considered a triumph.
People around here were very happy because all the other small roads, they are not in a very good condition. It has a nickname around here. It's called the Küstenautobahn, which means the coast autobahn. People come here for the nature, for animals they can't see in other parts of Germany anymore.
Cars reach their destination faster and bypass the small villages along the way. Win-win, right? Well, not quite.
Just 12 years after opening, this efficient expressway had become a highway to hell.
At the end of September 2017, the road just collapsed. It started with one part, direction into the east, and a couple of days later, the whole road was closed down.
This is definitely not the thing you'd expect from a country that's so famous for its roads.
A section of new autobahn had completely collapsed, leaving a 40-meter-long hole in the highway. Thankfully, no one was hurt. But the disaster wasn't over yet. Within 5 months, the damage had more than doubled. Head of Highways, Ronald Norman, was sent to assess the damage.
Die Autobahn ist letztes Jahr im Oktober zusammengebrochen, und zwar hier auf der rechten Seite, wo jetzt der Bagger steht. Ein paar Monate später kam die andere Fahrbahnseite dazu und die hat das Gründungssystem der Straße versagt und die Autobahn ist abgesackt. Alles gut, alles gut. Ja.
With this crucial transport artery out of action, Ronald's top priority was to establish what had caused the foundation to fail. Ecologist Dr. Gerald Jurasinski knows this area well and was brought in to consult.
When I heard that the Autobahn was collapsing,
My really first thought was, that shows that you should not underestimate a peatland.
This area of Germany is well known for its peaty soil. Peat is formed as decomposing vegetation such as trees and leaves get crushed and settle in a water-rich environment. Peat retains a high moisture content, making it soft and soggy.
Peat can be found in bogs and moors, so it's no surprise that it's up to 97% water, which is not ideal for building heavy structures on.
Northern Germany is essentially one massive peat bog, stretching across 22,000 square kilometers, and it's deep.
These peatlands extend 6, 7, 8, sometimes 10 meters into the depth, and therefore you don't have to underestimate them when you want to construct something on them.
Dieser Torf, das ist unser Problem. Das ist hier mächtig ungefähr 6 bis 10 Meter. In den Jahrtausenden ist hier viel Torf entstanden, ist dieser Torf eine ganz normale Erscheinung. Also wir wussten, dass der da ist.
Engineers knew the peat was there all along. The truth is, you can build on peat if you do it properly.
One solution to building over unstable ground is to treat it like water.
You should look at it like a very, very slow river. You know, the water is flowing through it. They built the autobahn here, and there you see that's like a bridge, and that's good.
Most of this highway was built like a bridge, and it still stands, for good reason. The large piles are driven through the peat, down into the bedrock, creating a solid foundation on which to build the road. However, with the section of collapsed autobahn, the engineers had tried a new engineering technique, designed to save time and money. But as with anything untested, there was no guarantee of success.
Wir haben hier unter der Straße viele tausende dünne Säulen, die sind so 18 Zentimeter dick aus Beton. Und diese Säulen tragen den gesamten Straßenbahn. Auf den 700 Metern sind 80.000 Säulen und darauf haben wir einen Straßendamm gelegt.
Thousands of mini friction piles were driven into the peat. Cheaper and quicker to build than the bridge technique. In theory, the vast number of piles would support the road above without needing to reach solid bedrock. But in reality, it didn't work.
Es ist ein neues, innovatives Verfahren hier gewesen, um diese Torflinse zu überbrücken, dass es an dieser Stelle falsch war. Dass diese Lasten, die hier drauf liegen auf der Säule, nicht getragen werden. Dadurch haben wir dann Spreizkräfte bekommen und der Straßendamm hat sich so auseinandergespreizt und ist dann in sich zusammengebrochen.
The weight of the highway, combined with the high moisture levels in the peat, caused the mini piles to splay outwards on both sides of the road. This resulted in the catastrophic failure of the road above. It seems the mini friction piles were the wrong choice for this location.
The road builders should have gone beneath the peat with their grounding work. And what they did with these small pylons of concrete just through the peat, it was not enough.
It's always good to see engineers thinking outside the box, but this time their experiment didn't pay off.
To ensure that the repair job will be sound, Ronald Norman's team is surveying the extent of the peat problem every step of the way.
Wir wollen hier die Lagerung der Schichten neu ermitteln. Was nach dem Grundbruch hier eingetreten ist, wie haben sich die Erdmassen verteilt. Und das untersuchen sie jetzt gerade für uns. Das ist ganz wichtig. Das ist der alte Straßendamm, der jetzt abgesackt ist. Und hier unten, da unten, dann beginnt der Torf. In ungefähr jetzt 6 Meter Tiefe war die jetzt. 6 Meter.
For this massive road repair, the engineers intend to rebuild the entire section with much larger piles that will go past the peat and down as far as the bedrock.
I can't help but think why they didn't build the whole road like that in the first place.
Meanwhile, the diverted traffic will continue to take a toll on the local roads.
Now you can see construction signs coming up. They lead to probably one of the biggest construction sites in in Germany right now. Definitely one of the most spectacular ones. The official speed limit right now is 60 kilometers per hour, but there's so much traffic that we can only go 15 kilometers per hour right now.
The village of Landorf should have benefited from the bypass, but is now congested with many thousands of cars a day.
Wird auch uns im Schlaf belästigen. Das hören Sie durch die dichtesten Fenster und durch die dichtesten Wände.
Jetzt ist ja hier ein Verkehr, das sehen Sie ja selber. LKWs fahren hier durch. Also die Staubbelastung oder Feinstaubbelastung durch die Fahrzeuge ist ja immens.
Auf der Autobahn hier wickeln wir alle Schwertransporter ab. Hier werden unsere Industriegüter ausgetauscht und hier fahren unsere Gäste, unsere Urlauber her. Und die sind jetzt gestört. Die schicken wir jetzt alle durch ein Dorf mit sehr engen Straßen, mit scharfen Kurven. Und das ist nicht mehr flüssig. Wir haben Staus. Auch diese Einmaligkeit hier. Und das ist auch unser Problem jetzt.
Many people are angry because they are afraid that the construction will take many years.
3 years may sound like a long time, but in highway terms, this is actually good going.
When we are putting roads down in a landscape like this, we have to really read the landscape and better understand how the processes in nature are working. You might think it's easy to construct something on peat or in the peatland or on a riverbank or whatever, but then, yeah, sometimes nature strikes back.
You've got to try new solutions to old problems, and often they do pay off. Even though sometimes they end in failure, it's these experiments that push forward the boundaries of engineering.
Engineers are always pushing the boundaries, experimenting with new designs and techniques. Sometimes they succeed, other times not so much. But building on an old, weak foundation is never a good idea. For our next construction catastrophe, it's off to Portland, Oregon, and an engineering issue that's become a growing epidemic.
Some people think it's a conspiracy by the city to make driving so unpleasant that people take public transit.
And this is an issue which is driving people mad.
This construction conundrum is so bad, people are desperate. Portland, Oregon, once known as a gritty port town, it's now a forward-thinking city.
Portland is a city that so many people love. It's one of the hippest upcoming cities in the US, but it's got one major problem, and that's its roads.
The city stretches over 350 square kilometers, with almost 8,000 kilometers of roads. Maintaining the infrastructure here is an ongoing challenge for engineers, made worse by Portland's wet climate. With around 160 rainy days a year, Portland ranks third on the list of wettest cities in the US. Freezing winter storms combine with heavy rain to trigger a major engineering problem. Portland's streets have reached breaking point. While some of the potholes might be small, the scale of the problem is huge. As local journalist Marty Smith demonstrates.
Boom. Oh my God, look at these. Everyone agrees that the streets of Portland are in bad shape, and no one can agree on how to pay for that. You can't convince somebody that the street needs to be fixed and we need to put money into it until it's literally falling apart and your teeth are chattering out as you go over them. Like, here's a giant one right here.
The real costs of this engineering epidemic spiral ever higher, with damaged tires, suspension, car bodies, and even injuries to pedestrians.
Cowabunga.
Heavy traffic and Mother Nature caused the damage, but there's a fundamental problem with the way the roads are built.
Road surfaces in America are made of asphalt, and this is largely an aggregate of gravel and tar and other things.
Binding gravel and sand with tar, known as bitumen, creates a hard-wearing asphalt surface for our roads. Erdem Koleri is an asphalt expert.
So you make the asphalt mixture by using the asphalt binder. So this is the black part, and then you heat this to high temperatures, and then you mix this with the aggregates and recycled asphalt material to produce these asphalt concrete mixes you see here. So these are two samples that we produced in the lab. So you can see that they look brand new because they have black color on top. It's actually taken from a highway section in Oregon. And when you compare this to our lab sample, so you can see the color is very different. So asphalt is also aging over time and oxidizing, and this oxidation is actually making the asphalt more brittle and reducing the cracking resistance of asphalt.
The surface starts out strong and flexible, but age, weather, and wear and tear take their toll. As the road turns brittle, it cracks, allowing Oregon's wet and cold climate in to wreak havoc. But the cracking is only the start of the problem. A long history of resurfacing roads by laying new on old, like wallpaper, makes things much worse. Michael McGee heads up one of Portland's road maintenance teams.
Water hits the surface, it works its way through the cracks, it makes its way to the next layer of cracks, and it gets down there, and it wants to go down, and you can see the cracking that's occurred on top of this in this large pothole. And then below that is the layer of the asphalt that was before that. That might be 15, 20 years old. And you can see the cracking that's existed in that part of the road. And then here's probably the original roadway, which is probably 50 or so, 60 years old. And I bet if we opened this up, we'd see even more cracking. So when we have these really deep potholes, that's because it's gone through layer after layer after layer of asphalt, because we have cracks below cracks below cracks.
The asphalt surface sits on older layers, resting on rock, gravel, and sand, known as aggregate. When new, the surface is waterproof, but with age, small cracks form. As water gets under the asphalt, the aggregate expands, and the cracks in the asphalt grow. As trucks and cars pass over the weakened surface, it breaks up and is forced out, creating a pothole.
So you can see, if you look beyond here, you'll see that we have surface cracking. A lot of them call it alligator cracking because it looks like alligator skin. All those cracks right now, there's water that's seeping down below there, and it's going to reach that next layer, and as people drive over it. So this is a future pothole that's going to come if we don't do something with it.
During the winter of 2016, Portland's pothole problem got much worse as the city was hit by a barrage of storms, the heaviest snowfall since 1995, and almost 30 centimeters of rain. It was Portland's wettest winter on record. The pothole problem escalated, and by spring, the city was receiving around 50 pothole-related complaints a day, an increase of over 350%. With their roads crumbling, engineers have only two options: repair the potholes one by one, or resurface the entire road.
To fully fix the road is about $150,000 per mile, and that's just the road, to take out the road surface and put it back, not including any utility work or other things. Just to fix this one individual pothole costs us about $500.
Resurfacing is not only costly, but disruptive to road users. So, for now, the crews are tackling Portland's potholes one by one.
They heated up the surface to make sure that they try to get it up to temperature and make sure there's no more moisture or any debris in there.
The binding agent, or tack, is also heated to remove water. The team knows just when to stop heating and call in the asphalt truck.
And that's what they call turn or break, and that's how they know when it turns black that it's ready to go. That's essentially the glue that helps everything, gives it a head start to stick.
There's also an art to knowing how deep to fill the hole for a smooth ride and to prevent a new hole from forming too soon.
The trick of that is, where the craftsman is, making sure you get the right amount of mix in there. You saw that he left it a little bit high because when he compacts it, it's going to go back down a little bit. So he has to judge how much asphalt to put in there to make sure that it doesn't end up too low or too high. This is a very low volume street, not a lot of traffic, but we still want it smooth. We want it smooth for the people that use the road, but also when it's smooth, it's going to be a lot more durable because then the wheel will just go right over the top of it.
Meanwhile, the key to smoother roads in Portland lies in advances in road surfacing technology to make them more flexible and crack resistant.
So the new strategies are using polymers in asphalt mixes. So this is, for example, a polymer modified mix that is used in Oregon, or using some asphalt, rubberized asphalt, putting some rubber into the asphalt mix to improve the flexibility of the asphalt mixes. There are also different strategies like using fibers to improve the strength of asphalt concrete materials. For example, they are using fibers coming from bulletproof vests, and they are recycling those and using those in asphalt to improve the cracking resistance of asphalt mixes.
The process of patching Portland's potholes seems to be a never-ending story.
Frustrated with the road's shortcomings, local businessmen like Trey Shannon have found alternative means of raising revenue.
We thought as a business it would be great to create a pothole donut, which is basically a bar that's dipped in chocolate with Oreos, and then that was the lane. These, I think we sell these for $2.75 or something, and maybe 10% of sales or something could go to help with the roads. Imagine if 500 businesses did it. Maybe just the community itself could fix these problems as opposed to just putting it on city government, for sure.
Until money can be found for a long-term solution, Trey has decided to take matters into his own hands.
So here what we're doing, we're gonna fill this hole here with some donuts and see if we can. I hit this thing every day on my way to work. It just drives me crazy. So I think, yeah, right here, let's throw some donuts in there, Kevin. There we go. And I think a couple of cake ones. I love it. That's probably good. I think it's me trying to be an outstanding citizen in a way. Now let's see what happens here. That donut right there that's got the eyeballs, that's the Portland cream. So that's the official donut of Portland, Oregon. Yeah, see that? It looks great. It's phenomenal. It just squirted perfectly. It's got the whole thing. It's all level.
As much as I like the idea, I don't think the donuts are going to cut it in this case.
Civil engineering at its best.
Engineers are behind some of the most ambitious projects on the planet, shaping the world we live in. But sometimes, a catastrophe can be a reminder that in the end, nature will always win. For this next calamity, we head to Greece and a deserted mountain village.
It looks like a war zone. Like, what happened here?
What seemed a small engineering decision might have caused a sudden catastrophe.
I've heard about a moving house, but a moving village?
The village of Rapoto, in the central Greek uplands, perches on the sloping sides of Mount Koziakas.
When most of us think of Greece, we think of these vacation spots, these beaches. But in actuality, much of Greece inland is these rugged mountains.
This picturesque village, famed for its orchards, was home to over 300 families. Until one night in 2012, when the entire village started sliding down the mountainside.
Να βλέπεις να πέφτει ένα σπιταπεδό και να λες τι γίνεται.
Όλα κυλούσαν καλά, μέχρι που συνέβη όλη αυτή η καταστροφή.
Ήταν καταστροφή ανάμεσα του χωριού.
Villagers like Argyris Siolos will never forget that night.
Θυμάμαι ότι έγινε ένας πανικός, να μην ξέρεις προς τα πού να πας. Και φύγαμε έξω από εδώ και από εκεί από την καθολίστρια να μην μας σκοτώσει τουλάχιστον, όχι τα πράγματα άστα και τα σπίτια. Ο άνθρωπος να μην σκοτωθεί.
The event is still painful for Georgios Roubis to talk about.
Πανικοβλήθηκε ο κόσμος, πέταγαν τα πράγματά τους από τα παράθυρα όλοι έξω, τα πέρανε, φύγανε. Ήταν σε μια καταστροφή, αυτά έγιναν εδώ.
Overnight, residents were forced to flee. Damage to the architecture and infrastructure was catastrophic.
Το ήταν το σχολείο το παλιό, το πέτρινο, το πρώτο σχολείο από το 1954. Και εδώ δίπλα ήταν τα καφετέριες και ένα μαγαζί παντοπολείο. Από εκεί ήταν πάλι παντοπολείο.
The tragedy still haunts Rapoto resident Aris Zanis.
Γύρω στα 100, κάπου εκεί. Το χωριό ήταν ζωντανό. Αλλά αφού έγινε η ζημιά που έγινε, αναγκαστήκαν να φύγουν.
The village looks like it's been abandoned for decades, and it's hard to believe that this was a thriving place just back in 2012.
Although sudden, the landslide wasn't the first in the area. It had always been a risky place to build a village. The area's steep gradient, soft ground, and high water content was a known recipe for disaster. As geologist Vasilis Marinos explains.
Now we're in a very nice sunny day, but the people living here, when it rains heavily in this area, they are very much afraid.
The fear of heavy rain is well-founded. The entire area is made up of weak rock and vulnerable to damage from water.
We are in the heart of Greek mountains, and it is a very interesting geological environment to be in. This area here, this material where the village stands, it's a very weak one. It's very soft. It has deformed a lot from tectonical process through mountain building.
The mountains in the area are made up of limestone, with a layer of weak rock called flysch lying on the top. The unstable rock gathers in valleys. The center of Rapoto sits right on top of a pile of flysch.
The mountains were formed millions of years ago and left areas of hard rock and areas of soft rock. The area where the village was built was soft.
The central part of the village, all this material has slided and not the flanks of the village. And this is due to the nature of the ground. Where people still live in, there are better rock masses. They don't have this kind of weak, soft material like in the center.
Weak and unstable, flysch is prone to landslides. Whether triggered by earthquakes, volcanic activity, or water saturation, gravity takes over and pushes the flysch down the slope. The result? A landslide.
In many cases, these areas are areas where the ground has landslided in the past, in very old times, 100 years ago, 1,000 years ago.
Όπως ήταν πάντα το πρόβλημα, κάθε χρόνο λίγο μετακινούνταν ο χώρος.
But it wasn't just natural causes that triggered Rapoto's catastrophic landslide. Another possible factor was the decision to end a 50-year-old engineering project. In the 1960s, after a period of heavy rain, Rapoto experienced a substantial landslide. Buildings and roads were destroyed.
Προβλήματα κατολίσθησης πάντα υπήρχαν στο χωριό. Διαχρονικά, πολλά χρόνια.
The buildup of water was threatening Rapoto, so mountain streams were diverted around the village using man-made channels. This prevented the ground becoming waterlogged and unstable, and kept the village safe for years to come. By the 1980s, Greece was experiencing growth. Engineers built heavier structures in the village, including a large hotel.
Ο Ξινώνας έγινε μέσω πρόγραμμα επιδοτούμενο από την Ευρωπαϊκή Ένωση. Η εκκλησία ξεκίνησε το 86-87.
Despite the development, the drainage systems around Rapoto were keeping the fragile ground dry for now.
You could say they were setting themselves up for a fall.
But in 2011, an engineering decision may have left Rapoto on the brink of disaster. Many believe the trouble began when a decades-old program to divert water around the village was suspended.
Με αποτέλεσμα όλο αυτό το νερό να υποσκάπτει από κάτω και να γίνει αυτή η ζημιά που έγινε. Πάντα υπάρχουν λύσεις για όλα.
Water built up in the soft fleisch rock beneath Rapoto, and gravity did the rest.
The water is the principal factor that triggered this landslide. And the water from the infiltration, from the rain, this created the big landslide problem.
If you don't divert it, that water's got to build up somewhere. And in this case, it's going to be underground. And if you already have an unstable foundation, that's going to lead to trouble.
Trouble that was always lurking.
Ξεκινάει η καθολής της και τα ρέματα αν δεν κλείνανε, προφανώς να μην παθαίναμε την καταστροφή.
In an area prone to landslides, whether to spend money in hopes of preventing the inevitable is always controversial. Although costly, the building of pile walls is one engineering solution to consider, as geologist Marius Vasilis explains.
We may have found some technical solutions in order to stabilize it. Drainage with building pile walls in this large landslide, in different levels you have to build this pile wall, not just one pile wall. And I discussed about the width of the landslide, it's almost 300 meters, and all this mass coming down. So you have to retain big forces into that. So you have to spend millions in order to stabilize this mass.
A pile wall is made by hammering a row of columns or piles into the ground. Standing adjacent to each other, they form a wall. Here, to stabilize the slope, they would need to reach bedrock. And to support such a large area, there would need to be more than one wall up the mountainside.
Mountainsides can be shored up using pile walls, and these are kind of huge concrete blocks that are placed underground. Now, to do so here, you'd actually have to destroy the entire village, and it would cost millions.
This would be, again, a very expensive solution. That's why this would be, in my experience, a not feasible solution.
Since the disaster of 2012, Marius has been monitoring the region for ground movement. His studies have revealed that the town has slid around 15 centimeters in 6 years.
The length of the landslide is around 800 meters, roughly. The width of the landslide is about 300.
With no cure in sight for Rapoto, instead, it's important engineers learn lessons from the disaster. When the ground is destined to shift, it's better to build elsewhere.
Είπαμε, διελύθηκε το χωριό. Όταν το σημείο αναφοράς διελύεται η εκκλησία που εκκλησιάζησε το σχολείο, πάντα παιδιά στο σχολείο, κοινοτικό κατάστημα, αυτά δεν υπάρχουν, η καμπάνα δεν χτυπάει, δεν υπάρχει και χωριό.
Δεν ξαναγυρίζει κανένας μέσα.
This really feels like a paradise lost.
Construction calamities come in all shapes and sizes, from the surprising to the huge, the frustrating to the devastating. So long as we keep building, there will always be more engineering mistakes to fix. Construction catastrophes come in all shapes and sizes. A railroad bridge brought to its knees.
The valley just looked like you would expect after a battle.
A skyscraping medieval cathedral on the brink of a modern-day catastrophe.
This cathedral has been the victim of a combination of tragedy and folly.
A massive waterway washes out one problem, but ushers in another.
5 to 10,000 of them just erupting out of the water.
And a fairy tale town living through a nightmare.
It's an earthquake in slow motion.
With big builds, even the smallest mistake can be a huge disaster. From miscalculations to misunderstandings, these are the massive engineering mistakes that only an expert can hope to fix. When it comes to revolutionary design, sometimes we can learn from the past, other times we can improve on it. But rebuilding on an old foundation can be a huge mistake. For this construction calamity, we head to Pennsylvania, USA, and a famous bridge that fell from grace.
This is a massive fail. It's utterly incredible that no one got hurt.
If a train was going over it, it doesn't bear thinking about.
What was once considered the eighth wonder of the world is now a relic of engineering oversight. The small town of Kinzua, like many other places in Pennsylvania, was central to America's steel production. In the 1880s, demand spiked and trainloads of coal were needed to feed the factories.
Railroad engineers faced a giant obstacle, the steep, deep Kinzua Gorge off the foothills of the Appalachian Mountains. The trains had to get through, so they set to work on one of the most ambitious construction projects of the day, the Kinzua Bridge.
Completed in 1882, at over 300 feet tall and 2,000 feet long, Kinzua Bridge was the tallest railroad bridge in the world.
At the time, this was pretty much the eighth wonder of the world. It was such an unbelievable achievement. Even with today's technology, this would be a challenge, let alone back in the 1800s. So to actually achieve a viaduct over that size gap was incredible.
Jerry Clark from the Bridge Foundation knows what made this build so epic.
Other railroads went around the Kinzua Valley. The bridge went across it and used every bit of the engineering technology available during that time.
To achieve this shorter direct route, the bridge had to be high, long, and capable of supporting heavy coal trains. Engineers ruled out the conventional bridge-making materials, stone and cast iron, instead choosing wrought iron.
Building a bridge of this size out of stone or brick would have taken forever, and using cast iron would have been too brittle, so they looked to wrought iron as a suitable material.
Wrought iron had another advantage too. It's malleable. So they used sheets of iron to create an innovative support structure known as phoenix columns.
These phoenix columns were made out of wrought iron that was folded around and held together with rivets, and this made them stronger and lighter.
The revolutionary design was also quicker and cheaper to build. However, within a decade, locomotives doubled in weight. This meant more strain on the bridge and more vibrations.
Vibrations are not a bridge's friend. You expect them up to a point, but here we had a tall, long bridge with trains going over. The trains were getting heavier and heavier. They had to be careful not to push it too far. The material could withstand it to a point, but whatever they did not want that material to crack.
To minimize vibrations, trains were forced to cross at just 8 kilometers an hour. Not the most practical solution, in a fast-moving world. Fortunately, an alternative was now readily available: steel.
At the time, steel was the strongest, lightest and most flexible bridge-making material around. So it sounds crazy, but they actually ripped the old Kinzua Bridge down and rebuilt it in steel.
No bridge meant no coal, so a quick construction was essential. And in just a matter of months, 120 men erected the new bridge.
90 days is all it took to completely rebuild the longest railroad bridge in existence.
The new steel bridge used the original trestle design, with large A-frames supporting the pier on top. It could now carry as much coal as the steel mills needed. But in an effort to save time, a decision was made that would turn out to be disastrous. Rather than installing new steel anchor bolts to hold the bridge in place, the legs were secured to existing bolts. They were too short, so engineers used extending nuts called collars to bridge the gap.
So replacing these anchor bolts would have taken forever. You would have needed to dig out, blast away. It would have been a real hassle. So instead, they just put these collars over the top of it.
At the time, the collars seemed a reasonable solution, but they hadn't completely factored in Mother Nature.
This quick fix did the trick, and the bridge carried freight and passenger trains for over a century without incident. In 2002, a maintenance team discovered corrosion on the bridge's legs. They closed the bridge to trains and pedestrians and began repair works. But in the summer of 2003, disaster loomed. An epic tornado spiraled towards the Kinzua Gorge. Structural engineer Brian Ember was on the restoration team.
In July of 2003, I got a phone call, middle of the afternoon, that a tornado had hit the bridge. I jumped in my vehicle right away, made the trip, and got here right about dusk. And it was clearly a tornado scene, trees everywhere, clouds and mist. I met with the crew and made my way down here to the edge of the ravine and turned the corner, and the valley just looked filled with smoke like you would expect after a battle. You could barely start to make the structure in the fading light, and you could see pieces of steel emerging from the fog, and then what was remains of the structure still standing. It was clear it was a catastrophic failure.
The 160-kilometer-an-hour tornado had sent a huge section of the bridge crashing to the valley floor.
This must have been so frustrating. They were onto this problem, they saw it, they were acting on it. So if it struck a few months later, they would have been fine. This is such bad luck.
Although devastating to the repair team that spotted the corrosion, closing the bridge had potentially saved hundreds of lives.
To have such a freak of nature storm come in and take it down was really devastating to my crew, my team, and me personally, that we weren't able to get to it and save it in time. Had the tornado arrived a year later, we'd have finished with the repairs and hopefully sustained the structure so it would have survived the storm.
The day that it fell down in there, you kind of felt like you lost a family member.
Brian and his engineering team suspected the original iron anchor bolts and new steel collars were to blame. And their suspicions were confirmed in the wreckage.
So the next morning, I went down to the valley and found these anchor bolts and couplings littering the floor everywhere of the valley, where they had ruptured and failed at almost every single pier.
The choice not to replace the iron anchor bolts with steel was catastrophic. To demonstrate steel's strength and flexibility, mechanical engineers Dr. Mark Zupin and Dr. Tim Topoleski are using a load frame.
The one on the right is 1018 steel, and the one on the left is cast iron. You can kind of see that they look similar. So looks can be deceiving. And what we're going to do is test the two of them and see what happens.
The load frame measures the amount of force required to fracture the metal by pulling it from each end. First up, the iron.
In-tension cast iron expresses a brittle behavior, or a behavior in which it'll fail without warning.
Now, the steel.
There it goes. The steel exhibits what we call ductile behavior. You'll see the specimen narrow in the middle, and that's what we call yield behavior. And essentially, the specimen is absorbing energy to allow it to handle more load. And therefore, in contrast to the cast iron, you're going to get a warning before it fails.
So, although similar, steel's structure gives it increased flexibility, whereas iron can crack without warning.
Metals can either be brittle or ductile. A brittle material like cast iron shatters when it breaks, much like glass. A ductile material like steel, though, it deforms before it breaks. So it gives you a visible warning sign that failure is about to occur. So when you use steel in a bridge, you get a warning that it's about to break before it does.
Although steel was clearly the stronger and more flexible material, the bridge's iron anchor bolts didn't fail until the tornado of 2003.
The problem was that the original designer didn't think there was going to be uplift. An uplift comes from wind blowing on the towers. When wind blows on the tower, it wants to try and overturn it, and so on this leg, there would be uplift. The original designer, he used these because he didn't think there would be uplift, when in fact there would be with a 100-mile-an-hour wind. And it turned out to be inferior, especially after years of wear and tear, and it cracked.
A combination of extreme weather and the decision not to replace the anchor bolts over a century ago was the undoing of this epic piece of engineering.
This was a hugely ambitious project, and at the time it really pushed the boundaries of engineering knowledge, and it looks like a tiny miscalculation and the use of these collars unfortunately led to the demise of this bridge.
Today, around 180 meters of the structure still stands. Rather than tear it down, it was kept as a monument to mankind's ingenuity in engineering.
Everything here could have been scrap metal, but there were people that had the foresight to say, this is worth saving. Actually, there are more people that come to the bridge after it was down than when it was up.
To prevent any further collapse, Brian and his team have devised a solution. It's no surprise that it includes steel anchor bolts, an idea that the original engineers overlooked.
When it comes to the foundations, you should never cut corners. It may have taken over 100 years, but that lesson was learned in spectacular style.
Some construction calamities are unhappy accidents, but other times, engineers really should have known better. Like this story in northern France, and a cathedral that's experienced a catalog of catastrophes.
This one is a blockbuster of a building blunder.
It seems the engineers' zeal to reach the skies clouded their better judgment.
This cathedral has been the victim of a combination of tragedy and folly.
And when modern-day engineers tried to make a fix, it almost ended in disaster.
It's a miracle it's still standing.
Beauvais, a small city in northern France. But there's nothing small about its 800-year-old centerpiece, the gravity-defying Cathedral of Saint-Pierre.
So we've got Sagrada Familia, yep, Notre Dame, yep, St. Paul's, but St. Pierre's of Beauvais.
Although little known outside of France, the ambition of this cathedral once rivaled any other on Earth. Dr. Tom Nixon is an expert in religious architecture.
Beauvais Cathedral was begun in the 1220s by an extremely ambitious Archbishop, Bishop Mars of Nanteuil, and his vision for this cathedral was really something that would trump all the other major churches in France and the region.
Most cathedrals are designed in the shape of a cross, with three main sections: the choir for the clergy, the transept, which forms the arms, and the nave for the congregation. The nave is often long and grand, but here there was an obstacle.
Now, Beauvais could never be particularly long because the site was constricted by the presence of the Bishop's Palace at the West End. So it could respond to the ambitions of its patrons by being, first of all, very wide, but it could also be very, very tall. And this church, as built, was taller than any Gothic building ever built.
And size was very important.
With cathedrals, just like stadiums and concert halls, the aim is to have as much space as possible under one roof. But of course, the taller and wider you go, the bigger the engineering challenge.
And the greater the chance of making catastrophic mistakes. On close inspection, the grandeur of Saint-Pierre is overshadowed by centuries of repairs that literally hold the building together. And it's all because the original engineers were more focused on height than stability. In fact, their drive for height was so relentless that they had to hold up the tall, unstable walls from the outside.
So it's really remarkable to be able to come up here to the upper parts of the cathedral. Up here, we can really get a sense of the way that this forest of flying buttresses supports the upper levels of the choir. And what's really extraordinary, I think, is many of these piers are still super slender.
Flying buttresses act as an exterior skeleton to support the cathedral, but are built to look ornate and elegant, not like mere scaffolding. Engineers hoped these buttresses would be strong enough to prevent collapse.
They're working very hard to ensure that the windows are not obstructed at all, so that we have this wonderful kind of sense of vertical thrust from the cathedral, even though, of course, the reality is the very opposite. What we have is gravity trying to pull this building down.
Back in 1284, Saint-Pierre's ongoing battle with gravity came to a head when a fierce storm hit the town of Beauvais. The devastating winds twisted the flying buttresses, forcing them to breaking point. Suddenly, the high vaulted ceiling came crashing down. The city didn't let that stop progress. The damage was repaired and construction continued. In the 1500s, the cathedral reached dizzying new heights, with the lantern tower soaring over the choir. Jean-Lucien Guénon, one of France's chief architects, explains.
Donc ça en fait la construction à la fois avec la voûte la plus haute de la chrétienté pour le chœur, 48,50 m. Cette tour-lanterne, dans l'esprit de Beauvais, est la tour-lanterne la plus haute de la chrétienté. Elle s'élève à plus de 150 mètres de haut.
The lofty tower was the pride of France, but it had hardly been completed before disaster struck again.
Cette flèche est achevée en 1570. Mais tout de suite, on constate qu'il y a des fissures qui apparaissent et tout s'écroule en 1573, après la messe de l'Ascension. Il n'y a pas de victimes, heureusement.
Two massive fails before construction was complete wasn't just bad luck. All of the cathedral's problems stem from one major engineering mistake: building too high without enough support from below.
In the race to tower over the Amiens Cathedral and Notre Dame, they pushed higher and higher before they had completed the lower floors, which now sounds crazy.
Defying centuries of cathedral construction logic, Saint-Pierre's was built with only the start of a key structural element: a nave.
So here we can see the junction of the 10th century cathedral, which originally extended much further to the east, and the new work, the new Gothic church begun in the 1220s, although what we're looking at here is really the transept in the very beginning of the nave, begun in the 16th century.
The ancient church didn't provide any support for the massive new cathedral. Leaving the nave unfinished was a fundamental error. The huge weight of the towering walls was pushing them outwards.
They went to all the trouble of digging 10-meter deep foundations, which would have been a huge undertaking, and yet they didn't finish off the nave, which is the essential part to keep the rest of the cathedral standing.
Fixing the damage caused by the collapses finally drained cathedral finances, and construction of the nave was put on hold for a few hundred years.
Au 19e siècle, il y a quelques projets où on veut continuer la nef, mais ça n'a pas de suite, on ne trouve pas d'argent. Les travaux suivants, ce seront essentiellement des travaux de restauration.
Although construction remained at a standstill, during the Middle Ages, architects realized the walls were on the brink of collapse. A resourceful fix was needed, and fast.
The builders weren't totally blind. They could see the building was struggling. And to stop it from bowing outwards, they installed iron tie bars.
The tie bars literally tied the walls in place, a crude but effective fix that stabilized the cathedral. Fast forward to the 1960s, and modern-day engineers thought they knew better, with almost catastrophic results.
And so it was decided to replace them, but this time not with iron, but with steel tie bars that had less flexibility. And so, whereas the old structure had a certain amount of give and take, it could respond to the winds, the new structure was much more rigid.
By replacing the iron tie bars with steel, a more rigid alternative, the cathedral had lost its flexibility, which left it at the mercy of Mother Nature.
So basically, by trying to modernize the fix, the engineers had actually made the cathedral more vulnerable than it had been for centuries.
With such a fragile piece of architecture, today, engineers keep a watchful eye on any change in the cathedral's stability. Saint-Pierre is closely monitored, using modern technology. Constant Chacoz and his team use highly sensitive sensors to detect the slightest movement.
On this pillar, we can see optical strands fixed onto the structure. Optical strands are very accurate sensors dedicated to the measurement of strain and displacement of the structures. The resolution of these sensors is about 1 micron. Micron is 10 smaller than hair.
1 micron might seem like a tiny amount, but when you've got thousands of tons of stone shifting around, I'd want to know exactly what was going on.
While monitoring for modern-day movement, Guillaume Caron is laser mapping the cathedral in 3D to check for hidden defects in the original construction.
This image is a kind of blueprint, but made from a 3D digital model of the Cathedral of Beauvais. And what is interesting from this information is it's not a manual drawing, it's got from measures. So from this blueprint, or digital blueprint, we can highlight some deformations and to measure exactly, for instance, the distance between each pillars in the cathedral.
Laser scanners bounced high-energy light off every surface in the cathedral, creating a highly detailed picture of the building. It was so detailed, they could see things that weren't visible to the naked eye.
What Guillaume's team has discovered is more than a little disturbing.
So, using this image, for instance, we are able to highlight that the pillars that are on the southern part of the choir are very nicely aligned, but there are some misalignments between the ones in the northern part.
These misalignments have remained undetected throughout the ages, but reveal a whole new instability threat.
We were surprised by these deformations and the fact that the building is still not collapsed.
To further stabilize the walls, engineers have taken the radical step of installing giant braces.
The braces, they're not pretty, but at least the cathedral is still standing.
This building is clearly a survivor.
Engineers building groundbreaking projects have to consider every worst-case scenario they can dream of. But sometimes, even the best-laid plans can turn dreams into unexpected nightmares. Our story begins in Illinois, where a radical piece of engineering dating from 1900 has inadvertently opened the Great Lakes to invasion.
5 to 10,000 of them just erupting out of the water. I've been struck in the head, one who nailed me right in the thigh.
This Army engineering solution is truly shocking. Chicago, Illinois. In the 19th century, the Windy City grew from a staging post to one of the most influential places on Earth.
Home to hot jazz and deep dish pizza, Chicago is the place to be. And in the summer, there's no place you'd rather be than on the nearby shores of Lake Michigan.
Lake Michigan is one of North America's 5 Great Lakes, the largest group of freshwater lakes on the planet. Jennifer Caddick represents the Great Lakes Alliance.
The Great Lakes region supports a multi-billion-dollar tourism industry, but there's also a thriving hunting and fishing economy in the Great Lakes region as well. People come from all over the world and all over the states to hunt, fish, and recreate here.
By the late 1800s, Chicago's rapid growth posed a problem: more and more sewage.
Back in 1900, Chicago had problems that their sewage, all of their waste were flowing into the Chicago River, and then that was flowing out into Lake Michigan and right towards their drinking water intakes.
To stop sewage from contaminating the fresh water of Lake Michigan, engineers came up with an epic idea: to send the city's waste in another direction by reversing the flow of the Chicago River. Work began on the Chicago Sanitary and Ship Canal, connecting the Chicago River with the Des Plaines River, 45 kilometers away. The new waterway connected Chicago with the Mississippi Delta and ultimately the Gulf of Mexico, not only solving the sewage problem, but also creating a trade route. However, the ingenious engineers had unknowingly opened up the Great Lakes to a major threat.
I'm stating the obvious here, but connecting 2 waterways that have never been joined before sounds like a recipe for disaster.
This disaster came in the form of an invasive interloper, the Asian carp.
Initially, in the 1970s, the Asian carp were brought in intentionally to eat algae in sewer treatment plants. However, they have since escaped via flooding into the surrounding waterways and are now running rampant throughout the Mississippi Delta and right up toward the Great Lakes.
Asian carp are a highly invasive species that spawn rapidly. They overwhelm native fish, consuming their food and threatening their very existence. By the 1990s, the carp had spread to the Mississippi Delta. Today, they are within mere miles of Lake Michigan, and they are still on the move. Asian carp are not only a threat to native fish, but they can also be potentially lethal to humans. They weigh up to 45 kilograms, and when startled, they can leap out of the water unexpectedly. With a tourism and leisure industry worth billions of dollars a year, the last thing the Great Lakes need is Asian carp. To stop the subaqua menace in its tracks, an engineering solution is in place at Romeoville, 50 kilometers southwest of Chicago. It's an underwater electric fish barrier. The barrier is operated by the U.S. Army Corps of Engineers. Colonel Reisinger is in charge.
This is our control facility, which puts electricity into the Chicago Sanitary and Ship Canal. And what you see here is these are the control systems that allow us to control the amount of voltage which we want to put into the water. That allows us to have the most effect on the Asian carp that we're trying to deter here in this waterway. The input power for one of these systems is 1.5 megawatts. It's about 2,000 volts per electrode.
Colonel Reisinger is on a mission to hold back these foreign invaders.
We are standing on top of barrier 2 alpha.
Each barrier unit generates an electrical field reaching across the canal.
As the fish moves from downstream to upstream, they run perpendicular to that electric field generated. When that fish hits that low array field, our intent is to create enough voltage potential there that the fish decides it's uncomfortable enough that it just turns around and goes back down river.
Romeoville actually has 3 separate electric barriers at intervals along the canal, in the hope that if a carp gets through one, it will be stopped by the next.
Further up canal, we have barrier 2 Bravo, and then even further up from there, we have what we call the demonstration barrier. If that fish pushes through the wide array field and gets into the narrow array field where we have a higher voltage drop potential, at 2.3 volts at the surface of the water,
the electric fish barriers appeared to be a solid solution. However, recent studies suggest that this piece of engineering isn't watertight.
Tests have shown that 62% of fish could get through. The jury's out on this system. It's costing millions of dollars a year, and it might not even work.
If the electric field is undisturbed, it's hard for any fish to get through. However, when a big metal boat goes through that field, it breaks up the field, and fish can slide in the bow wake. Also, if fish are in big groups, the outer fish disturb the electric field, and the inner ones can slip through.
With invasive fish potentially slipping through the barrier, regular patrols downstream monitor and head off the problem. Expert fish hunter Justin Peterson has his sights set on carp.
Today we're looking for small Asian carp. This past summer, we caught a silver carp in a marina that was 5 miles from Lake Michigan. Carp are extremely dangerous. They'll jump into the boat. I've been struck in the head. I had a big bruise on my thigh once from one who nailed me right in the thigh.
Justin's methods are just as shocking as the barriers.
Fish get stunned by the electricity. We net them, put them in this tub. Every Asian carp that we catch is weighed and measured. It's a war on carp. I mean, we're at the front lines here, trying to beat them back, and they're trying to keep going forward. At one point, we hit the electricity, and we saw them in the range of 5,000 to 10,000 of them just erupting out of the water.
When you're at war, it's important to know your fishy friend from your fishy foe.
This guy here, that's a gizzard shad quillback, smallmouth buffalo. And this guy here is a silver carp. All these fish, they're stunned. Within 5 minutes or so, they'll be back to normal, and we'll release them back into the water. Minus the Asian carp, we don't release those ones.
Back in Romeoville, U.S. Army engineers are constructing a 4th barrier in an attempt to strengthen their defenses.
4th barrier? That tells you all you need to know about the effectiveness of the other 3.
Some people would say that building the 4th barrier is a waste of money because you're just pushing the problem along.
With the U.S. Army Corps of Engineers desperately trying to stop the advancing fish, experts are looking into other possible solutions. But to truly protect America's Great Lakes, they may have to turn back time. Perhaps there is only one real engineering solution that will work.
Long-term, re-separating the Great Lakes from the Mississippi River Basin is the complete solution. We know that there are many steps between where we are now and that long-term vision. You know, the Great Lakes are my home, and so it's so important to me, and I know to millions of other people, that the lakes are protected not only for our health, for our ability to recreate, but also for our children and grandchildren.
The impact to fisheries and to tourism could be in the millions, if not billions of dollars.
Let's hope they can save the Great Lakes and stop the Asian carp once and for all.
When it comes to construction catastrophes, decisions can sometimes split opinion, but this next one divided a whole town. For our final calamitous tale, we're heading to Germany and a town that's literally cracking up.
It's an earthquake in slow motion.
People thought about a catastrophe.
It's a disaster that's spiraling out of control.
This town is just coming apart at the seams.
This is a nightmare in a land of fairy tales.
The ancient city of Staufen im Breisgau, with its 500-year-old buildings, looks like it's straight out of a fairy tale. But in 2007, an engineering disaster began to tear this town apart. Journalist and local resident Raina Ruther opens up on Staufen's nightmare.
Those who live here around the main square, they heard noise at night. They asked themselves, why can't I close my window? Why does the door doesn't close anymore? Cracks started to appear on one building, two buildings, and people asked themselves what had happened.
The cracks continue to grow and spread.
What you see here is one of the, I would say, main affected buildings in Staufen. It's right on the Marktplatz, right on the market square. It's an earthquake in slow motion. This is what they say here.
The ancient town hall had sunk by almost a centimeter, or a third of an inch.
A third of an inch might not sound much, but if your building hasn't moved for 500 years, that's a huge amount.
After just 2 weeks, a staggering 68 buildings were showing signs of damage. And for pharmacist Peter Gasper, there was no cure in sight for this perplexing problem.
We detected some cracks in the walls, and nobody was certain what was the reason or the cause of these cracks. Some people got emotional, some people thought about a catastrophe, and so everybody was worried. If you walk through the house, you can find cracks all over the house.
Anxious residents called in geologists who discovered something extraordinary. Staufen had indeed been sinking, but bizarrely, the ground under the town had now begun to rise. The team quickly zeroed in on the culprit, a project to heat Staufen's town hall with a green energy source.
The Earth's core is extremely hot and full of geothermal energy. To harness this geothermal energy, you need to drill down straight into the Earth's crust.
This heat energy is then drawn up the borehole to the surface, where it powers heating and cooling systems. Drilling began in 2007, just before the town started to crack.
When I heard about the idea, when they wanted to repair the building, that they want to use geothermal energy to heat and cool the house, I said, what a good idea. And the town council unanimously said, what a good idea.
Free energy might sound like good news, but to reach the heat, engineers unintentionally triggered a slow-motion earthquake.
To tap into this geothermal heat, they drilled a hole about that wide, 6 inches, about 140 meters or 459 feet down into the rock from the surface.
There, they reached the water table.
Anywhere on the Earth, if you drill down deep enough, you're going to hit something known as the water table. And this is when water from the surface trickles down and settles at a certain level. That level will differ in height depending on where you are, but it's always going to be there. When they drilled down into the water table, there was an initial drop in pressure, and on the surface, things began to sink.
Loss of water explains the ground sinking, but with the town rising, something else had to be going on.
After further investigation, the geologists realized the problem. The town was built on this anhydrite.
Anhydrite was formed millions of years ago by the evaporation of salt water on ancient seabeds. Environmental scientist Konstantin Kinzua explains.
So there's basically just a big layer of anhydrate right underneath of Staufen.
This commonly occurring mineral rapidly absorbs water.
So when anhydrate and water mix, it expands and forms gypsum.
The expanding gypsum creates subterranean pressure.
Imagine the layer to be like something like a sponge, and you pour some water on it so it expands or it bulges up right at the spot where you pour the water on it. And the surface itself bulges the same way. So if you have a house standing on top of it, the floor is basically tearing apart.
The geothermal boreholes had brought the anhydrite in direct contact with the water table.
What I have here is a normal diaper. What this diaper has, and basically every diaper has, is that it has superabsorber in it. And this superabsorber is going to act as our anhydrate. And once I pour water over it, it's slowly going to absorb the water. It also increases in volume by quite a bit, and that's the same thing that the ground is doing as well. So this is exactly what's happening underneath of Staufen.
More than 10 years on, and the city continues to rise and crack.
You've got to understand that this is relentless. Slowly but surely, the ground under Staufen is rising.
Parts of Staufen have risen by up to 60 centimeters, and over 270 buildings are now damaged.
So we're now right inside the town hall, and you see the cracks and the uplift, which has done all the damage to this ancient building. Well, this crack, you see, it's one that starts right down in the basement of the building, comes up here, and you see the damage that has been done here to the building. This is a kind of logbook of the cracks, and when people started realizing, you see that they marked the number of centimeters that the building has moved. So we come up here in February, 6.9, in not even 1 month, in 10 days. Then if you add this all together, it comes at this 15 or 16, even 17 centimeters.
With their buildings crumbling around them, the people of Staufen desperately look for a solution to their anhydrite nightmare. With the city in pieces, local authorities are working on a fix. The first stage was to plug the boreholes to prevent water from the surface from adding to the problem. Local geologist Sandra Heisler reveals how the town papered over the cracks.
Als man dann festgestellt hat, dass eben die Problematik dann mit diesem Anhydrit zusammenhängt, hat man dann eine Lösung gesucht, und dann hat es 2 Jahre gedauert, bis man das wieder geschafft hat, diese Bohrlöcher abzudichten.
But sealing the holes from above was not enough, as the anhydrite is still in contact with the ever-present water table.
Hat man eben hier eine Pumpe installiert, weil man in 140 Metern das artesische Grundwasser hat, was man abpumpen möchte, damit es nicht weiter nach oben steigt.
By continuously pumping up groundwater, the process is slowed.
Also es ist von diesen 10 mm pro Monat, ist es runtergegangen auf 1 bis 2 mm. Also es hat sich verbessert, aber eben ist noch nicht zu Ende.
Pumping out the groundwater is helping slow the destruction. But it's not a proper solution. It's like putting a Band-Aid on. But for now, all they can do is keep pumping.
It's impossible to stop the anhydrite from absorbing water. Instead, residents must hope that it will cease naturally in time.
Da kann keiner was dazu sagen. Da gibt es keinen Zeitrahmen. Man kann nicht sagen, das geht jetzt noch 1 Jahr, das geht noch 10 Jahre, das geht noch 20 Jahre. Da gibt es keine Aussage. Das macht auch keiner.
It's estimated that repairs could cost around $60 million. This is one fairy tale that has truly become a nightmare.
I can only imagine how horrible it must be to be living in this town that's literally cracking up around you.
Engineering disasters take many forms, from sudden catastrophes to slow-burning cataclysms. One thing is for sure, The more that engineers keep pushing the boundaries of what's possible, the more hard lessons they will learn along the way. Coming up in our global quest for the greatest engineering disasters, a Baltimore sewer that's laying waste to a town.
The city is releasing tens of millions of gallons of raw sewage into the harbor.
A housing estate in Ireland with a distinct sinking feeling.
The ground has settled well beyond what the houses have settled.
An eccentric Italian count's vision for a millionaire's playground.
What Count Bagno used to call the city of toys turned into a city of disaster.
And a crossing catastrophe that nearly ran off the rails.
The potential of so many people being injured or killed, it was just a shock.
With big builds, even the smallest mistake can be a huge disaster. From miscalculations to misunderstandings. These are the massive engineering mistakes that only an expert can hope to fix. When engineering goes wrong, the fail can happen suddenly and in plain view. But sometimes calamities unravel slowly, and nobody is any the wiser until it's too late. Like this first construction catastrophe in Maryland, an engineering problem that really stinks.
This engineering blunder is enough to turn your stomach.
There's a 10-mile sewage backup underneath the city of Baltimore.
This aging sewage system was laying waste to parts of the city.
The stream flowed over. The sewage came with it.
Ever since Baltimore was established in 1729, this port town has lived and breathed water.
Baltimore is an old East Coast city, dating back to the 1700s. And like most old cities, it is fraught with aging infrastructure.
This old town has a very old sewage system. By the 1980s, the city's antiquated sewer system was among the most contaminated in America.
The early sewer pipes and storm drains were made out of clay, concrete, brick, and even wood. And as a result of this, over time, they've cracked, allowing sewage, raw sewage, into the waterways.
But it wasn't just age causing trouble with the city's waterworks. A fundamental part of the problem was the way the pipes were laid in the first place, something environmental biologist Alice Volpitta knows all too well.
Our pipe infrastructure is laid in such a way that the sewer lines, the sanitary sewer lines, are placed directly next to the stormwater lines. And both of these systems are very old and crumbling. So over time, what can happen is raw sewage can just leak out of those cracks in the sanitary sewer system and go directly into the neighboring pipe, which is the stormwater system. And once that happens, because the stormwater system isn't designed to be treated by a wastewater treatment plant, you just get raw sewage flowing through the system into the next waterway.
The storm drains that carry rain and groundwater are constructed lower than the sewage pipes which take the waste to be treated. This means that when cracks appear in the aged infrastructure, untreated sewage can leak into the storm pipe below, flowing straight into the river, which in this case is the Jones Falls.
We're here at the Jones Falls along Falls Road in Baltimore City, Maryland, and today we're going to be taking some samples of effluent from a stormwater pipe to see if we can find any evidence of sewage contamination. This is supposed to be part of the stormwater system, so that means that after about 48 hours of dry time, there shouldn't be any liquid running out of these outfalls. But this spot is chronically contaminated, so in the past we found sewage contamination coming out of these outfalls. We can do an ammonia test to see if there's any ammonia present in the water. And if there's more than 0.3 milligrams per liter of ammonia in our water, that's a really good indication that what we're seeing is sewage. Okay, so we have a reading of 0.58 milligrams per liter of ammonia here, and anything greater than 0.3 milligrams per liter is a pretty good indication of sewage in the water. The ammonia test is indicating that we have sewage in the stormwater right now. So now that we've identified a potential sewage leak, we're going to report this to Baltimore City so that they can conduct their own follow-up investigation, find the problem, and fix it.
Baltimore's stormwater flows into a stream called Jones Falls, and it's unsurprising that effluent from the cracked sewer pipes found its way there.
It's a problem that long-suffering residents like Helena Hicks have encountered far too often.
The Jones Falls is really our sewage system. So the fact that we get raw sewage, I guess, shouldn't be a surprise, because that has been the sewage line for Baltimore forever.
The contamination isn't just a local problem. The Jones Falls River runs directly through Baltimore, so much of the city is affected. Environmental journalist Tom Pelton has been monitoring pollution levels in the downtown Inner Harbor area for years.
It looks beautiful, but when we did sampling of the bacteria levels in the harbor, we found that 35% of the time, fecal bacteria levels are too high for human contact.
The level of effluent in this city's harbour has been 400 times above safe levels.
So that's a serious public health problem when we have kids playing down here in canoes and kayaks and the dragon boats that are very popular. It's not safe. And we had some public health experts look at the data and say that there should be warning signs for the public not to have contact with the water. If we could only clean up the sewage problem, it would be a place where we could fish and swim and enjoy without having to wear rubber gloves to avoid the bacteria levels.
In 2002, Baltimore was told to clean up its act and sued by the Environmental Protection Agency every time raw sewage was discharged into the river. The city had until 2016 to fix things once and for all, or face massive fines.
It's a problem that the U.S. Justice Department sued the city over, and now the city is compelled to fix its leaky sewer system.
One of the city's solutions is to close and repair sewage outflow pipes to prevent cross-contamination. The fix will include 460 kilometers of so-called cured-in-place pipes inside the 23 original sewer lines. Cured-in-place pipes are created by inflating balloon-like linings made of resin, fiberglass, and felt within cracked pipes. As the pipe is inflated, the material hardens or cures and seals the old walls from the inside, eliminating the need to replace them. Engineers also regularly examine the lines with a remote camera for any new cracks or root growth that has damaged the pipes. Jeremy Richards is helping the city to flush out the problem.
Today it's an investigation. The city is looking to see the condition of the pipe, on what their next step for maintenance would be, whether there's an issue where it would need to be replaced. It could be lined or nothing at all. This is a clay pipe that's probably 70, 80 years old. It's broken in this location.
Any damage to the clay pipes has to be fixed to prevent soil and roots from clogging them and to stop sewage getting out.
At some point, if it isn't repaired, this will fall out of the pipe. This will be missing. and what you will see is more than likely soil or the gap that it has left.
This is a long and ongoing project. By 2016, not only had Baltimore failed to fix its pipes, but that February, one of the heaviest storms ever to hit the city made this sewage nightmare a whole lot worse.
What was happening was the sewer and the storm drains were so full that this household toilet waste had just nowhere to go. And so it ended up backing up into people's basements.
Nearly 10 million gallons of untreated water was released into Baltimore's waterways, carrying with it bacteria and viruses that could cause diseases.
Gradually, the more homes they built, the more the underground water system started finding its way into the neighborhoods.
Officials realized that their problems were compounded by building part of the city on a floodplain. Floodplains are areas of flat land beside a river or stream. The level ground makes them appealing for construction. But as the name suggests, they are also at much greater risk from flooding.
When we had the big flood, which put us on the map, where most of the homes flooded, then they began to realize what they had done, that they had built a neighborhood really on top of an active stream bed.
It doesn't take much imagination. If you put a building on top of a watercourse, be it a river or a stream, you're gonna get some flooding.
Once again, Baltimore had to act and took a huge step towards cleaning up the city's sewage problem. They're building a $430 million water treatment plant, the Headworks project, scheduled for completion by 2020. Monty Simon is project managing this ambitious construction.
So we're currently standing in our core stream facility. In about 24 months, you'll have this online and we'll be treating about 800 million gallons a day of sewage. At the end of the day, this project is very large. It's going to solve about 80% of the sanitary sewer overflows that are in this collection system. Directly for the citizens, you're going to have a lot of the backups into the houses and whatnot will be taken care of. And also your surrounding waters like the Inner Harbor and the ultimate Chesapeake Bay will be cleaned up by this project. So I think it'll be a great benefit to all of the citizens of Baltimore.
It might have taken decades and will ultimately cost billions, but it looks like Baltimore is finally solving its sewage problems, although some residents remain skeptical.
We're not sure whether or not the Headworks project is going to fix all of our problems. I certainly do hope that it reduces sewage overflows because sewage is the #1 pollutant to our streams and our harbor, and it's causing the waterways to be unsafe to recreate in, to fish in, to boat in, swim in, and it's also really causing a lot of ecological damage to our waterways.
The good news is, though, this problem is finally receiving the attention and investment it deserves.
There's so much potential down here at the harbor. It's such a gorgeous place, and if we could only clean up the water, it'll be so much more attractive to the businesses and the restaurants and all the condos and homes.
Some engineering disasters develop over time and become harder and harder to live with. But when a construction calamity suddenly comes to a head, the outcome can be life or death. For this story, we head to Ireland and an engineering catastrophe that came to the end of the line.
Hundreds of people's lives were at risk.
Only luck prevented this construction calamity from becoming a major disaster.
Potential of so many people being injured or killed, it was just a shock.
If this train were 10 minutes late, it would have ended in tragedy.
Malahide in Ireland lies just 16 kilometers north of Dublin. this sleepy coastal town enjoys all the benefits of seaside life. It's also home to the Broadmeadow Viaduct that carries more than 10,000 commuters a day over the Broadmeadow estuary to Dublin. But on August 21st, 2009, this small community was nearly derailed by catastrophe. Rail spokesman Barry Kenny remembers the events of the day.
It was a Friday evening, people were commuting home from work. It was a lovely sunny evening. And our line here is a very busy line. There'll be 17,000 people every day who cross it. So a train crossed going north. And then the southbound train came along about 95 seconds later. And as it was crossing, the driver of the train, Keith Farrelly, noticed splashing coming up beside his train.
Water splashing from the sea onto a 200-ton train might not sound like a big deal, but the driver immediately knew that something was very wrong. The bridge appeared to be collapsing beneath the train, as rail spokesman Barry Kenny recalls.
The driver of the train, Keith Farrelly, looked to his side. He could actually see that the pier on the viaduct was giving way, realised the danger that he, the train and the customers on board were in, and reacted perfectly in terms of putting the train into coast. And he immediately contacted our signaller. So within 7 seconds, the signaller had been alerted, and another 15 seconds later had set all signals to red to make sure that no other trains could enter the section. Keith, when he got to Malahide Station, then walked back and saw what was happening, and as he said at the time, his legs turned to jelly.
The driver's quick thinking had not only averted disaster, but by bringing the entire line to a halt, he prevented a potential tragedy. Train engineer Eamon Balance realized how close the town had come to catastrophe.
It was a Friday evening. I was at home and I got a call who advised me there was some problem in Malahide. I arrived in Malahide Station and walked out towards the site of the bridge. What greeted me there was quite startling. Pier 4 had been washed away, and the two spans resting on Pier 4 were lying in the water with a torrent of water flowing on, through and above them.
Quite clearly, we had narrowly averted what could have been simply an enormous tragedy, but we're also then facing extended disruption to a line that thousands rely on every day for their commuting.
Although this disaster happened one summer evening, the seeds of the engineering failure were sown more than 150 years earlier.
The railway was built in around the early 1840s. The original viaduct was made of timber, and it was supported into the seabed using timber piles.
Because of the strong tidal flow in and out of the estuary, the timber piles supporting the first bridge were susceptible to erosion. To reduce the volume of water washing in and out, a stone weir was constructed along the entire length of the structure.
Basically, they built an embankment which is substantially underwater to protect the piles from erosion.
This embankment, or weir, was made of large stones placed underwater around the timber supports.
A weir can be used to control the direction and pace of a river, protecting structures like the bridge from erosion.
To replenish material washed away by the sea, engineers would drop stones from the train through the gaps between the rails as they passed over the viaduct.
In 1860 approximately, they built a new bridge. And the bridge was built of wrought iron construction, resting on masonry piers.
In the 1960s, the bridge was replaced again with a modern concrete structure which wasn't susceptible to erosion. But engineers had overlooked one crucial thing.
The installation of the new concrete beams meant you had a solid floor on the bridge, and it was now impossible to replenish the weir by trains dropping stones. The solution arrived at was to grout up the weir. This basically involved injecting liquid cement into the stone structure. So in fact, they grouted up the entire crest of the weir under the piers all the way across. This was thought then to remove the need for future maintenance. It basically locked the stones in place.
Grout is a dense liquid like glue that binds the rocks together underneath the water. However, it's permeable, so water can flow through.
Back then, engineers thought the grouting solution was a permanent fix to an age-old problem. So over time, the aging weir supporting the bridge was forgotten, as accident investigator Jill Lowry discovered.
Historically, information about the viaduct was passed by word of mouth. However, engineers that knew about this had moved to a different division. So the engineers in place at the time of the collapse of the viaduct incorrectly assumed that the masonry piers were supported by the bedrock of the estuary, where in fact they were supported by a permeable weir.
People forgot to a great extent that the weir existed. There was no concept really of the extent of the weir and the need to maintain it.
With old structures like this, the original plans can sometimes be lost in history, lost in the ether. No one knew what was underneath.
In 1997, an inspection was carried out, and engineers discovered that the weir under Pier 4 was eroding. But it seems the report was misfiled rather than acted upon.
There was a hidden problem. The grout was being washed away slowly, and the weir was becoming again a non-confined structure. It was becoming unstable.
Just 7 days before the catastrophic collapse, an unintentional inspection was carried out by local resident Ivan Barrett. While Ivan was kayaking on the estuary, he spotted something alarming.
We went out paddling on a Friday night, and we discovered that a rock had been washed away at the base of the fourth pillar, and the flow, instead of going right through the centre of the waterway away from the pillars, was now being diverted against the pillar. So after the weekend, on the Monday morning, I made a call to Irish Rail, explained it through, and I suppose even at that stage myself, I thought there was a danger, but not imminent, that I thought maybe months out something may happen. But as far as I remember, the course of the conversation said, well, look, if something isn't done about this at some stage, there is the potential it's going to fall down. I subsequently discovered Irish Rail did have a look at the bridge and the structure on the Wednesday.
From the photographs that the engineer took, we can see that there was serious undermining of Pier 4 occurring. Tunnel-like erosion started occurring. A whirlpool had formed around the base of Pier 4.
Years of erosion had weakened the piers, and without sufficient maintenance, the outcome was inevitable.
2 days later, the fourth pier gave way, taking a piece of bridge with it and almost a train full of people.
Thanks to the quick thinking of the driver, disaster was averted. But Irish Rail was under pressure to come up with a more permanent solution.
For Pier 4, which was washed away and in fact never seen again, we never even found the pieces of Pier 4 because of the fast-flowing water, it was determined that a totally new pier would be piled into the seabed.
Pier 4 was completely rebuilt, and the remaining piers were reinforced by driving steel piles deep into the seabed.
It was determined that the weir could be reinstated safely to a new design with heavier materials and a new shape profile.
Thanks to new solid foundations, this bridge won't be going off the rails anytime soon.
The tracks were just dangling in mid-air. If a train had gone over them, it would have ended up in the estuary.
The legacy that remains with locals and commuters is that a great tragedy was narrowly averted.
I think there was a sense of what didn't happen. At the back of their minds was like, but you know what? It happened and nobody was hurt and nobody was killed.
I remember how shocked everybody was when they realised the only reason people noticed this was because a driver saw it at the corner of his eye, and if he didn't, dozens of people would have been hurt.
Although this event was shocking, one good thing did come out of the reconstructed viaduct.
A major positive development out of the incident was that Irish Rail then met with both the Malahide Scouts leadership and members of the Irish Canoe Union to see could they include something within the redeveloped foundations that would help our canoeing programme. So beside the fourth pillar area, they put in a basically a sluice gate. It's 28 meters long, and it provides a route for canoes to go down, and it throws a whitewater wave up on the bottom, which makes for very good whitewater canoeing, and it's a really excellent training area.
It's great that some good has come from this, but let's hope that lessons have been learnt.
You've got to take your hats off to that train driver. His cool, calm actions under such pressure may have saved not only his life, but the entire train full of people.
Most engineering projects are built with society's best interests at heart. But sometimes, construction enterprises are born as flights of fancy and end in disaster. Like this story in Italy, with an engineering project that was the downfall of a whole town.
Count Bagno completely flattened off the ancient village of Consonno.
A count with a grand plan and an appetite for destruction.
Conte Mario Bagno la fece abbassare con gli esplosivi.
This is every architect's dream turned into a nightmare.
An ambitious construction that was sliding out of control.
One man's vision just kept slipping away.
If you fight nature, nature will fight back.
Consonno nestles in the foothills of the Alps in northern Italy. Villagers lived here peacefully for hundreds of years. But all of that changed in the second half of the 20th century, as former Mayor Antonio Giraldi recalls.
Fino al primo dopoguerra, 1950-52, tutti lavoravano la campagna e così. Poi ha incominciato a svilupparsi un po' l'industria a valle e quindi qualche persona ha incominciato ad andare a lavorare nell'industria e così via.
With villagers taking jobs in nearby towns, an eccentric Count Mario Bagno saw an opportunity to buy up land in Consonno and build his dream.
This guy wanted to build his own version of Las Vegas in Italy.
The Count's vision included a casino, nightclub, shops, and restaurants, a millionaire's playground. Environmental engineer Franco Cavalieri remembers the inspiration behind this bizarre project.
In the early 1960s, Italy, and especially this part of Italy, north of Milan, was experiencing never known before wealth. And they wanted to live like the Americans. They were watching on TV movies from Hollywood, and they were admiring the American way of life. And Mario Bagno wanted to leverage on this, and he started to build this place following Las Vegas or Disneyland.
The Count had the perfect plan, the perfect location. Even an ancient hilltop village wasn't going to stand in his way.
Mario Bagno wanted to make money as quick as possible, so he bought this place cheap. He completely flattened off the village, the ancient village of Consonno.
It simply beggars belief to blow up a village that's been there for centuries. It seems like madness.
While obliterating a 1,000-year-old village was no problem for the Count, historian Katia Brilli believes it was devastating for residents.
Many old people who had been living their entire life here in the village were very resented of the idea of moving away, of leaving their old idyllic town and change totally their own life. So this represented a great trauma for many people, especially the older.
With the village destroyed and the people displaced, Count Bagno could begin his elaborate construction. With the relaxed building regulations of the 1960s, as architect Anko Racek makes clear, the Count had a free hand to realize his vision.
People didn't really take into account the environment, they didn't take into account any context, and as we can see, it was possible for someone to come purchase a whole place and flatten it completely just to build his dream.
What's more, as Giovanni Zardani expands, the unconventional Count had his own inimitable style.
La particolarità di Consonno è che Bagno aveva messo un sacco di stili, dallo stile arabo a una pagoda cinese, che stava tra due fontane, con queste sculture per l'epoca moderne, che avevano all'interno una palla da discoteca, quella con gli specchietti, che veniva fatta ruotare dall'acqua che cadeva, illuminava tutta la zona. Alle spalle della fontana vi era il grande Hotel Plaza e all'interrato il Night.
Very kitsch, very tasteless, completely different from the traditional Italian taste for life.
They called it the city of toys. So it was this playground for the rich, for the elite of Milan, where they were gonna go and spend their evenings, spend their money in a beautiful location.
The City of Toys opened while construction was still underway, to huge excitement.
It was the 60s. It was new and exciting. If you had money to blow, this was the place to be. And people loved it.
The rich and famous came from all over Italy to revel in the Count's exclusive creation.
This was a real big kids' playground. A casino, restaurant, nightclub, a multitude of shops.
No, all the spaces here were shops for tourists. Here they were selling all kinds of usual, regular gadgets and items and gifts for tourists. Nothing particularly interesting, nothing particularly tasteful, really kitsch. But it was the core of the places, the shops, where people spend their money.
Era occupata da un ristorante panoramico, queste erano tutte le finestre del ristorante panoramico, e poi iniziava la galleria dei negozi.
But the fun was short-lived. Soon after opening, the resort began to lose its footing, quite literally.
It was not long after the Consonna opened to the public that what Count Bagno used to call the city of toys turned into a city of disaster. The road originated to Consonna was hit by landslides. There were 6 of them, and they all took place in different times. Over the 10 years the park was open.
A landslide is usually a rather sudden event and can have devastating consequences. In this instance, car parks and roads were completely destroyed.
Constant landslides meant constant repairs, and in some cases, complete rebuilds. It was as if the Count's dream of an Italian Las Vegas was never meant to be.
The ancient village of Consono had stood firm for 1,000 years. But once the Count built his city of toys, the village was hit by 3 landslides in just 10 years. As any engineer knows, the original vegetation on the hillside would have been vital to the town's stability.
The village was surrounded by dense forests. Now, this didn't suit the Count. But what he didn't know is the root structure was integral for the stability of the land.
The roots of the trees and shrubs were spread throughout the soil, holding the ground in place on the hillside. Digging them out to make space for buildings removed this natural protection against landslides.
There was a massive deforestation of the area, so many trees were lost, even roots were eradicated, and that left a large part of the area without the support of the roots that in the previous time kept the soil together.
The material the Count used for construction added to the problem.
He wanted to be quick, so he made use of a lot of concrete, a cheap material for building construction that was easily available, would cost little money, and would allow for a very quick building time. So with so much buildings, heavy buildings, on the top of the hill began slowly going down.
When you've got unstable ground, the worst thing to do is to build massive, heavy concrete structures. It's a wonder that some of these things are still standing.
Not only were concrete buildings too heavy, the machinery used to build them was part of their downfall.
Also, the building with the support of so many bulldozers and so many heavy trucks had a negative impact on the resistance, on the resilience of the soil, which was very soft.
As if that wasn't enough, the Count resorted to explosives to ensure the very best views for his guests.
Vedere lo fece abbassare con gli esplosivi e da quel momento gli abitanti di Consonno chiamarono la collina che non c'è più Monte Mario.
The hillside simply couldn't handle the amount of damage it had been dealt.
In particolare poi negli anni 70 ci fu una frana che bloccò l'accesso e Consonno venne completamente abbandonata tutto d'un tratto, mai terminata.
In 1976, the City of Toys Hotel closed for good, and the Count's dreams were over. But after the Count's death, another use was found for Consonno.
After the abandonment of the site as an amusement park, this place became an old people's home for several years.
It's got to be the most bizarre old people's home I've ever heard of.
And then it was abandoned again. That's when young people started to come here to organize great rave parties, and here they started to cover the place with graffitis.
In its own special way, the City of Toys continues to draw thrill seekers to this day.
Consonno è un posto molto particolare, è un posto che visto alla sera mette un po' paura.
Sì, questo posto sarebbe bello vederlo di notte, sarebbe più creepy, sì.
Consonno might be creepy, but it's perfect for playing one of Italy's less-known national sports.
A national hide-and-seek competition? This is not the playground that the Count had in mind.
Today, the City of Toys is abandoned, and the Count's grand plan to build an Italian Las Vegas lies in tatters.
There's a lesson to be learnt here. If you're more interested in making a quick buck than building in harmony with the landscape, you're asking for trouble.
As every engineer knows, when it comes to building something new, if you ignore what lies beneath, you're just asking for trouble. Like this story in Ireland, and an eerily quiet housing estate.
It's just completely deserted.
This engineering calamity caused more than just house prices to sink.
It's every homeowner's worst nightmare.
Donegal in northwest Ireland, famous for its low mountains and lush green scenery.
They call Ireland the Emerald Isle for a reason. It's this epic expanse of green landscape.
But this epic wet landscape isn't always ideal for heavy engineering projects. This is the Ryerk-on-Shaskin housing estate. Although it was built just 10 years ago, it's now a ghost town.
It looks like a scene from a post-apocalyptic movie, as if the houses have been abandoned overnight.
It's been nicknamed the Titanic Estate, not only because everyone's abandoned ship, but because it's sinking.
At first, it looks like the houses have popped out of the ground, but then when you look, you see that the ground has sunk.
Engineer Francis Harvey is in charge of assessing what went wrong.
What we're looking at here is where the ground has settled well beyond what the houses have settled. This is the entrance ramp that was constructed in compliance with the building regulations for wheelchair access and disability access, and we can see that it's fallen off completely. This is the regional tar macadam that was laid after the houses were built, and this level was the same as this, which is the bottom of the paint. The down pipe had a gully, which was immediately beside it, but it has now sank down this far. This is the soil pipe, which takes the fittings within the house, the toilets and wash and basins, etc. This pipe would have gone down as far as here originally and connected to an upstanding pipe for the sewage, but the householder would have found it necessary to keep putting in these intervening pieces to keep in touch with the ground piece, which was sinking.
the sinking around these houses is all down to the very ancient, wet, and spongy type of soil on which it stands. Local surveyor Hugh Boyle knows the lay of this land.
The main type of soil that we have here is peat, poorly drained and a saturated peat. It makes it a very unstable foundation for anything that's placed on top of that because there is movement. It pushes the ground outwards.
Ireland is well known for its peat bogs. In fact, more than 10% of the country is covered in peat.
Peat is a type of soil created as vegetation decomposes in a water-saturated environment. As peat accumulates, it retains water, forming bogs and wetlands that gradually expand with time. Peat is widely used as fuel and fertilizer, but it's definitely not ideal for building on.
The sinking estate is just about 600-700 meters south of here, and as you can see, the peat here is very, very wet. If it's not removed, it does present many problems. Peat like this can have up to 70% moisture content. It's a soft material.
When peat is wet, it continues to decompose, releasing gases and reducing its mass. It's far from ideal for foundations.
The engineers who built the houses knew all about the peat underfoot, so they designed their foundations accordingly.
The houses are standing proud because the engineers put foundations going down into the hard rock, knowing that peat was an issue.
The foundations are concrete and steel piles that pass through the surface layer of peat, supporting the houses on the solid rock below.
Piles were designed, specified, and were installed correctly. The ground beam was correctly fitted on top of it, a reinforced concrete, and then the houses are built on top of that.
So, the houses themselves are solid.
As for the roads and the services area and the driveways, these were built on top of the existing ground, but it was specified that a geotextile material would be used.
Geotextiles are permeable fabrics designed to separate, reinforce, and protect ground while allowing water to drain. Layered with stone-filled ballast, geotextiles can make peat stable enough to build on.
This geotextile material was to be covered with approximately 1 metre of stone fill, and obviously that was not done, and the geotextile membrane has failed completely, and the ground is sinking and is continuing to sink. The amount of subsidence on the ground as compared to what the houses are is in place up to ½ metre.
As extreme as it looks, this titanic engineering calamity might not be an isolated case. Another nearby community looks to be experiencing a similar issue, as local resident Liam White explains.
This estate was built about 12 years ago by a private developer, and they've been having trouble with sinkage ever since. The tower is moving out from the house. As time goes on, that'll go further and further away from the house. As you can see, the playground is a bit lopsided. The curbs are another example of the subsidence. It's a tough place to live when you have these problems outside your front door, basically.
Having the world sink around you is far from ideal. The question for Donegal's engineers is how they can combat these local peat-based catastrophes.
If it's shallow, you can scrape it away and fill in that area with something else. But if it's deep, you just have to put foundation piles going straight down to the rock below.
By securing piles into the rock beneath the peat, solid platforms can be constructed below the ground surface. As well as for houses, these provide reliable foundations for roads and services. However, for an existing estate, it's not an easy fix.
To
create platforms under the ground and around these houses will be very tricky, and not to mention hugely expensive.
The real solution here would be for engineers to get it right the first time round.
The houses weren't going to sink if only as much attention had been paid to the surrounding area.
The repair bill for this estate is estimated in the millions of euros, and more than 10 years later, these houses remain abandoned. Construction calamities come in all shapes and sizes, messy or maverick, big or small. So long as we keep building, there will always be more engineering mistakes to fix. Coming up in our global hunt for the greatest engineering catastrophes, a California dam on the brink of disaster.
I told my wife and kids we need to go now.
A Scottish landmark that risked becoming a crossing calamity.
The lifespan of the bridge was a serious concern.
In Germany, a big build that's gone completely off the rails.
This is nonsense which has to be stopped.
And in England, a blazing end to the year.
It very quickly got serious.
With big builds, even the smallest mistake can be a huge disaster. From miscalculations to misunderstandings. These are the massive engineering mistakes that only an expert can hope to fix. With epic building blunders, the fail can strike when the welds are still warm and the paint is still wet.
It's a 360-degree problem, not just one for us.
But sometimes the root of the problem lurks hidden for years.
Over time, coupling actually split.
A ticking time bomb just waiting to go off.
And it hit like a mortar round. Boom!
Just like this construction calamity in California, an engineering disaster that threatened to wipe whole cities off the map.
It was panic. People were panicking.
I asked them if this is for real, and they said, yes, it's for real.
As disaster loomed, 180,000 residents along the Feather River were ordered to evacuate.
These people could have been less than an hour from annihilation.
California is known for its endless sunshine and 1,300 kilometers of coastline. But despite being right on the Pacific Ocean, it has a long history of massive water shortages. In the 1960s, work began on a solution near the small town of Oroville.
Most people have never even heard of Oroville, but it's actually home to one of the largest infrastructure projects in U.S. history.
Completed in 1968, the 235-meter-high Oroville Dam across the Feather River is, to this day, the tallest dam in America. Built from 140 million tons of mud and earth, the dam created Lake Oroville, storing more than 4 trillion liters of water.
The dam is vital, supplying farms, cities, and towns throughout the state of California.
But as with every dam, if water levels get too high behind it, there's a risk of damage or even catastrophic collapse, which could lead to massive flooding down the Feather River. Not only a threat to the nearby town of Oroville, but thousands of people living downriver towards the San Francisco Bay. So, The Oroville Dam has a safety valve in the form of two spillways.
When the water reaches a certain height, the water flows down these spillways so the reservoir doesn't overflow.
The main spillway is a concrete chute the width of a 12-lane highway. When levels in Lake Oroville are high, control gates are opened and the water is released, flowing more than 900 meters down to the Feather River. As a failsafe, there is a secondary emergency spillway beside the chute, a fixed ridge over which water would naturally spill if levels ever topped 275 meters before rolling down the hill to the river.
Spillway is a bit of an exaggeration. The second one is basically the hillside.
The dam functioned as planned for nearly 50 years, not only stockpiling fresh water, but preventing flooding and generating electricity too. But in 2017, Northern California experienced its wettest winter in more than a century. Lake Oroville was running at 151% of normal capacity. Journalist Risa Johnson heard rumors that all was not well with the dam.
On February 7th, we got a tip that there was something going on with Oroville Dam. Someone said that they might have seen a piece of concrete fly, so we thought something was up.
The main spillway was open, but was not only struggling to cope with the flow, it was starting to break apart.
The force of the water being released from the dam broke a huge hole in the concrete spillway.
A photographer got some pictures, and that was when we saw that there was a huge hole in the spillway, and so it just really escalated from there.
The main spillway was in serious trouble. Local pilot Gonzalo Curiel filmed the disaster unfolding from his light aircraft.
Most people in town, most people anywhere couldn't see the dam. I was fortunate enough, because I am a pilot and I do have an airplane, I could go up at any time and see it and get photographs and video of it. The main spillway being blown out, to see it from the air was spectacular, you know, in a sense, but it was also scary because we didn't know what was going to happen.
There was a lot of erosion going around the sides, and there was a lot of mud in the water, and it looked really bad.
Residents down the Feather River, like Genoa Wilder, were also getting nervous.
They noticed chunks, like big rocks, chunks of cement flying down with the water. And so that was the first, I mean, it was being shared all over Facebook, people were commenting, and that was the first sign that something was wrong.
Engineers were forced to slow the flow down the damaged main spillway. But the stormwaters kept coming. Unable to drain quickly enough, the lake kept rising and was rapidly approaching the 275-meter maximum.
Seeing the storms coming in and how much water was coming into the lake and seeing how fast it was accumulating, that's when I started to get worried.
On Saturday, February 11th, 2017, for the first time in the dam's history, water started spilling over the lip of the emergency spillway.
The emergency spillway had never been used before. This was uncharted territory.
With the main spillway struggling, the second emergency spillway was the only hope for the dam to remain intact. But as the water flowed down the hillside, mud and rocks were also being washed down to the Feather River. By Sunday, the cascading water and debris had destroyed the road below. But much worse, the hillside was eroding fast. The emergency failsafe spillway was failing. If the emergency spillway suffered a total failure, experts predicted a 9-meter-high wall of water would hurtle down the Feather River. The authorities were forced to order a mass evacuation of more than 180,000 people living downstream.
I think it was about 3 o'clock. People got that emergency 1 hour, you have 1 hour to get out, emergency evacuation order.
I asked them if this is for real, and they said, yes, it's for real.
sounds like something out of a movie. 180,000 people were literally told to drop everything and flee for their lives.
The Oroville Dam was in real trouble. The emergency release spillway continued to erode as it struggled with the excessive amount of water from the recent storms. If it collapsed, the scale of the disaster would be unthinkable.
If it did actually fail and flood this area, those people would have been washed away.
They said 50 minutes. And if within 50 minutes, if that would have failed, there would have been a lot of lives lost. When the evacuation actually happened, there was like a live countdown on the news of this is when it's going to fail, this is when the water is coming. And then there's this aerial footage of the highway heading out of town and cars just at a standstill.
While the water continued to gush down the hillside, engineers tried to reduce levels in Lake Oroville. The damaged primary spillway worked overtime. Gradually, the flow down the emergency spillway slowed, and hour by hour, the lake surface began to fall. 2 days later, the evacuation order was downgraded, and shaken residents were allowed to return to their homes. This close call highlighted two main engineering issues from the original construction phase. First, geological studies pointed at the hillside that the spillways were built on. In places, the rock was too weak to support the constant battering by water. As geologist Eldridge Moores demonstrates,
I can actually pick a piece off of this outcrop right here, and I can roll it around in my fingers, and I can make the rocks, disintegrate. The problem is the emergency spillway eroded in places that's as much as 20 to 25 feet deep in a week.
But geology wasn't the only problem. A forensic report found that a key cause of the main spillway breaking up was the concrete being too thin around drains in the chute.
The concrete in the main spillway was only 7 inches thick, about 17 centimeters. It was no match for the huge amount of water pouring from the reservoir above.
All told, the spillways suffered from several faults, from poor quality bedrock beneath to multiple cracks in the chute, which allowed water to flow underneath and caused yet more damage. With the immediate crisis over, engineers went to work on a solution. To create a solid foundation for the primary spillway, the weak rock beneath it was sprayed with liquid mortar, while thicker, stronger concrete walls were added. The eroded hillside of the emergency spillway next door was reinforced with a very different solution. A so-called cutoff wall dug into the slope. Holes were drilled deep into the solid bedrock, then filled with concrete, creating a robust terraced wall designed to both strengthen the hillside and slow the flow of water. Estimates put the cost of the emergency and repairs at $1 billion, but the dam and its spillways should be prepared for anything Mother Nature throws its way.
When, this crisis happened, they were all operating under the assumption that it was bedrock and that it wouldn't erode.
This isn't the only aging piece of infrastructure in the United States. The country is full of projects that need to be inspected.
Construction calamities can strike when they're least expected, with the original engineering errors hidden by history. But sometimes, things can go wrong while construction crews are still hard at work. For this story, we're off to Germany and a mammoth engineering development that's struggling to stay on track.
This is one railway that is definitely not running to schedule.
It takes so long, the costs increases.
Nobody think it's needed.
A runaway rail project that's 6 years and 4 billion euros over budget.
It sounds like this project has gone wrong in a very big way.
Stuttgart is at the heart of German manufacturing. and the birthplace of one of the world's greatest inventions and engineering triumphs, the automobile.
Carl Benz and Gottlieb Daimler worked around this area. There is clearly precision engineering in the blood.
In 2010, construction started on a radical multi-billion euro station to speed up the city's railroad system. Transport specialist Christian Butger gets up to speed with the city's ambitious plans.
The idea was to get the main railway station in Stuttgart underground. In Stuttgart, we have a railway station that is like a terminus. The idea was that by putting everything into a tunnel, you wouldn't need to have to stop and to shunt anything, but just go through the city. It would allow the railway to get a faster connection to the high-speed lines that were thought to be built at that time.
The grand plan is to transfer the entire station underground, creating nearly 32 kilometers of new tunnels, and move from a terminus station to one that allows trains to pass under and straight through the city.
The main driver was not interest in railways, but the main driver was really city development. Stuttgart is in a valley, it's a growing city, and so they have a big pressure on real estate. By putting it into the tunnel, you could release quite a significant piece of land, and so the city of Stuttgart would love to have this additional city quarter for development.
The groundbreaking project was named Stuttgart 21 and due to be completed by 2019.
Smoother train journeys, fancier stations, real estate above. What's not to love about this?
It all sounds great on paper.
But the transformation of Stuttgart's main railway terminal into an underground station ran into trouble almost immediately. Right from the start, engineers faced a huge problem that existed long before the project ever got dreamed up: the rock beneath the city.
There is some concerns that the tunnel in itself will never be working properly due to this very unpredictable rock that is around that. And so an engineering company that did an investigation on behalf of Deutsche Bahn, they said there is an unusual big risk with this moving rock which is around that.
The geology around Stuttgart makes it really unsuitable for this kind of construction. There's something in there called anhydrite, and when that gets wet, it expands. And that's a real problem with this type of construction.
Millions of years ago, as ancient oceans shrank, crystals of the chalky mineral gypsum settled on the sea floor, forming beds of rock. When the sea evaporated, the rock baked completely dry, with gypsum turning to anhydrite.
Anhydrite comes from the Greek word anhydrous, which literally means without water. And like this sponge here, it absorbs water and expands. Definitely a problem when tunneling.
It sounds like Stuttgart is the last place you would want to put the lines underground.
Stuttgart's ambitious plan to transfer its central railway station underground was way off track. And with the project already suffering huge delays, engineers needed everything to run smoothly. But as well as unstable rock, there was another problem. This wasn't the only tunneling project in town.
Stuttgart already has a vast underground metro, so building any more tunnels is a logistical nightmare. They literally have to thread their way over and under the lines that are already there.
Local campaigner Werner Sauerborn gets to the bottom of the construction challenges.
What you see here is the S-Bahn. This is an urban train connection which goes this direction. And on the other side of the building side, we have another S-Bahn track. And now they try to bring the new tracks above those and under the other.
It's a huge engineering headache, and it's forced them to defy design convention.
To avoid the existing metro lines, they had to build the platforms at a much steeper angle than normal.
They are forced to have a big slope on the tracks. It's a slope of 6 meters from the point we are standing here to the end of the tracks. There are few stations in Germany which have a very small slope. And even on these stations, there are often accidents. Accidents with rolling wheelchairs, with buggies. And here we have a much higher slope than in other comparable stations in Germany.
By 2018, the project was 6 years behind schedule and 4 billion euros over budget. And for residents, the signals were there that this project would never be completed.
The 21 in Stuttgart 21 stands for the 21st century, but at the rate it's being developed, they'll be lucky if it's finished by the 22nd century.
There was a huge public discussion about that project, and probably we never had such an emotional discussion about an infrastructure project in Germany within the last 50 years. It really split the city.
Despite the billions being spent on the project, many experts claim that Stuttgart 21 will actually make public transportation in the area worse.
The old station had 17 platforms. The new one has only got 8.
No wonder people aren't happy.
Stuttgart commuters are still using the century-old station and are unconvinced that the new one will make things any better.
There is heavy doubts whether this tunnel now will have even the same capacity as the current railway system has. There was an estimate that for about 19% of the passengers going to or through Stuttgart, the project will get shorter travel times. For about 13%, it's going to get longer travel times. And for the rest, it won't make a difference.
That's not the end of the project's problems. It's rumored there's another burning issue they've yet to tackle.
Some believe that the station's fire safety system wasn't approved. So rather than hold up construction, they decided to put it off and add the system at a later date.
You would think that a project of this size would have sorted out something as important as a fire safety system from the very start.
Problems in construction mean the official opening date has now been pushed back to 2025. But with the troubles stacking up and a runaway schedule, some think that Stuttgart 21 should simply be shelved.
They are continuing a project which has no sense, which costs a lot of money. This is risky because it works in anhydrite and it has a platform with a much too high slope. So if you take all this together, this is nonsense which has to be stopped.
The planners, politicians, and project managers will all need to work together if Stuttgart 21 is ever going to be finished.
German engineering is the envy of the world, but in this case, it's gone off the rails.
When construction goes wrong, the mistakes can be massive without being a serious threat to life or limb. But sometimes, a small flaw can threaten a major catastrophe. For this story to Scotland and a bridge that nearly became an engineering catastrophe.
People did feel unsafe.
The lifespan of the bridge was a serious concern.
A crossing that no one wanted to cross.
I've heard of a bridge over troubled water, but this was a troubled bridge.
The River Forth, north of Scotland's capital, Edinburgh. In 1890, the Forth Railway Bridge was its first crossing and was heralded as a masterpiece of Victorian engineering. But with no room for vehicles or pedestrians, for over 70 years, if you didn't go by train, there was only one other, very slow way to get across. Engineer John Carson recalls.
I can remember as a boy here with my parents sitting on that south shore for 3 or 4 hours to catch a ferry over to just one of the villages on the north shore.
This all changed in 1964 when the Forth Road Suspension Bridge opened. The 2.5-kilometer long engineering marvel has 2 69-centimeter thick main cables with hundreds of hanging wires to support the deck below.
The Forth Road Bridge was a huge achievement in its day. It was the longest bridge outside of the United States.
The two bridges wedded together to create an iconic impression on the Scottish landscape. But in structural terms, after just 4 decades, this honeymoon was over, as reporter Alan Roden discovered.
I was told by the people who worked there that the lifespan of the bridge was a serious concern. They told me that the bridge could be closed in as few as 10 years.
The rail bridge is still going strong after almost 130 years, but the road bridge was in trouble after just 50.
Nobody puts these bridges up and expects to get only 50 years out of them.
In 2004, the first large-scale inspection of the two main cables in the bridge's history revealed a concerning development.
There are thousands of cables in a bridge like this, and in the inspection in 2004, 22 had been found to have elements of corrosion.
They might look like single cables, but they're actually made up of over 11,500 thin wires.
22 corroded wires out of more than 11,000 might not sound like much, but it's too many to be ignored, as architectural journalist John Glenday explains.
You've got many thousands of cables all wrapped tightly together in bundles, and they're all taut tight. So unfortunately, it's not as simple as just going in and replacing individual snapped cables. The whole thing hangs together as a single entity.
Engineers needed to know what caused the corrosion. Part of the problem was how and where the main cables were constructed in the first place.
The major issue is Scotland's weather. It's very temperamental here in Scotland. As you can see behind me, we get a lot of damp, moist weather. That led to corrosion. We also get a lot of dry weather as well. It's not raining all the time in Scotland, despite what people may say. So you've got a real mixed climate here.
To make matters worse, during the entire 6 years of construction, the cables were spun together on site, exposed to the elements.
The wrapping and the spinning of that went on in all sorts of conditions, so you can imagine they were built in the wet and wrapped in the wet. So effectively what happens is that corrosion sets in.
The problem was, with the two main cables under constant tension, they couldn't physically be removed for repairs. So, to detect further corrosion, engineers installed acoustic monitoring equipment using microphones along the entire length of the bridge.
What you've got is a bundle of steel wires bound very tightly together. So if something snaps in the middle of that, you can't actually see it. The only way is to hear it. So you'll have sensors which can detect the sound of the cable actually physically snapping.
So every time a strand pops, it sets off an alarm. So they can actually tell now how many were breaking.
The 2004 inspections revealed an estimated 10% loss of strength in the bridge's cables.
The 10% failure rate on a piece of critical infrastructure like the Forth Road Bridge is a high margin.
Local cab driver Julia Fredrickson remembers the community becoming worried about making the crossing.
People did feel unsafe, they were frightened to go over, and I think especially the older generation who were like, oh well, you know, what if anything happens when I'm on the bridge, not knowing how bad it was.
You know, people drive across this bridge. The idea that some of the cables that are holding their vehicle up are corroded, it's a worrying prospect for them.
Yes, Scotland's longest crossing was corroding, just 40 years after it had been built. But engineers had a plan. To stop the rot, technicians proposed a solution known as dehumidification. This had been used on similar bridges in Japan to great success.
The cables were covered and hot air was continuously pumped through, a bit like a giant hairdryer designed to remove moisture.
The rust could only thrive if the bundled cables were wet inside. Dry out the moisture and the corrosion is halted.
So the dehumidification process took around about 2 years at a cost of £8 million. It was a very innovative idea, and yes, it did actually work. It started to dry out the cables, which was a huge relief for the engineers involved in the Forth Road Bridge.
With the solution found, the Forth Road Bridge should have had a clean bill of health. However, there was another problem. which was putting a strain on much more than the cables.
When the road bridge opened, it carried around about 4 million vehicles a year. That was a lot, but it was designed for that kind of number, for a steady increase, but nothing like the massive increase that it saw.
Just 4 decades after its opening, the bridge was now carrying 6 times the amount of vehicles it was designed for.
The Forth Road Bridge had to cope with around 24 million vehicles a year, which is way more than it was ever planned to take.
That's 70,000 a day. That's a huge number.
To add to the bridge's already considerable load, the vehicles themselves had changed over the years.
The bridge itself was designed for 25-ton, 30-ton trucks maximum. This bridge now is taking 44-ton trucks. And the pounding that does to a structure like this is huge. So it not only exerts stress onto the cables and the hangers, but it also damages the decking, because the decking has supports in it spaced to cope with the old 30-ton lorries. It doesn't have spacing in it to cope with the new 44-ton lorries.
Despite the triumph over corrosion, by now, no amount of clever engineering could return the bridge to its former strength. So in 2011, the radical solution was to build another bridge.
This was the biggest transport infrastructure project in the whole of Scotland. It took 6 years to build. It was a phenomenal project, and in 2017, it opened to traffic.
At 210 meters tall, the £1.3 billion Queensferry crossing is the UK's tallest bridge, with a very different design to its troubled predecessor. A modern concept that spreads the load more evenly.
Here what we have is a mast. That mast basically holds up the whole of that structure from the ends of the cables there to the ends of the cables here. And it's built incrementally, one section at a time. And it's called balanced cantilever construction.
Balanced cantilever construction starts from the mast and works outwards, laying road sections on either side to maintain balance during assembly.
So effectively what's happening is all those little segments are being picked up and the load's being transferred up the mast and the weight's transferred down through the foundation.
The cables are laid in sync with the deck sections being placed and connected directly to the roadway from the mast. From the start, the cables are weatherproofed, acoustically monitored, and unlike its predecessor, any and all of the cables can easily be replaced. Architect Alan Dunlop believes the design is also a more stimulating improvement.
The thing about the cable structure is that, it provides a kind of elegance and very slimness to the structure itself. So not only do they perform very well structurally, it also gives a very beautiful and look to the bridge itself. So you look as though you have a bridge which is spanning over quite a large distance with a minimum of means, and it's very light and as a consequence of that, quite beautiful.
The Scottish Government wanted this, I think, to be a landmark project, and they've got a spectacular bridge. It is absolutely fabulous.
With the traffic pressure now relieved, the old Forth Road Bridge is back in business. Sort of.
The original road bridge was reopened, but this time only to public transport, pedestrians and motorcycles.
Today, this trio of functioning crossings offers a dynamic vision of Scottish engineering.
Far from competing, I think the three bridges in context add to each other, complement each other. We see through time as well as across the Forth. We see our Victorian ancestors and the work that they achieved, and we can also be proud that we're carrying that baton forward into the present day.
Building a whole new bridge is an extreme and expensive solution, but it does mean that Scotland has a state-of-the-art bridge that will keep the country moving for years to come.
For engineers, this is bridge heaven.
Construction calamities can be one-offs, a unique problem that can be put down to experience.
There could be up to 200,000 fatalities.
But sometimes, one fail is a reminder that engineering needs to keep on its toes. For this story, to England, and a blazing end to the year.
This is like a disaster movie come to life.
A shocking reminder that engineering has to move with the times.
Very quickly got serious.
This looks horrendous. It was a miracle that no one was hurt.
A catastrophe that created a scene of total carnage. Liverpool in northwest England, and it's New Year's Eve 2017. The city's main arena is hosting a huge event. At around 4:30 p.m., Sue Wright drove into the venue's already packed multi-story car park as disaster struck.
We looked to the right and there was a row of cars parked, and behind that row of cars was a car on fire. And then everybody in front of us had stopped, and everyone panicked, and they just abandoned their cars and started running to the exit. The noise was quite intense. There was lots of bangs and pops of the explosions. You could smell the smoke. People were coughing. Within a few minutes, I think within about 7 or 8 minutes, the fire brigade arrived.
Local reporter Jenny Kirkham was near the scene and could sense a breaking story.
I was heading out to another job, and I thought I'll swing by and have a look and see if, what's going on. From then, you could see smoke coming out of the different floors. It was mostly on the 3rd floor, and then it spread. You could hear the pops of the fuel tanks in the different cars and things like that, but it was mainly contained and it looked like it was under control.
But inside, the fire was raging out of control.
Around 7, 8 o'clock, black smoke just filled all of this. Everybody was being pushed back because the smoke was getting so thick and it was spreading. And then from then, the massive flames just started bursting out of the car park.
As the inferno spread, the event was canceled. Around 4,000 people fled as the area was evacuated. Drivers were forced to abandon their cars, while residents in nearby apartments were also told to leave their homes.
It was quite frightening when that kicked off. It very quickly got serious here. What started off as pops of fuel tanks was turned into full-blown explosions. It was maybe 3 or 4 going at a time.
Hundreds of cars were now on fire inside the 10-year-old building. 85 firefighters battled through the night to extinguish the raging inferno.
It's not surprising because there were over 1,000 cars.
Although the blaze started in one SUV with a modified fuel system, more than 1,300 vehicles were destroyed. But amazingly, no one was seriously hurt. One fundamental problem may be the design of multi-story car parks, as fire engineering specialist Fatih Tarada explains.
We still, unfortunately, have the situation where a fire in a car park can be tantamount to the perfect oven. The flame from a burning car actually goes up to the ceiling, which is quite low, it's around 2.2 meters, and then starts to move horizontally. So the neighboring vehicles might have it from both directions, both from above and from below. So therefore, you can have an extremely dangerous situation.
In the mid-20th century, as more cars poured onto the roads, city center car parks grew upwards instead of out. These multi-level constructions could pack in more vehicles, but the combination of low ceilings, good airflow, and sheer number of cars risked turning a single car fire into a raging inferno. Although the Liverpool car park was only 10 years old, like all car parks in the UK, its regulations are based on vehicles from the 1960s. Cars have got much bigger, but the car parks haven't. Planning expert Russell Simmons explains why design regulations need to move with the times.
So the fire risk within buildings has certainly changed, along with the design changes associated with motor vehicles themselves. And the research that was undertaken most recently, which was several years ago now by the Building Research Establishment, was done utilising cars from years ago. And since that design change has taken place in cars, we must take that into consideration in the design of car parks. The risk has completely changed.
Car parks haven't really changed. The spaces are still the same size. You've got cars, SUVs, in closer proximity to each other. So the problem is, if you have a fire, you've got the fire closer to another flammable object, and that's going to cause a real problem.
With bigger cars, you get bigger fuel tanks and more fuel.
With the Liverpool car park packed with more than 1,300 vehicles, there was a huge amount of fuel just waiting to burn. But it's not just about the size of the cars or the car park. There's another issue with modern fuel tank design.
Another reason why cars are becoming more combustible these days is because their fuel tanks are now made from plastic themselves. So if you do have a fire from a neighboring vehicle affecting another vehicle, then if the fuel tank melts, it can release the fuel, and that in itself can become a hazard and can burn readily.
Car parks were constructed with petrol vehicles in mind, but since the 60s, there's been an explosion in the number of diesel cars on the road, which is likely to have made the situation even worse.
If you release diesel, it's more likely to pool, it's more likely to collect, rather than simply evaporate and dissipate. So it's more likely to flow into other areas that can catch fire.
Per litre, diesel has got around 10% more energy than petrol, which means it's going to burn for longer. It's also gloopier, so it sticks to things. So if you imagine it's burning, you're going to get burning fuel stuck to something. That's going to cause a real problem when you've got a fire.
Just a small amount of diesel can burn around 1,000 degrees Celsius, and that's around 1,800 degrees Fahrenheit. So it's no wonder the car park was an absolute inferno.
In this fire, what happened, as I understand it, is that the first tank will have blown, that will have then cascaded the fuel down to the next car, gone to the rubbers of the tyres, that car will have gone, and then it was a domino effect.
You can see how this spiraled out of control. You've got a slope in the car park, so all of a sudden you've got this burning diesel and it's able to move around all over the car park.
So, a combination of sloping access to each level, 5-decade-old design regulations, and a growing number of diesel cars all turned this city's celebrations into a flaming fiasco.
You can't change how every car is built or knock down every car park and start again.
One simple solution could be to install sprinklers, as is the norm in tunnels in the UK.
In tunnels, fire safety is heavily regulated, but in the UK, in car parks, there's almost no fire safety regulation.
As ridiculous as it may seem, it's not mandatory to have sprinklers in car parks.
Traditionally, there aren't many systems installed in car parks, and it's very rare to actually find a sprinkler system installed in an above-ground multi-storey car park. It's much more common underground, but there's no specific requirement for a sprinkler system to be installed in any car park.
Fatih Tirada demonstrates how effective a sprinkler system can be.
What we're going to do now is we're going to have a suppressed pan fire. So we will be using a fire extinguisher, and the fire will be contained within this metal gauze frame.
With burning fuel, the spray has to be foam, not water.
You can't put water on burning fuel. Fuel, oil, petrol, diesel just floats on water, so it's just going to spread everywhere. The key is to pour on foam. That starves the fire of oxygen, and it's going to extinguish it.
This is what we might have had if we'd had a sprinkler system in the car park.
Merseyside Fire and Rescue Service said a sprinkler system would have given crews a better chance of stopping the fire, while the mayor of Liverpool believes lessons need to be learned for the future.
Despite the raging fire, The car park did actually stay standing, and thankfully nobody got seriously hurt.
Had that car not been in there, that fire wouldn't have broke out and those cars wouldn't have been destroyed. So the car park did perform its function, but I think there is questions to be asked about car park safety and what we could do to stop this happening in the future.
Construction calamities come in all shapes and sizes, from the breathtaking to the groundbreaking, the stunning to the terrifying. So long as we keep building, there will always be more mistakes to fix. This time on our global roundup of the greatest engineering catastrophes, America's first space station threatens to fall to Earth.
We had 3 mission control teams, each on for 8 hours, and we began to control the Skylab 24 hours a day.
Modern waterworks destabilize an ancient Italian town.
I'd hate to be the one cleaning up that mess.
A skyscraper that was almost sweeping people off their feet.
The height, the position, and the concave shape of the building were the perfect conditions to create the perfect storm on the streets below.
And brand new trains get too close for comfort.
This led to one very close shave.
With big builds, even the smallest mistake can be a huge disaster. From miscalculations to misunderstandings. These are the massive engineering mistakes that only an expert can hope to fix. Engineers are constantly pushing the boundaries, striving to haul the world into the future. But when those creations are right on the limits, engineering errors can be revealed in dramatic style. For this first engineering catastrophe, we're heading into orbit and a space station that threatened to crash down to Earth.
This engineering disaster is out of this world.
A sequence of engineering fails struck the station, and people across the planet looked up in fear.
Big space station, don't know where it's coming down. I need a helmet.
July 16th, 1969, and Apollo 11 carried the first humans to the moon.
It's one small step for man, one giant leap for mankind.
Apollo 11 and the 5 moon landings that followed still rank among the greatest achievements in history. And yet, these were the first small steps in a massive engineering challenge, our quest to explore new frontiers in space. As author David Hitt explains, our ambitions went beyond moon rockets.
From the beginning of planning for space exploration, there was an understanding that at some point, if we're wanting to live in space for long periods of time, if we're wanting to go places out in deep space, we're going to need a platform to enable that.
NASA's experimental solution was a space station called Skylab. The plan was to launch it on a Saturn V moon rocket. The rocket would fall into the ocean, leaving Skylab in orbit around the Earth.
Skylab was built to be a workshop and solar observatory in space that would orbit the Earth almost 5,500 times a year.
The space station, complete with laboratory, kitchen, bedrooms, and bathrooms, would be launched unmanned, with the crew sent up 24 hours later. After 6 successful moon landings, NASA engineers had total confidence in the Saturn V rockets, but one crucial piece was untested: Skylab itself.
10, 9,
On May 14, 1973, the new station was launched.
5, 4, 3,
61 seconds into flight, at 1,100 kilometers an hour, Skylab punched through the sound barrier. As shockwaves shook the rocket, alarms sounded in mission control. Instruments on Skylab recorded a short, unexpected sideways force. As engineers raced to decode the data, the rocket hurtled on, and 9 minutes later, Skylab was in orbit. Data streaming to mission control indicated that a paper-thin protective shield, the size of a billboard, had been ripped from Skylab's side. As the astronauts headed home to rest, they didn't know if they'd fly the next day.
Before they even get home, they're hearing, hey, we've got a problem here. We have a space station in orbit, but it's crippled. And the question then becomes, just how bad is it?
If the data was right, there were 2 major problems. The lost panel doubled as a heat shield, and the damage was blocking a solar panel from opening, leaving the station dangerously low on power and at risk of overheating. The crew was scheduled to head to Skylab the following day, but the risks were deemed too great. The launch was postponed. It took engineers 10 days to address the problems.
You have people throughout the agency working to figure out what's happened here and what can we do to save it. And 10 days was an insanely short amount of time.
3 years earlier,
Okay, Houston, we've had a problem here.
NASA engineers and crew had brought the stricken Apollo 13 safely back to Earth. This time, although no astronauts were on board, the team still didn't want to lose their space station. As the crew trained for the unexpected repair mission, 2 seamstresses stitched together a sunshade. Meanwhile, engineers worked round the clock to come up with an emergency repair procedure. 11 days after the initial disaster, the 3-man crew launched on a mission to save Skylab. They had no idea what condition the space station would be in, and before docking, they flew a visual inspection. This revealed engineers had been right.
During launch, one of the thermal panels broke away, ripping off one of the spacecraft's 2 solar panels. This prevented the other one from opening and exposed Skylab to excessive heat.
NASA's official report concluded that a combination of engineering fails were to blame, from miscommunications to flawed components. The result? As Skylab went supersonic, shockwaves forced air behind the shield, and it was ripped from the rocket, damaging the solar panel as it went. With their visual inspection over, the astronauts prepared to dock with Skylab and try to repair the damage.
Although the astronauts were never meant to leave their spacecraft, they actually had to climb on the outside of Skylab to address the fault.
To make Skylab safe, astronauts had to both install the sunshade to cool it down and deploy the damaged solar array to increase power. Luck was on their side.
They very fortunately get out there and discover that there's actually a islet in a place that wasn't on the trainers. So thankfully they're able to run a tether through that to get purchase in order to use their clipper to cut the piece of metal that was holding the solar array in place. It deploys outward, and now for the first time they have something resembling the amount of electrical power that they were supposed to have.
2 weeks after launch, the power and temperature problems were resolved. Skylab had survived its first engineering catastrophe. The multi-billion-dollar program was back on track.
With the problem solved, the lab was now working, and in its first year of orbit, 3 different crews lived on board.
They're able to start doing the biomedical research, the Earth observations, the solar observations, the science that changed the way that we understand our planet.
3 crews and thousands of experiments later, the Skylab mission was declared a success. The station was left in gravity's grip and expected to fall to Earth in 10 years. But the engineering fail that made Skylab world news was yet to unfold. It was coming down much sooner than planned. The 77-ton station was expected to splash harmlessly down into the Indian Ocean in March 1983. Gravity pulls all satellites down to Earth. But in the mid-1970s, NASA engineers discovered the massive lump of metal was losing orbit faster than expected. With Skylab, it seems they had underestimated the power of the sun.
Once the last astronaut had closed the door behind him, the space station was supposed to orbit the Earth for another 10 years.
Skylab is there and it's in orbit, and it's essentially at that point been abandoned. It's flying overhead. People remember that it's there, but it's not being used. It's not active. What is active during this time is the sun, and in a way that nobody had anticipated.
We think of space as a vacuum, but Skylab's orbit was influenced by the Earth's atmosphere. In the mid-1970s, the sun was unusually hot. The result, the atmosphere heated up and expanded. This created drag on the space station, slowing it down and starting to pull it out of orbit.
NASA had underestimated the impact of solar activity, which had effectively halved its lifespan.
The result? Skylab would crash back to Earth 4 years earlier than expected.
Skylab was a very large chunk of metal, and people kind of understood that this was a thing that it had taken a giant rocket to put in space. This is a big thing that's up there, and now it's going to be coming down.
To buy them time, NASA looked at ways to keep Skylab in orbit. One audacious plan depended on a revolutionary spacecraft that was still in development, the Space Shuttle. The shuttle would carry an Apollo capsule up to Skylab and use the capsule's thrusters to boost Skylab into a higher, longer-lasting orbit.
So now we have a space station up there. The atmosphere is expanding faster than we anticipated. It's putting more drag on Skylab than we anticipated. And at the same time, down here on Earth, work on the space shuttle is taking longer than was originally anticipated.
Skylab's re-entry was getting closer, but the space shuttle's launch was delayed.
Eventually, it's realized these things aren't going to cross. The Skylab is going to come down before the space shuttle starts flying.
Skylab was going to crash back to Earth years earlier than expected, and where it would land was anyone's guess.
The idea of dropping it on somewhere like Idaho or Mississippi really got people thinking, however remote the possibility.
You had people who were selling and buying Skylab hard hats to protect them. You had a kind of a general sense of panic that is this thing going to land on me?
NASA engineers weren't just going to stand by. Professor Bonnie Dunbar is a former shuttle astronaut, but at the time was a navigation officer at Skylab Mission Control.
When NASA realized that the shuttle wasn't going to make it on time and that the Skylab was deorbiting faster than anticipated, said, well, we're going to be responsible about finding a way to deorbit it in a particular place.
The real aim was to ensure that the final entry was over the sea or an unpopulated area to avoid disaster.
The Southern Hemisphere has fewer people and more water, so Bonnie and the team planned for an Indian Ocean splashdown. However, the ailing space station wasn't designed for major course corrections. All they could do was adjust its angle relative to the atmosphere.
You have the ability to change the orientation of Skylab, but it's very limited, and that's all you have to work with. At this point, they're controlling the space station, they're controlling its re-entry simply by turning it and increasing the drag.
It's sort of like putting your hand outside the car window and letting the wind hit it. If it's flat-handed, it's going to drive your hand back, and there's a lot of drag there. It'll actually slow you down if it were big enough. But if you put it sideways, it's like a wing, and so there's not much drag.
Changing Skylab's angle would influence its speed and how quickly it would lose altitude. In theory, this gave NASA some control over where and when the station would come down. But would they be able to bring it down safely? Yes, America's first space station was falling to Earth 5 years earlier than anticipated. But NASA engineers were working 24/7 to control where it fell.
We had 3 mission control teams. We were each on for 8 hours, and we began to control the Skylab 24 hours a day for 9 months.
Finally, on July 11, 1979, Skylab started its final descent through the Earth's atmosphere. 16 kilometers up, hurtling faster than a speeding bullet, the space station started to disintegrate. Several large pieces survived re-entry and smashed into parts of Western Australia, but luckily, no one was hurt. However, Australian authorities did fine NASA $400 for littering.
It taught us from an engineering point of view as much from its re-entry as it was when it was up in orbit.
The Skylab mission was plagued by engineering problems, but NASA learned vital lessons which have taken space exploration to whole new frontiers.
Really, everything that we're doing in spaceflight today is because of what we did with Skylab.
Despite its problems, Skylab was still a hugely successful mission. Not only did it teach us a lot about what's out there, it taught us a great deal about engineering too.
Construction calamities can threaten even the most robust structures.
If all the computations are correct, these connections would have broken.
But as every engineer knows, if you build on soft foundations, you're just asking for trouble. Like this story in Italy, a catastrophe that created a ghost town.
We've all seen ancient ruins, but Krakow is an ancient city abandoned in modern times.
Perché aver abbandonato questo paese, il quale ci ha dato tanto, sento tristezza.
An engineering project to modernize this historic Italian town's waterworks helped trigger its downfall.
Krakow survived earthquakes, volcanic eruptions, even war. In the end, they were done in by some plumbing.
Krakow, in southern Italy, with its imposing hilltop defenses, held attackers at bay for more than 1,400 years. And despite appearances, it was full of life until the 1980s. One of Krakow's last residents, Sfera Domenico, recalls a good life in the town.
Ci si viveva bene, c'era vita, c'era tutto, avevamo tutto. Era un piccolo paese, ma avevamo tutto.
Sfera's hometown thrived for so long, not just through its defenses, but the surrounding landscape too, as architect Francesco Manfredi explains.
Non era solamente un caso che si andasse a costruire sulle cime, sulle montagne, sulle alture, magari dettato solo da aspetti legati alla difesa, in un'epoca in cui la difesa era quasi un elemento fondamentale per la costruzione dei centri abitati, ma anche la conoscenza geologica.
For centuries, Krakow sat safely on solid rock at the top of its mountain. 2 rivers at its base created fertile and rich farmland. According to archaeologist Nicola Massini, these were golden times indeed for the town.
Historically, it was known as Monte d'Oro, which means in English gold mountain. The period of greatest prosperity is the 16th century, when the village counted about 2,500 inhabitants. In this period, the village expanded from the tower towards the valley.
But as the city expanded, that created a problem for town planners. The town's founders built Krakow directly on the exposed rock at the top of the mountain. As the population grew, room on the rocky surface reached capacity, and buildings had nowhere else to go other than down the sides.
In fact, Krakow's growth and prosperity was ultimately part of the problem.
The trouble is, although the mountain on which Krakow stands looks solid, this whole region is geologically unstable.
Basilicata is the region of landslides. It was something that occurred all over the South Mediterranean region, but in Basilicata there was also the component of the geological fragility.
This geological fragility is caused by a combination of soft ground and sloping sides. The sides of the mountain are formed by a layer of clay 50 meters deep, sitting on solid bedrock. Clay is made up of small, densely packed particles. When it gets wet, it turns soft, and with the added water, it gets heavier.
The danger of building on clay is that if the clay gets too wet, it can slide along the bedrock underneath, taking whatever is on top of it for a ride.
The steep slopes and clay explain Krakow's long history of landslides. For hundreds of years, the slides were small and local, just part of life in Krakow. But in the mid-20th century, it seems engineers modernizing the town triggered events that helped to destroy it. Traditionally, residents drew their water from wells beneath the town. But in the mid-20th century, engineers installed modern water and sewage pipes. As geologist Giuseppe Loccarotolo explains, this had a massive impact on the area.
I pozzi sono stati abbandonati. Non è stata più tirata acqua dalla falda, perché l'acqua arrivava tramite le condotte idriche.
With no more groundwater being taken from the wells, the water table was saturated. So the clay was more prone to moving around, which cracked the plumbing and caused trouble for the town above.
In più, il movimento franoso ha fatto rompere le tubature dell'acqua e quindi da queste tubature è iniziata a fuoriuscire dell'acqua che ha peggiorato, ha accelerato il processo di la dinamica, il movimento sostanzialmente della frana.
Krakow survived hundreds of years of earthquakes, volcanic eruptions, the bubonic plague, even war. In the end, they were done in by some plumbing.
In 1959, heavy rains added to the already saturated clay, which over the next year or so triggered a series of slow but disastrous landslides. As local historian Savio Grippo reveals, the damage was catastrophic.
Behind me you can see the old town of Krakow. You can't see anything more, but you should imagine that all around us before we had houses. This was in fact the center of Krakow. They built in areas who were not exactly stable like the rock and activated this process of landsliding, who little by little brought down all the new area of the city.
The expanding city was built on clay instead of the solid rock in the city center, thus the instability.
Just the part on the rock remained standing in the exactly same position.
In an effort to stabilize the ground and stop the slides, engineers dug massive retaining walls 30 meters down into the clay of the hillside. But as geomorphologist Domenico Capolongo explains, it just made things a whole lot worse.
We see here the last made retaining wall done in the 1970. They went down 30 meters roughly, but the clay bedrock is 50 meters down.
The concrete pillars fell 20 meters short of solid bedrock. Instead of protecting the hillside, the wall added weight to the already unstable clay, making the problem worse.
They added a lot of weight more on the side of the hill, so accelerating the process of the landslide. After it, they could not solve the situation anymore, and little by little, all the center of Krakow slided down, damaging and destroying all the houses present here.
I danni si vedevano giorno per giorno, non è che si è visto tutto una volta, addirittura si vedevano perché le lesioni che apparivano nelle case si aprivano e si vedeva addirittura il sole all'esterno, la luce del sole.
The ongoing landslides, and then finally an earthquake in 1980, left the town uninhabitable, and residents left for good.
Siamo stati costretti ad andare via, ad abbandonare e andare via, dove abbiamo abbandonato anche le masserizie, molti hanno abbandonato anche le masserizie, perché non si sapeva dove portarle.
Krakow was once a thriving town with a university, a castle, a church. Now it's a ghost town.
Venire qua è una tristezza comunque, è una tristezza. E vedere tutto questo scempio è una tristezza, perché ci sono tanti ricordi.
To prevent this once thriving hilltop town from disappearing from history, the World Monument Fund has placed Krakow on the watch list to help pay for conservation efforts.
Quindi qui a Krakow non sappiamo che cosa si poteva fare, ma sappiamo cosa non si sarebbe dovuto fare.
Now Krakow's only guests are sheep, donkeys, and the occasional Hollywood movie star.
This particular place was also used for several movies, like The Passion by Mel Gibson, James Bond Quantum of Solace, or even an entire horror movie.
We've all seen ancient ruins, but Krakow is an ancient city abandoned in modern times.
Construction mix-ups can strike anywhere, from cities to the backwoods, from bridges to dams. But nothing grabs the public's attention more than when engineering goes wrong on a skyscraper. Like these stories. First up, an iconic piece of the Manhattan skyline. 601 Lexington was built in 1977, and its revolutionary design is as impressive today as it was then. The 59-story Goliath was built on stilts, but unconventionally, they are not at the corners. Engineers were confident that the structure was sound. However, a miscalculation uncovered by a student revealed that strong winds could topple the building.
The entire building would have fallen sideways.
There could be up to 200,000 fatalities.
The problem lay in the internal steel structure.
The contractor modified welded connections to bolted connections.
A weld will take much greater forces than a bolt.
All 200 bolted joints had to be welded over to improve the building's strength. Fortunately, the fix was completed in time and tragedy was averted. From a hidden design flaw to a sinking subterranean nightmare. San Francisco, California. Completed in 2008, the Millennium Tower is 58 stories of prime real estate. But soon after these multi-million-dollar apartments opened, residents noticed something wasn't quite right.
One of San Francisco's tallest residential buildings was sinking.
Engineers had built a foundation consisting of a huge concrete slab, supported by friction piles sunk deep into the ground. However, during construction, it seems some steel elements were switched to concrete, making the tower a lot heavier. Although the developers don't agree, some believe the existing foundations were too weak. Either way, the building is not only sinking, but leaning too.
He rolled this marble 10 feet toward me. The marble slowed to a stop, turned around, and rolled back.
One potential fix involves the installation of more piles, this time all the way down to the bedrock. But the cost is estimated at over $100 million. For now, the residents of this West Coast icon will have to keep their balance. Next to London, England, and a tower that was struck with a very surprising problem. The Leadenhall building, nicknamed the cheese grater because of its unique shape, stands at 52 stories. Opened in 2014, this skyscraper's distinctive design set it apart from its neighbors. Rather than opt for a central concrete core to support the structure, engineers surrounded it with an external megaframe, all held together with 3,000 massive bolts. Only months after opening, disaster struck when 2 of the giant megabolts fell from the building.
Can you imagine a bolt the size of my arm falling from the 19th floor of a skyscraper?
Soon after, a 3rd bolt fell. Fortunately, no one was injured. The bolts had suffered a chemical process that caused them to crack. Engineers knew that the only sure fix was to replace every single bolt. The repair cost millions, but at least it's now safe to walk beneath. Staying in London, our final skyscraper isn't sinking or losing a piece or two, but it was having a major impact on people below in a totally unexpected way.
Believe it or not, until fairly recently, buildings in London's financial district were relatively short, but now they're playing catch-up.
The people of London love giving their buildings nicknames. We have the gherkin, the cheese grater, and the walkie-talkie.
Standing 38 stories high, when built, 20 Fenchurch Street was one of London's tallest buildings.
The Walkie-talkie is a true mega-bucks skyscraper. When it was sold, it was the most expensive UK building ever.
But since opening in 2014, this design marvel has been fraught with issues. Thomas Lane, editor of a building trade magazine, has written about the walkie-talkie.
This building has suffered from quite a few environmental problems, famously the melting of cars.
The owner of a luxury Jaguar was shocked to find that the building had caused damage worth around £1,000 to his parked car.
The shape of the building, because it curves in at the curves at the front, actually has the effect of focusing the light like a lens.
For 2 hours every day, its unique shape was focusing the sun's rays into one concentrated spot, creating temperatures of over 90 degrees centigrade at street level.
The problem cost millions of pounds to fix. No wonder the building got the nickname the Walkie-Scorchy.
Engineers solved this problem in May 2014 with slats on the front of the building. However, this wasn't the end of the walkie-talkie's issues. The tower was wreaking havoc not just with light, but with air. Volker Butgerit is an aerodynamics expert from London's Imperial College.
If you put up a tall building in London, then this building is generally of a much larger scale than the surrounding buildings. And what that means is the potential for the building to impact on ground level wind environment is much stronger than it would be otherwise.
On windy days, pedestrians on the ground near the building were finding it tricky to stay upright. This drafty problem was again down to the building's curved shape. Justin Parkinson works close by.
But when it did open, there was another criticism about the wind that it created, the so-called downdraft. It was causing women's skirts to rise, it knocked over street signs, and people were just wondering why this particular part of London was so much windier than neighbouring areas.
This downdraft effect occurs when southwest winds hit the front of the building. They're forced down towards the ground. The downdraft is made worse by another factor of this old city. Its narrow, intricate network of streets focus the wind.
This part of London really wasn't designed for skyscrapers. Its plans were drawn up in the 1600s and it was made up of lots of tiny, narrow roads.
The height, the position, and the concave shape of the building were the perfect storm of conditions to create the perfect storm on the streets below.
The combination of strong winds and narrow streets causes a phenomenon known as the Venturi effect. Here, This occurs when air is forced through the narrow streets, resulting in a drop in pressure, but an increase in speed. The ancient roads around the Walkie-talkie have become wind tunnels.
So you can have a tall building that might be causing a downdraft, and that might have a certain strength, but if you then have an Venturi effect, that can really cause quite high winds.
A series of clever solutions were put in place to tackle the tower's wind issues.
Once it was discovered that the downdraft was causing this effect below, the building's management took steps to alleviate it. They put a canopy at the bottom of the building to stop the wind hitting directly at street level.
What that does is it doesn't prevent the downdrafts from occurring, but it prevents them from reaching ground level. So the downdraft occurs, it disperses at high level, and so at pedestrian level, the public realm doesn't really see it anymore. So what you then need to do is really have local wind mitigation schemes in areas of interest, so soft landscaping, hedges, that sort of thing. Sometimes when you walk around tall buildings, you can see those things in action.
It might sound simple, but something as easy as planting trees and bushes can lessen the impact of the wind.
As well as the wind canopy and soft landscaping, to diffuse the wind, engineers also added a steel mesh to the side of the building.
Well, I think the trees and the canopy were probably fairly cheap, but this row of grates across the whole side of one building that's got more than 30 floors must have cost an absolute fortune. Just imagine being the person who had to climb up there and do that job, and the designer who had to work out how to install them.
The world will continue to look to London as a leader in architecture and design. But when engineers push the boundaries, there will always be problems that have to be solved.
I'm sure that in future architects and builders will take greater pains before the building's actually constructed to work out the effect of the wind, so they don't end up spending millions and millions of pounds on alleviating it.
Next, to France, and an engineering mix-up of epic proportions.
This led to one very close shave.
This baffling engineering blunder came at a massive cost.
A 15 billion euro project? This mistake is almost impossible to comprehend.
Since France's first railroad began operation 2 centuries ago, the system has grown rapidly to be the second largest in Europe, with almost 30,000 kilometers of track. It's operated by France's national rail company, SNCF, a member of the International Union of Railways, the UIC.
The International Union of Rail was formed in 1922, and it helped to standardize railways and trains throughout the world. It now has 194 member countries across 5 continents.
Millions of passengers pass through France's stations daily, but due to its popularity, the railroad now faces a problem: the need to carry more passengers. Building more lines wasn't an option due to land limitations and construction costs, and the schedule was too packed to run more trains on existing lines.
So one solution was just to make bigger, wider trains.
In 2009, SNCF ordered 2,000 new trains to be built at a cost of 15 billion euros. The new models would be wider, not only carrying more passengers, but allowing step-free access from platforms. Journalist Mark Frezos knows the story.
La conception de ces trains date des années 2009. Les régions voulaient des trains qui aient de grandes capacités pour transporter le plus de passagers possible sur des zones interurbaines, entre les grandes villes et la banlieue, entre les grandes villes et la campagne, et voulu un train donc très large, où on puisse mettre 5 personnes de front.
But when the new trains came into operation, a massive engineering mix-up came to light. The carriages would not fit into certain French stations. Transport writer David Haydock has an in-depth knowledge of railroads.
There are 2 very important things in order to build the trains the right size. The first one is the track gauge, which is the distance between the rails. The second thing which is important is the loading gauge.
The loading gauge defines the maximum height and width for railroad vehicles and their loads. It ensures safe passage under bridges and through tunnels. Loading gauges can vary across any network, even if the track gauge remains the same. In this case, the loading gauge of the new trains was too large for over 1,000 French stations.
The trains didn't fit. It was like a DIY nightmare on a national scale.
This oversight was down to a mix-up in the figures surrounding standardization.
The problems came when these trains started to run on the network, and they were found that they would be too close to the platform.
Local activist Eric Sowry is frustrated with the situation.
The engineers of SNCF, they finally understood that there was a problem when they made the first trial for real, which is incredible. When you face the reality with the first trials, oh my gosh.
The carriages of the new trains were 20 centimeters wider, making them too large for many station platforms. The platform overhangs would make it impossible for them to even enter these stations at all. When SNCF ordered the new trains, they consulted the organization responsible for maintaining the French network, the Réseau Fer de France, or RFF.
There are two massive organizations employing hundreds of thousands of people, and sometimes when you get large institutions like this, information can get lost or muddled.
The RFF said that all stations were built to the international standard. But it turned out that was only the case for platforms that were less than 30 years old.
Il y a des choses qu'il faut savoir, c'est que au fil des années, les gares évoluent, les quais sont refaits, les quais sont reconstruits ou sont élargis. Et que ça, c'est au fil de l'évolution. Et personne ne sait vraiment aujourd'hui quelle est la dimension de ce quai, est-ce qu'il est conforme à sa dimension d'origine il y a 50, 60 ans.
So here you've got these new trains fitting international standards going into these old stations that each had their own unique specifications of the time.
Realizing what had happened, SNCF had to work out how to solve the problem.
In a situation like this, there are two possibilities. One of them is that you actually move the track. Now, the problem with moving the track is that you would have to bring along an extremely expensive and very long train, which removes the ballast, which is the stones underneath the rails, pick the track up and move it slightly, just a few centimetres one way or the other, put it back down again and then put more ballast back. And that would cost a small fortune. So you actually deal with the station platform and plane a little bit off the edge, a few centimetres off the edge. It doesn't cost very much at all.
The engineering fix was to modify every station to accommodate the wider trains.
It's maddening to think that they had to get in there with angle grinders and shave down the entire length of each platform.
On average, 2 centimeters of platform had to be removed from around 1,000 stations across the country.
The official figure for the number of platforms to be modified is 1,300 out of 8,700 in France. But the number is bound to go up as more modern trains are ordered by the regions.
The fix cost French taxpayers 80 million euros.
C'est vrai que je me mets à la place de ceux qui, eux, tous les jours payent le train, payent un abonnement, payent des impôts pour ça, et derrière, c'est vrai que c'est pas clean de pas vérifier ces informations avant de faire quelque chose d'aussi conséquent, d'aussi important.
I thought that it was a really, really big mistake. I mean, well, it's not fit. I mean, it's millions of euros. That there was a big, big disappointment for everyone.
Although trains are still running in France, this is one engineering catastrophe they'd rather forget.
The 15 billion euro project
was almost totally derailed.
Construction calamities come in all shapes and sizes, from out of this world
Okay, Houston, we've had a problem here.
back down to earth. The towering to the ridiculous.
And Mario Bagno want to build this place following Las Vegas or Disneyland.
So long as we keep building, there will always be more engineering mistakes to fix. Coming up, as we search the world for engineering catastrophes, a construction calamity swamps downtown Chicago.
Water blew through this hatch opening 8 or 9 feet above our heads.
In Pennsylvania, a slow-burning engineering emergency.
The entire town is gone.
An English town that's falling into the sea.
We've lost 40 meters off the back of my property.
And an international railway that hit the buffers.
We are inside the station. In that side was the hotel, but now there are nothing.
With big builds, even the smallest mistake can be a huge disaster. From miscalculations to misunderstandings, these are the massive engineering mistakes that only an expert can hope to fix. When construction goes wrong, there's a chance engineers might get lucky. But sometimes, tiny mistakes escalate into massive disasters. For this first catastrophe, we head to Chicago, a city in turmoil.
The city was officially declared a disaster zone.
This engineering error opened the floodgates on calamity.
A small crack quickly became a catastrophe.
Engineers raced against time to stem the flow of disaster. Chicago, Illinois, with more than 2.7 million people calling the Windy City home, it's the third largest in the U.S.
Chicago is a really important, big American city. It's built right on Lake Michigan and built around the Chicago River.
The Chicago River is central to the city's infrastructure. But on Monday, April 13th, 1992, its contents started showing up in some very unexpected parts of downtown, all thanks to an engineering error. Myron Maurer, COO of Merchandise Mart, woke up to the news that the basement of his iconic building was flooding.
Well, the first call came to my home about 6 o'clock saying that the boiler room had reported there was a foot of water.
Myron rushed downtown, and when he reached the boiler room an hour later, a small leak had become a gushing torrent.
Water blew through this hatch opening and actually with such force that it went up and hit this ductwork here, which is about 8 or 9 feet above our heads.
But Myron's flooding wasn't the only case. Emergency calls were pouring in from across downtown. City officials were completely baffled. Journalist Neil Steinberg was downtown that morning.
And the first thing I saw was a phalanx of 6 police horses, 1, then 2, then 3, cantering up Wabash Avenue. So it was a very distinctive moment for me. And then I got to City Hall, and there was all this equipment parked here on Randolph Street, pumps and lights and command centers.
As residents woke, few knew that an emergency was unfolding downtown, and the source of the water remained a mystery.
So when water starts to appear in the basements of major buildings, the first question, of course, is where is it coming from?
At 9 a.m., as downtown prepared to open for business, onlookers spotted a clue: a small but unmistakable whirlpool in the Chicago River under the Kinzua Bridge.
The whirlpool was a giveaway because just like when you drain water out of a bathtub, if it's got one single area that the water is exiting through, you get this whirlpool building above it, and that's what was happening here.
The whirlpool was a sure sign that there was a hole in the riverbed, but that raised a question. How was the water getting from here to the basements of 30 buildings? Local historian Bruce Moffat had a good idea what was going on.
When I turned on the radio, and there were reports of all these older buildings in the loop drawing water, and no one seemed to know where it was coming from. And I thought, well, I know where. It has to be the freight tunnels. And I knew that many of these buildings they listed were all connected to the tunnel still.
In the 19th century, engineers constructed a network of service tunnels to carry cables beneath the downtown area. The 60 miles of tunnel were abandoned in the 1950s and largely forgotten, but now it seemed the Chicago River was draining into the labyrinth. Just hours after the first signs of a flood, multiple iconic buildings, including the Mercantile Exchange and Chicago Board of Trade, reported up to 12 meters of water in their basement.
Eventually, it filled through here and it came into this room. This room is about 30 feet tall, and it came just about 5 feet short of the concrete deck that you see up here with my flashlight.
Around 10 a.m., an emergency evacuation was ordered of the entire Loop District. The race was now on to stop the flood in its tracks. With the unlimited waters of Lake Michigan and the Chicago River, the flood wouldn't just run dry. Engineers needed to know what had caused the leak. The whirlpool in the river near the Kinzua Bridge was the biggest clue. The bridge is surrounded by a series of wooden piles.
The Kinzua Bridge has a small structure just to the side of it, and to protect it from river traffic, it's got some wooden piles that are secured in the riverbed around it.
Just 6 months before the flood, these simple wooden barriers had been replaced. Contractors positioned 37 new piles just a short distance away from their original location. They hadn't realized that the abandoned tunnels ran under the river here, almost directly beneath the new position for the wooden piles. As the piles were hammered into the riverbed, the dense clay was pushed aside, triggering a series of unfortunate events.
The wooden piles didn't actually crack the tunnels directly, but they were in such close proximity to the tunnel walls that the clay pushed up against them, and that's what cracked the tunnel.
Pressure from the displaced clay, combined with the weight of water pushing down from above, caused the crack to grow until finally the tunnel breached.
So it started out as this small crack in this tunnel, once the water started going through, resulted in a metropolis in turmoil.
With the Chicago River draining into the tunnels, city officials had a huge challenge on their hands: how to plug a leak in a riverbed.
Plugging a hole like this is not as simple as just putting your finger in it. A hole that can create a whirlpool in a river is going to need something a bit more substantial.
Engineers were fighting a battle on two fronts. First, blocking the leak from above.
And they brought out a barge with mattresses, with rock and other debris that they would toss in.
Using mattresses might seem strange, but time was critical. So engineers improvised with any materials that might slow the flow. Plugging the hole from above was only half the job. The team also had to seal the tunnel from within.
But they had these, they called them pigs. They were large, inflatable sort of bladders that they were bringing in. The Army Corps was bringing in.
Pig balloons are inflatable spheres that are used to stop the flow of materials through a pipeline. By inflating pig balloons inside the flooded tunnel, engineers successfully sealed off the damaged section.
They were pouring in aquatic concrete to sort of plug the thing, because they couldn't drain it until they plugged it.
The concrete permanently sealed the tunnel, but the flooding problem wasn't over yet.
Once they'd stemmed the flow of water, now they're still stuck with tunnels full of water. What do they do with it all? Fortunately, there's a sewer system that runs even lower, and they were able to tap into that, making tunnels between the two, and just drain the water out into the sewage system.
Now, all that remained was to remove millions of gallons of water from skyscraper basements across downtown.
So you still had these huge buildings that had basements full of water and fish. And the only thing to do at that point was to get pumping.
Pumping the city dry took days, and the repairs cost around $2 billion. To ensure that the underground tunnels could never again spread floodwaters so extensively, J.J. Madia and his team have installed watertight safety measures.
These are what we call river crossing bulkhead doors. Once we go through these doors, we are actually underneath the river. So if there was another breach due to the river water coming in, this would isolate the rest of the tunnel system from receiving the water. These doors, before you can open up a door, you need to open up the valve to make sure there's no water on the opposite side.
The flood was epic, but the Windy City hasn't suffered anything quite like it to this day.
It turned out to be a very odd kind of disaster. It was a flood where almost no one got wet, where almost no one saw water. They caused incredible damage, almost $2 billion worth.
It just goes to show in engineering that if you ignore small cracks, they can turn into big problems.
Some engineering calamities can be caused by a single mistake, oversight, or plain bad luck. But when Mother Nature unleashes her full fury, it can trigger a chain of events that lead to disaster. For this calamity, we head to the east coast of England, and a village that's teetering on the edge. When it was developed in the 1930s, builders couldn't predict the storm that was brewing.
Where you can see through the door there, that was the kitchen. It went over the edge. We were actually stood here, and we had this great big crack.
Now, residents are desperate for an engineering solution to save their homes.
Houses falling on the beach, it's not something you see every day.
Hemsby, England. This seaside resort is famed for its picturesque beaches and cliffs overlooking the sea.
The village dates back to Viking times, when the raiders braved the brutal North Sea in search of glory. They decided that they liked it and stayed.
Over the centuries, Hemsby grew into a small town, with houses stretching more than a mile back from the coast. Most homes were built to last, with solid concrete foundations. But in the 1930s, people wanting to enjoy sea views built wooden vacation homes or chalets on the fragile cliffs. The houses lacked foundations and weren't built to withstand extreme weather. But in March 2018, the UK was hit by some of the most brutal storms on record.
It may have been spring in the UK, but a powerful cold storm blew in from Siberia. So bad it was nicknamed the Beast from the East, and it lashed the country.
In Hemsby, waves hammered the cliffs, which started to collapse. In just 2 days, the cliffs receded by over 5 meters. The storms of the beast lasted a month. By the end, 11 meters had disappeared. Army veteran Lance Martin had only just moved into his clifftop home when the beast arrived.
We were actually stood here, and we heard this great big crack and a rendering sound, and we looked around and it had gone. It was really scary, and you know, I grabbed hold of one of the guys that was in here and I kind of threw him towards the front door. That was my first reaction, and then I thought, why have I thrown him towards the door? Why aren't I running? This was my living room, so I had a sofa here. I had a chair there. That was the bedroom. with a double bedding and a wardrobe. Where you can see through the door there, that was the kitchen, the bathroom and a wet room, and that room was 12 foot by 18 foot. Sadly, it went over the edge, and it just went with a big crash and a bang.
But the beast wasn't done yet. Lance's home took a further beating.
Subsequently, the storm that we had knocked another 20 metres off, so we've lost 40 metres off the back of my properties.
The storms left 13 cliff-top homes uninhabitable. Although the damage caused by the beast from the east was extreme, it wasn't the first time Hemsby's cliffs had been attacked by Mother Nature. 5 years earlier, in 2013, this same stretch of coastline was pounded by a phenomenon called a storm surge, as geologist Julian Andrews recalls.
In December 2013, there was quite a big storm surge, the biggest one around here for some time. And Hemsby here, there's evidence that the dunes, certainly in places, moved back by about 10 meters or so.
For a storm surge to form, you need 3 elements: a low-pressure weather system, strong winds, and a high tide.
Strong winds push water towards the coast, while low pressure overhead sucks sea levels higher. Add in a high spring tide, and the waves crash harder and further inland. The 2013 storm surge was the largest the UK had seen for 60 years. It drastically weakened the cliffs. When the beast from the east hit 5 years later, the wooden vacation homes were doomed. Back in the 1930s, builders couldn't have foreseen our current extremes of weather. But even so, it seems an oversight to build houses with no foundations on such soft geology.
Erosion has been ongoing in this coast really since the end of the last glaciation, about 7,000 years ago, and the coast has been eroding back at quite a steady rate, roughly about a metre a year since that time.
The reason Hemsby's cliffs are eroding so much faster than most places is because these cliffs were formed by huge glaciers grinding down the seabed into sand, and it's this sand that now forms the entire coastline surrounding Hemsby.
This pile of sand is far from rock solid when it comes to the erosive power of the sea. Not only that, but there's another issue which compounds the problem: the direction that the cliffs face.
So these are northeasterly facing cliffs and beaches. In the winter, the big storms are coming in from the northeast, blown by northeasterly winds. So these cliffs really take the brunt of that wave energy.
Taking the soft ground, the exposed location, and the fact that houses have fallen here before, isn't the mistake to build here at all?
With Lance's home on the brink of total collapse, the local authorities issued an ultimatum: demolish it or attempt to move it with the help of local engineers.
I've been given a deadline of 1 o'clock today to try and move it forward sufficiently that the council are happy with where I've moved it to and it's no longer a danger. It's now 10:25, so I've got basically 2.5, 3 hours to achieve this.
Without a foundation holding you to the ground, you can literally pick it up and drag it like a sled somewhere else.
So what he's doing now is levelling out the ground for us so that we can start the drag forward of the building. So we need that to be as level as possible so that when we do drag it forward, we don't hit any ruts or troughs. So he's doing the best he can to get us as level as possible.
The house was not built with this move in mind, so Lance and the team have no guarantee of success. First step, prepare a flat area far from the cliff edge, where they hope to resettle his home.
We need the front door to come to about here to keep the council happy, and then I'll have a good-sized garden at the back.
Next, the engineers attach cables around the base of the building to haul it back from the edge.
Right, here we go, boys.
The structural integrity of Lance's house will be pushed to the limit.
Yeah, cracking.
Get out the way.
If it holds together, Lance might just save his home. But For some, the outcome is more harsh. Kane Fincham is a local demolition expert. He's well aware of how dramatically the cliffs have changed here.
These were built in the 1930s, and back then there was a good 100 metre, 200 metres out, of sand dune. 15 years ago when I came here as a child, there were 3 tiers to it, and now there's nothing.
This chalet is too weak to be moved, so demolition is the only option.
First visit a month ago, that porch had about 2 or 3 metres ahead, a bit of a garden, and now there's nothing.
With machines crunching from above and below, in just 30 minutes, the home is reduced to a pile of wood. With so many homes falling over the edge, residents are hoping for a solution. As the saying goes, you can't hold back the tide. But with modern engineering, we can try.
One of the options that people have considered recently is what we call managed realignment. So you can make decisions to essentially let nature take its course, but guide it a little bit.
In Hemsby, work has begun on a chain of honeycomb-shaped concrete blocks, a so-called beehive barrier. The chain is designed to allow tidal waters to pass through, while absorbing the impact of waves before they reach the cliffs.
Concrete barriers are ugly and expensive, but if the alternative is that people are going to lose their homes every time there's a big storm, then it's probably a price worth paying.
These honeycomb defenses might well save the coastline in the future. But for Lance, the survival of his home is in the hands of engineers.
If we can get another meter, that would be fantastic. Then I know that I'm in the safe zone. Fantastic.
Mission accomplished. Lance's home is finally safe. The question is, for how long?
Elated, elated, I really am.
When it comes to this ongoing battle with Mother Nature, engineers will continue to innovate while repairing the oversights of the past. It's easy to see an engineering mistake when it collapses before your eyes. But when a disaster is unfolding out of sight, you might not spot it until it's too late. For this catastrophe, we head to Pennsylvania, and a mining town turned wasteland.
It's incredible to think that this whole thriving community is now gone.
This mass exodus was due to an engineering error that's an ongoing problem to this day.
Nearly the entire town is gone. There were 400 or 500 buildings here, and now they're down to maybe 4 or 5.
Centralia, Pennsylvania. In 1854, this area started to grow rapidly when a railroad was built to capitalize on its mineral-rich terrain.
Pennsylvania is well known for the Appalachian Mountain Range and also the coal region, which historically was the coal mining capital of the US.
Thanks to the coal mines, Centralia and its community thrived for almost a century. Former resident Tom Dempsey recalls a good life here.
It was nice. It was a nice town to grow up in. And we had a great time here. You know, when we were kids, it was a safe place. There was approximately 2,500 people living in the town when I was a kid. And we used to play around the coal mines. We used to play around all the places that you shouldn't play is where we played.
The 2,500 residents are now gone, and Centralia is a ghost town. But these empty streets once bustled with life, thanks to the particular type of coal lying underground. Coal forms when rotting organic matter is crushed underground for millions of years. Where the ground buckled into hills or mountains, the coal was heated and compressed further, The result? Undulating seams of the hardest, cleanest burning coal on Earth, anthracite. It's also the most valuable, and almost all U.S. anthracite is found in northeast Pennsylvania.
Anthracite coal. This has less impurities and less moisture, which means it burns really easily and at the highest temperature.
This high-grade coal gave life to Centralia, but ultimately sparked its dramatic downfall. Local journalist David DeCock knows the area well and recalls how it looked in its heyday.
We're in the village of Marion Heights, Pennsylvania, which is about 8 miles from Centralia. Marion Heights looks very much like Centralia did. The houses are very much the same. They come right up to the street. There's no front yards. They were both coal mining towns. There's certainly a lot of old coal mines in and around Marion Heights.
But compared with the streets of Marion Heights, Centralia now looks very different.
This picture shows the main street through Centralia. In the fall of 1983, nearly the entire town is gone, wiped off the face of the earth.
What could wipe an entire town off the map? It all began back in May 1962, when local officials unwittingly sparked an underground fire. A fire that would make the town uninhabitable. Mining towns across America regularly dealt with their trash by using abandoned coal pits as landfills. When full, these would be set on fire, and some believe this could be what triggered Centralia's downfall.
They would let it burn for a while, then they would wash it down with water from a tanker truck, go away, everything was fine. But in 1962, this was the first year that the dump was in this location. And so they did what they did, they let it burn, thought it was out, but it was smoldering down in the lower depths of the garbage. And the fire spread from the garbage through an opening in the pit that went into this labyrinth of abandoned coal mines beneath the town. And that's how the mine fire got started.
No one knows for sure how the blaze reached the coal, but it's possible that the pit hadn't been properly lined before the fire. As the trash burned, the townsfolk didn't realize it had ignited the coal beneath it. The anthracite coal burned readily, and the fire smoldered underground. With more coal seams beside it, the blaze soon spread.
Howdy.
Geologist Dr. Cynthia Venn is heading into a nearby mine to reveal just how densely packed the seams are in this region.
What we have here is a seam of coal, the orchard vein, and you can see it's sandwiched between like a sandy shale kind of rock above and the same below. Because these veins are separated by this other rock, if you have a lot of cracks in the rock, or if you have a very thin layer of rock between the veins, then one burning vein, which gets very, very hot, can kind of heat through to the other, and so you can get this sequential sort of burning of veins if they're close enough together.
The large network of abandoned coal tunnels supplied the fire with oxygen, fueling the blaze, and the high-density coal lying beneath the town made matters worse.
Once the coal is lit, it's very hard to put out, especially as it's anthracite coal.
In 1969, engineers attempted to prevent the fire from spreading. The plan was to dig a trench through the seam in front of the burning coal, like a fire break in a forest. But the blazing coal smoldered past before they could dig deep enough. They hoped that the fire would eventually burn out, but a decade later, the coal was still smoking.
The fire was releasing noxious gases which were blowing towards the town. The answer was to drill down to the burning coal and allow these gases to escape away from the houses.
This shows the vent pipes that were installed around us here right around 1980 or 1981. And the purpose of them was to pull the fire and the deadly gases away from the town of Centralia.
99.
As the fire burns, it's oxidizing the sulfur in the pyrite, and so you're getting sulfur dioxide from that. You're also getting probably carbon monoxide because it's not burning completely. There's not enough oxygen down there.
It's a real witch's brew coming out of that pipe, just of nasty stuff. Yeah.
Nasty stuff, yeah.
Just a few years after the vent pipes were installed, some argued that they were making things worse by feeding the fire with oxygen. So the decision was made to seal them. But the coal seam continued to burn, and pressure from noxious gases built up beneath the town. The results were disastrous. Roads began to swell and crack open, releasing toxic fumes. Remarkably, Centralia's residents continued with their daily lives, despite the disaster burning beneath them. Engineers tried again to stop the fire in its tracks.
Let's say this coal seam was on fire, you just dig down past that coal seam all the way around and then put some kind of a non-combustible barrier on there. And if you do that, then the coal will burn to the barrier and then quit. Then they sort of tried that early on, but they didn't finish the barrier, and when they did a couple of times, and the one barrier, they went down and they were behind the coal. They had misjudged where the fire was.
By the late 70s, having failed to prevent the fire from spreading closer to the town, residents were warned that Centralia was unsafe. But most people stayed put until a dramatic event convinced them of a very real danger.
When coal seams burn underground, they undermine the integrity of the surface. Frighteningly, this can result in sinkholes opening up, revealing the burning coal below.
That's exactly what happened on Valentine's Day 1981, when a young Todd Domboski was exploring his grandmother's backyard.
Right now we're standing in front of the home of Todd Domboski, the young 12-year-old boy that fell into the sinkhole. Now that sinkhole was in the backyard, which it's hard to get to with all these brambles and stuff here, but it was about 30 feet back on the right. He saw a puff of steam coming out at the base of the tree, so he went over to see why. And when he got there, the ground just went out right from under him and opened up. And steam shot about 50 feet in the air.
Miraculously, the boy was hauled out by his cousin and survived.
Eventually, it attracted all the major news media in the country and the world, really. Usually a mine fire didn't cause too much attention before. But that shone the spotlight on it. And then the end result was what you see now. Everybody left.
By chance, state politicians were visiting that day and witnessed the aftermath. They insisted that the state intervene. But with the underground fire now so huge, extinguishing it was no longer a viable option.
It was Centralia, it was just finally a matter of money. What's going to cost more to dig this huge barrier and surround the coal, or just buy everybody out? And so they decided to buy everybody out as a cheaper alternative. I think it was $42 million as opposed to $200 million to do that remediation operation.
The government offered residents a substantial cash sum to leave. But despite the cracking highways, noxious gases, and sudden sinkhole, many people in Centralia were still reluctant to abandon their homes.
There was an engineering study done by an engineering firm from Pittsburgh, PA, and they published a book that was passed out to every family in the town, had all these different scenarios that could happen if nothing was done with the fire. And that scared the arses off the people, I guess you could say. And a lot of them then changed their mind and left.
This engineering report quashed any rumors or opinions that could gain authority in these situations, and it revealed the hard truth of what needed to be done.
This brought the reality home to residents, and most left town. By 1991, many of Centralia's buildings were demolished, and the main highway closed. A decade later, just 21 residents remain, refusing to leave their homes. Today, more than 50 years since it began, Centralia's coal seam fire burns on. With no end in sight, experts predict that it could smolder for another 250 years. Some engineering catastrophes are the result of the smallest mistake, with consequences that no one could have foreseen. Others, however, are so obvious that you can't help wondering how on earth they happened. Like this story in northern Spain, with a train station that hit the buffers.
How could such close neighbors get it so wrong?
As engineers from Spain and France discovered, every decision, however small, can have disastrous consequences.
It sounds like something was lost in translation with this blunder.
Canfranc, a small mountain village in the north of Spain near the French border, and home to one of Europe's largest railroad stations.
Canfranc is in an extremely remote location. It's hundreds of miles away from the nearest major city.
It was a village with only 500 people, so you'd think it would be the last place that they would build such a major station.
And yet, in 1928, trains started rolling in and out of this mammoth construction. Laura Roldan is a local tour guide.
The station is 241 meters longer. There is 150 doors and 365 windows. It's a big building.
This was an astonishing feat of engineering. They built a massive station as long as 2 football pitches in the mountains, 4,000 feet above sea level.
So, why go to all this trouble?
The huge Pyrenees Mountains cut Spain off from France, but both countries wanted to open up a trade route. And what better solution to transport goods than rail?
Raymond Campo, a local journalist and historian, explains the significance of this rail line.
Canfranc station was built because here is in the middle of the Pyrenees and is the shorter way between Madrid and Paris.
France and Spain were already connected by 2 rail lines, but these went around the Pyrenees. To slash journey times between the nation's capitals, the ambitious new line would cut directly through the mountains. The project involved the building of dozens of new bridges and drilling tunnels through the mountains. Just building the track was an epic engineering feat, and it demanded an equally epic interchange. The massive Canfranc station took Spanish and French teams 5 years to construct. The opening ceremony in 1928 was a grand affair, attended by both King Alfonso of Spain and President Gaston of France. Visitors gazed in awe at the spectacular new station.
The Canfranc station building was the second biggest in Europe after Leipzig in Germany.
There was customs, there was passenger controls. On the second and third floor, there was 40 apartments for staff.
Soon after it opened, the station buzzed with life. The giant transport link was nicknamed the Titanic of the Mountains.
Here, every day, arrive around 7 or 8 trains from France.
There are many passengers, there are people who work in the train, there are many bars and the hotel. All of them is movement until 6 in the morning and to night. The glory days here was many people taking the train from here.
But by the 1930s, just a few years after the first trains arrived, the glory days were over. Today, the station stands derelict.
We are inside the station. In this moment, the station is empty. In that side was the hotel, but now there are nothing.
Despite its initial success, Canfranc was doomed from the outset. What could have caused this grand station to rapidly fall from grace? The problem was a simple and yet fundamental engineering issue. French and Spanish trains couldn't run on each other's tracks.
Now we are in the Spanish side, and the tracks are different than the French tracks. Here, the side is about 5 feet 5. Well, this is the side of the French railway track, and it's 4 feet 8.5.
The Spanish tracks are almost 25 centimeters wider than the French, making it impossible for trains to cross from one to the other.
Today, nations work together to standardize all sorts of things: trains, planes, automobiles. But 100 years ago, this wasn't the case.
Without a standardized system, every nation and even region chose the best gauge to suit their needs.
Narrower gauge is cheaper and easier to build, both track and trains. But a wider gauge, although more expensive, can carry more weight. And a heavier or bigger locomotive equals more pulling power, more speed.
So the Spanish opted for a wider gauge, but legend has it that pulling power wasn't the only reason behind the different track width.
Spain have different railway line to Europe because they are afraid of invasion. Because in the 19th century, the French invaded Spain.
In February 1808, Napoleon turned on his ally King Carlos IV and invaded Spain. The French stayed for 5 years, leaving a bad taste in the mouths of the Spanish. Whether driven by invasion paranoia or simple practicality, Spain's track gauge decision created a huge problem at Canfranc. An issue that was too much for anyone to bear, including passengers.
Passengers arrive in this side, and they have to move another train in the other side of the station. This is the train Spanish and the train French.
I was a French passenger. I just go down the train, and I have to go to the Spanish side, so I have to pass into the lobby, and then I have to buy the ticket here. That's the ticket office. And then I have to pass to the Spanish side because there is waiting the Spanish train. So and we are in Spain.
Switching trains is a pain. We'd all prefer a direct journey over one with a change. But it wasn't just passengers. Every single product that crossed into France needed to change trains.
If the time and effort taken to transfer between trains wasn't enough to finish off Canfranc, there was one more fundamental issue between the two railroads: power.
We can see here that pylons, which the French train have the electricity. And in Spain, we had a steam train until 1970.
The Spanish and French railways couldn't have been more incompatible. Different gauge and different power.
So many issues made Canfranc a very unpopular transport link, and it rapidly fell out of favor with both traders and travelers. The line continued to operate with as few as 50 passengers a day until 1970, when disaster struck. Engineer Antonio Roche explains.
In 1970, an accident took place in the French side, and one of the bridges of the line collapsed. Since then, the line was cut, and this brought here a rapid decline.
The The decision not to repair the bridge was the final nail in the coffin for Canfranc. In 2010, high-speed rail travel between Spain and France was introduced, using a standardized gauge. But these lines go nowhere near Canfranc. Whatever the future holds, Canfranc will always be a reminder that a standardized system is an essential part of a united world. As we continue pushing the limits of engineering, some projects will be hits, others will be misses. So long as engineers keep using their ingenuity, for every problem, there will be a fix. Coming up on our grand tour of construction calamities, parking in Baltimore becomes a slow-motion catastrophe.
I can remember just seeing the vehicles go down, and they sank in.
A narrow escape for the most famous building error in the book.
The tower began to sway slightly out of control.
A Manhattan skyscraper with a deadly design flaw.
There could be up to 200,000 fatalities.
And a state-of-the-art bridge with a balance problem.
We were looking at it and we were thinking, what's going on?
With big builds, even the smallest mistake can be a huge disaster. From miscalculations to misunderstandings, these are the massive engineering mistakes that only an expert can hope to fix. When engineering goes wrong, news crews usually arrive after the dust has settled. But when the calamity is caught on camera, we get a unique window into what went wrong. Just like our first catastrophe in Maryland, USA, here in Baltimore, life on the street got very dangerous in 2014. The neighborhood had been sitting on a ticking time bomb.
When it was ready to go, boom, it just went.
And it hit like a mortar round. Boom!
Baltimore. This grisly old harbor town is nearly 300 years old. Almost a third of its buildings are registered as historic, more than in any other U.S. city.
Baltimore is one of the older cities in the U.S., and there's a lot of structures that were put there at least 100 years ago. And of course, you know, time takes its toll.
This aged Atlantic seaport is always in need of some TLC.
The maintenance of any large city is a massive undertaking.
As the Charles Village community discovered, dramatically, one rainy April day in 2014, residents of East 26th Street noticed that years-old cracks in the road were growing rapidly. Community leader Matt Brady witnessed the event firsthand.
I remember it was raining so hard, this crack right here, literally opening up, like peeling an orange.
Next to the railway, beneath the road, was a retaining wall, and it's worth mentioning that this wall is 100 years old.
The old retaining wall supporting 26th Street above the train tracks was beginning to give way.
One of my supervisors in the field came in named Howard. He said, hey, Matt, the street up there on 26th Street is about to give way. I said, what are you talking about? He said, the street. You know, the rain's coming down is causing the street to separate.
By midday, the cracks in East 26th Street were growing wider.
And I remember running over here It was amazing. And literally, you could stand right here and see this wall leaning. To be quite honest, I was afraid that if a train came through, somebody would die. I began to tell the guys, say, hey, I need you to do me a favor. I need you to take one of the trucks, block this street right here. Make sure no traffic goes down there, because that'll make it worse.
3 hours later, local residents looked on in shock.
Margaret Brent Elementary School is about to let out. And I said, man, we really got to make sure those kids don't get out. So we sent one of our guys over there to talk to the administrator, said, look, don't let the kids out. It's a major emergency. The next thing was to secure the area and to make sure these residents were out of their houses. Now, to stand right here, and I will never forget, to see these cars leaning literally at a 90, almost like it's like a 90-degree angle. And to hear the street crackling like bread, I mean, you can stand here and just listen to the street tear.
When the road starts cracking like that, and you've got this 100-year-old retaining wall, inevitably, it's not gonna go well.
A passerby with a camera pushed record just in time.
And I can remember just seeing the vehicles go down, and they sank in, and then like in a matter of moments, we watched that whole side of the street explode. And it hit like a mortar round, like boom!
The collapse was an urban landslide.
When landslides happen, they can be really sudden and dramatic. People in nearby houses thought a train had derailed just by the sound of this. And it brought, 8 cars with it. These things were totaled, just crashing down onto the tracks below.
Amazingly, no one was killed.
You never, ever would imagine a million years to witness something like that and to see the pain on so many people's faces, to see people crying. After it collapsed, there was like a deafening silence.
As the dust settled, witnesses wondered what had caused this cataclysmic collapse. The seeds of the disaster were planted more than 100 years ago, when a new railroad was built. This Baltimore neighborhood was at the top of a slope, leading down to the tracks. In 1914, engineers built an 11-meter-high retaining wall to support the road above the railway. It was a massive undertaking. And right from the start, it was subjected to Baltimore's extreme climate and soft geology.
Baltimore is built on clay soil and gets very cold, harsh winters, but also heavy rains. And all of those things combined causes a lot of ground movement.
Baltimore's temperatures fluctuate between scorching summers and freezing winters. As the Earth freezes, it expands, then contracts when it thaws.
It's those things that brought the retaining wall to breaking point.
April of 2014 was one of the wettest on record, and by the 30th, the already unstable ground was dangerously waterlogged.
There's no doubt that the heavy rainfall prior to this disaster played a huge role in bringing down the wall.
While the wall did stand up to brutal conditions for a century, in the end, this was a massive fail. The city had a disaster on its hands, with a road destroyed, a railway line buried, and residents forced out of their homes. An engineering rescue was desperately needed, and fast. Jim Gwinther was the project manager in charge of the repair mission.
About 1:30 in the morning after the incident, and we had everyone evacuated and we had all the utilities turned off. It was probably still raining. And at that point, we understood that we had to break this problem into 4 distinct parts. The emergency response, which was make it safe for the community. While that was going on, we then had to come up with a solution that would allow us to do a temporary fix that allow the residents to get back into place. and allow us to then work towards the final solution, which was excavating the material to allow for that construction.
Once Jim's team had cleared the site, they got to work on a new retaining wall to support the road above. To create rock-solid foundations in the soft ground, engineers installed 65 reinforced concrete columns. To improve drainage, they added a layer of sand and gravel. But this wasn't just a physical fix. The rules were changed to ensure this wouldn't happen anywhere else in Baltimore.
If there's a silver lining to this, it's that now there is one department who is responsible for monitoring ground movement and looking at its impact on structures in Baltimore.
An early warning could be the difference between life and death. Geophysicist Colin Dubinsky is part of Baltimore's new ground monitoring department. Colin and his team use cutting-edge tech to probe the ground for weakness.
We often call for these ground-penetrating radar scans in areas where we're unclear if there's an anomaly or a void that might be present underneath the street level. It's oftentimes that the sidewalk or the roadway, they don't actually fall in even if there's something underneath of it for some long period of time. So this equipment basically is our eyes below the ground.
Meanwhile, Jeff Basford checks for ground movement, lowering a slope-detecting inclinometer into a borehole beside a wall. Over time, the results reveal if the borehole is shifting in unstable ground.
We'll lower this probe to the base of our wall. We can take our sensor here, and we'll take an initial reading. And I'll pull it up at defined increments, about 2 feet at a time, and I'll take a second reading. And I'll do this successively all the way until I get to the top of the wall. Over a period of weeks of time, and we can make a plot. So what we're looking at here is the depth of the probe that is going down, and then the distance that that probe is out of vertical.
With constant high-tech monitoring, city officials can now spot problems developing below ground before they turn into a major disaster.
I think if there's a lesson to be learned here, it's that when you see warning signs like giant cracks in the road or land shifting, it's only a matter of time before something catastrophic happens.
Construction disasters can strike from nowhere without warning. But sometimes, the catastrophe unfolds in slow motion. For this next calamity, we head to Italy. And a new twist on the best-known building blooper of all time.
At 800 years old, this is the original engineering mistake.
The Leaning Tower of Pisa is one of the most famous buildings in the world.
Everyone who comes here wonders why it doesn't fall.
But just 30 years ago, engineers came close to destroying it. Pisa in the 12th century was a growing naval power.
The Pisans got rich quickly by raiding Sicily, and they wanted to show the world how important they now were. Centuries later, we still see how important they are, but not quite in the way they wanted.
In 1173, the Pisans started building an ornate bell tower for their cathedral.
No one had built anything so ambitious here, and things started to go wrong very quickly.
As tour guide Chiara Celli explains.
Just a few years since the beginning of the construction, when they reached the 3rd floor, the tower started leaning. And it was not supposed to lean, not at all. So this was a really bad mistake.
The tower was actually sinking on one side, but rather than stopping the construction, they continued to build it taller.
But as the tower was slightly leaning towards one direction, the second architect made the next levels slightly leaning opposite.
Building one side higher than the other is never going to be the best solution. Surely it's a sign that something is wrong. You are just asking for trouble.
Hoping to correct the lean, they even tried adding more steps and taller columns to one side. But the extra weight made things worse.
It seems obvious, but you have to remember that engineering knowledge at that time was nothing like it is today.
Throw in a series of wars, and it took 200 years to get the off-kilter building finished. Finally, in 1372, the tower opened, and it's been leaning ever since.
I can demonstrate with this ball that the tower is inclined, and this is not horizontal.
Ironically, the delays to construction are why it's still standing today. If they had built it any faster, the tower would have certainly toppled because they had made a fundamental error at the start.
What did the original engineers do so wrong that they condemned Pisa's tower to lean?
This might be the right time to point out that in ancient Greek, Pisa means marshy land.
Author Nicholas Schrady is well versed in Pisa's geology.
Most of the terrain in Pisa is essentially a former bog, a former swamp, and the subsoil in Pisa is extremely shifty and delicate, and it does not withstand heavy loads.
Sandy and soggy ground is definitely not ideal for tall, heavy towers unless they have rock-solid foundations.
And this is the root of Pisa's problem. The tower's foundation is far from solid. The 57-meter-tall tower sits on supports that are only 3 meters deep and surrounded by soggy ground. Nowhere near strong or stable enough for a 14,500-ton pile of stone.
It's like building a tall tower on a sponge. It can only go so high before it's going to start leaning. In fact, it's a miracle it never collapsed.
The tower's tilt was enough to startle onlookers, but crucially, not enough to topple it. The original mistake occurred at the beginning of construction, but the tower survived for centuries. However, just a few decades ago, engineers came very close to bringing the tower to its knees once and for all.
Most of the attempts have failed, and those who most wanted to save the tower are really those who almost contributed to toppling it over. One of the most brutal interventions in the tower was conducted by Mussolini, and that intervention was about as brutal as fascist politics. He had the idea of boring 361 holes in the foundation and pumping it with 90 tons of cement. Mussolini also owned the cement factory, it should be said. The tower began to sway slightly out of control, but it's always managed to stabilize itself.
By 1990, the tower's lean had reached an angle of 5.5 degrees. Officials feared this icon would finally fall, and for the first time ever, it was closed to the public. They had every reason to worry.
Now, lots of ancient buildings, they do lean, but the Leaning Tower of Pisa just looks like it's defying the law of physics. And that's all to do with its center of mass, which is just about here.
Experts calculate the tower's center of mass is around the 4th floor. As long as this sits above the base of the building, it will stand. But if it moves outside of that area, you have a disaster.
Calculations show that when the tower was at a lean of about 5.44 degrees, it should have collapsed. Now, by 1990, it was already at 5.5. It should have gone down. No one knows why it didn't collapse.
With so many rescue efforts over the centuries, the calculations of the lean have become confusing. To make matters worse, the lean compounds an issue hidden in the walls that could take the tower out before the lean knocks it over.
The greatest danger for the Tower of Pisa has not been that it should simply fall over because of its weight. There are other dangers as well, one of which is the incredible amount of stress which is produced on certain areas of the tower due to the weight of the tower.
The tilt strains the walls, which can be devastating to a structure built from solid stone. But while these look solid, the walls are filled with a random mix of building materials, making them less sturdy.
There has been a great concern that the tower would rather burst and implode rather than topple over.
Not only could the tower have fallen, it could have exploded at any point. It defies belief that it's still standing.
Back in 1990, with the icon threatening to fall, the world's best engineers rushed to save it, with almost catastrophic results.
What they first did was they bored holes down 40 meters into the bedrock and introduced steel cables to stabilize the tower. Now, in order to do that and not have the entire terrain become flooded with water, what they had to do was pump those boreholes with liquid nitrogen.
When you freeze the ground, you're also freezing the water contained within. And when water freezes, it expands.
And when the water thawed, the ground shrunk, causing the tower to rock back and sink as much in one night as in the previous year. Once again, this icon was close to collapse. Could engineers finally save the mighty tower? The team secured it with cables to prevent disaster, then went back to the drawing board. They came up with a solution that they hoped would finally stop the building from falling further.
Most solutions tried to help support the structure, but this just put more pressure on the ground underneath, making the problem worse. Eventually, wily engineers let gravity help out.
They had to start basically digging, drilling through into the soil, and they started removing really slowly the sand and a bit of the clay. So they created like a hill of clay nearby here, and then the tower started leaning a little bit less. So it became to lean now, it leans as it used to lean 2 centuries ago.
Digging under the tower turns out to have been a brilliant idea. It reduced the lean by about 10%, which, although that doesn't sound a lot, it brought the tower back from the brink.
It took more than a decade to complete the undermining fix, but in 2001, the tower reopened to the public.
Crucially, the angle was down to 4 degrees, well below the 5.44 limit, enough to prevent a collapse, for now.
But with a landmark this renowned, Nunziante Squeglia from Pisa University is leaving nothing to chance. He's using precision optical sensors to track the smallest changes in the tower's tilt.
This is an optical level. This instrument, we can measure on that scales if there are some movements of the tower. I measure the variation of that points, and from the variation of the elevation of that points, I deduce the rotation of the foundation of the tower.
In a way, the fact that the Tower of Pisa is located in the Campo dei Miracoli, or the Field of Miracles, strikes me as perfectly apt, because the tower should have toppled, in fact, centuries ago, and it hasn't. It goes on standing and will for 300 more years at least, and that, in a way, is a miracle.
Let's hope they're right and the tower continues to lean for hundreds of years, but just not too much.
With some fails, the engineering error is there for all to see. But other mistakes lurk hidden. A ticking time bomb, just waiting to go off. Now we're heading to New York and a skyscraper that was very nearly blown away.
This blunder sounds too incredible for it actually to be true.
This tower hit a deadly flaw that could have devastated Midtown Manhattan.
There could be up to 200,000 fatalities.
Until a sharp-eyed engineering student saw the storm brewing.
Only luck prevented a genuine catastrophe.
Manhattan, the spiritual home of the skyscraper. In 1977, a high-flying investment bank opened up its headquarters at 601 Lexington Avenue. At 59 stories, the tower was the 7th tallest building in the world.
601 Lexington, at first glance, looks like a typical skyscraper. It's actually this really unique engineering marvel.
The fact that it ever got built in the first place is a little short of a miracle.
Defying skyscraper convention, 601 Lexington is elevated on stilts, 9 stories high. Sitting not at the corners, but midway under each side. And nestling beneath the tower is St. Peter's Church. Construction lawyer Michael Vadaro explains the unusual layout.
When Citicorp purchased the land from the church that sits in the northwest corner, there was a specific mandate that the building could not in any way touch the church. It presented a very difficult scenario for the engineers and architects of the building to figure out how to effectively use the space and yet keep the church separate.
As part of the deal, St. Peter's had to get a brand new church at the exact same location. Avoiding the church was a serious architectural challenge.
With astronomical property prices in Manhattan, they couldn't afford to just use part of the plot. They had to use the whole thing. So the architect came up with a solution that really pushed the boundaries of engineering.
Incredibly, the new skyscraper straddled the church.
The design is ingenious. It avoided the church and it created a unique building. Problem solved, right? Not quite.
Placing stilts under the sides, not the corners, meant they had to rewrite the construction rulebook. Engineer Stephen Ressler explains.
That architectural design created a really unique set of demands on the structural system, and the structural engineer responded in an equally ingenious way. The essence of that structural concept was the inclusion of these V-shaped diagonal braces, called chevron braces, into the design of the structural system. And what the chevron braces do is pick up a very substantial part of the weight of the structure, which are configured such that they transmit that load diagonally from out here at the corners into the central spine, such that all that weight can then be safely transmitted directly vertically downward through the supercolumns into the building foundations.
Conventional skyscrapers are supported by both vertical and horizontal beams. Switching to chevron braces was the key to using stilts and levitating over the church. When the tower opened in October 1977, thousands of people were soon working in the 59-story giant. All seemed well until June of 1978, when Diane Hartley, an engineering student, discovered an unforeseen danger.
This was such an interesting building. It was really novel. The design was of a type that hadn't ever been done before. And so I attempted to replicate the calculations that the engineer of design would have undertaken.
Although Diane was still a student, what she discovered was astonishing.
She believed the 59-story tower building was at risk of toppling.
According to Diane's calculations, in a strong enough storm, the building would be blown over.
I called the engineers once or twice and got them on the phone and compared some notes, and they convinced me that the building was strong and the building was safe. I accepted their word and so noted in my thesis.
But the team did double-check its calculations and discovered that Diane was right. 601 Lexington Avenue really was at risk of falling down. Shockingly, the tower was under threat from an unforeseen danger: storm winds hitting the corners. Engineers crafted a tower that could take winds of up to 110 kilometers per hour if they hit directly on the sides, but not if those winds hit at the corners. Robert Rattay later worked with the lead engineer. and explains why this wasn't factored into the original design.
At that time, the building codes required that the wind loads on a building be calculated on the basis of the wind hitting the building flat on. And that's what they did. And then later on, by the student who did the thesis, it was discovered that actually the wind loads are different when it comes against the corner of the building.
But the risk from corner winds wasn't the only threat. There was another problem, this time with the building materials.
Lemaisure's engineers and the contractor who was responsible for building this structure had actually made a substantial change to the original design while the building construction was underway. And that change was to modify the connections which tied the diagonal braces into the remainder of the structural system from welded connections to bolted connections.
A weld is one piece, so it contains less points of weakness. That's not the case with a bolt that contains many different parts. So a weld will take much greater forces than a bolt.
If all of the computations that were done to document the problems are correct, these connections would have broken. Here, here, here. And these rectangular panels would have distorted into parallelograms, and the entire building would have essentially tilted over and fallen sideways.
Thousands of bank employees and Midtown residents continued with their daily lives, while engineers wrestled with the numbers. Based on the wind calculations and the bolted joints, experts predicted the perfect storm in terms of strength and direction could hit the tower once every 16 years, with catastrophic results.
Now, just a few blocks north and west of here, we have Central Park. But there are a number of buildings and a number of businesses that are located here. And so if you picture this 715-foot tall building toppling over, it would essentially create a domino effect that would take out this entire swath of Manhattan all the way to Central Park. The American Red Cross actually estimated that if that happened, there could be up to 200,000 fatalities.
Diane's warning came in June, and with hurricane season looming, engineers had a strengthening solution by August. To avoid panic, the team kept their work quiet.
So implementing the fix happened at night. During the day, workers would come into the building and work, yet at night, this secretive process of fixing all of the issues of the building was taking place.
I remember having seen more than once these lights, sparks at night. Sometimes people talk about it. You know, when you come into LaGuardia, you have these things. What's happening? Well, what was happening, they were welding at the City Core building, but nobody knew what it was.
The solution was simple. They welded 5-centimeter thick plates across each of the building's 200 bolted joints. The 3-month repair job became a race against time. Hurricane Ella was lashing its way up the coast. A massive evacuation was almost ordered, but at the last moment, the hurricane veered away and disaster was averted. The design flaw and subsequent fix went largely unknown for almost 20 years, until in 1995, a New Yorker article made it the stuff of legend.
With such a mammoth mistake, you'd expect the engineer responsible to be in a lot of trouble.
It has become a legend, the way he handled it. He came clean in a very professional and smart way. He not only announced the problem, but he came with a solution.
Diane, the student who saved the day, still reflects on the experience.
So when I think about the fact that My call led to someone after the fact realizing that there was such a critical problem with the building that if it hadn't been discovered, could have made for a major catastrophe in the city. It's kind of mind-boggling, and it makes you feel very humble.
This was a catastrophe waiting to happen, and until Diane warned them, nobody knew anything about it.
When you're attempting something that's never been done before, even the biggest brains will get it wrong sometimes.
When buildings go bad, not all engineers have the luxury of fixing them on the quiet. Some fails you just can't keep under wraps. Like this story in London, England, with a bridge that made headlines for all the wrong reasons. Bridges have been built across the Thames for centuries.
London is famous for its bridges. By my count, there are more than 30, some over 200 years old.
But 20 years ago, a new iconic bridge left pedestrians with a very queasy feeling.
It was a fundamental design flaw that even the biggest engineering brains overlooked.
With the year 2000 approaching, London was looking for a flagship project to mark the arrival of the 21st century. The winner was the aptly named Millennium Bridge, a unique pedestrian-only crossing spanning the Thames. Roger Risdell-Smith was part of the design team.
We came up with the idea of this being a blade of light because we wanted it to be a slim, very, very thin structure. We wanted something that when you stood on the bridge, you would have an unimpeded view all around you because there would be no structure that would come up above your sight line.
Engineers went with a modern take on a classic bridge design.
The Millennium Bridge may look different. There's actually a suspension bridge, like the Golden Gate Bridge in San Francisco. However, this is a lateral suspension bridge. Instead of the weight being supported by wires from above, they're tethered to supports on the side.
There were none of the columns or cables that would have ruined people's views of the River Thames.
You can see why this bridge was chosen. The design was absolute cutting edge, and even 20 years later, it still looks so beautiful.
The Millennium Bridge opened to the public on June 10th, 2000. But things didn't go as planned, as it started to sway dramatically.
It was around about 50 to 60 millimeters movement in each direction. So a total of about 100 to 120 millimeters movement. It wasn't continuous. It would happen for a little bit of time, and then it would stop again, perhaps 30 seconds, perhaps a minute, and then it would stop again. But nonetheless, it was an effect that we could feel, and it was something where we were looking at it and we were thinking, what's going on?
All bridges undergo some sort of movement or flexibility. It is built into the design, but this kind of movement was seriously worrying.
The more people that crossed the bridge, the more it swayed.
When the bridge opened, it became very, very crowded. In fact, we calculated afterwards that around 100,000 people crossed the bridge on that first Saturday.
Just 2 days after opening, amid fears of injury, they were forced to close the bridge.
Spotting the failure so soon after it opened made headlines around the world.
With the eyes of the world on them, the project's lead engineers had to figure out why their bridge was swaying, and fast. The cause was something they hadn't predicted, a perfect storm of physics and engineering, triggered by crowd dynamics. Professor Wanda Lewis is an expert in bridge design.
The people on the bridge, when they walk on a bridge, they don't walk in straight line like on the catwalk, models like that. We tend to walk like so. So there's going to be a certain angle to the force exerted on the deck. So there's going to be a predominant vertical force and very tiny lateral force. When you've got thousands of people on the bridge, each exerting this small lateral force, that was enough to put the bridge into lateral sway.
That tiny lateral force isn't a conscious choice, but how we've evolved to stay upright, as civil engineer John McDonald demonstrates.
So what we have here is a very simple representation of the human body. We've got the centre of mass or centre of gravity, which is roughly sort of tummy height, and then we're standing on our feet down at the ground, which is below that. So we're essentially unstable because we've got the mass up here, but the support down here. And so if we don't do anything, then we'll fall over. But what happens is, rather than falling over, we adjust the position of our centre of pressure under our feet. So rather than falling over, we move around in the same way as we move the centre of pressure under our feet to keep balance.
The crowds walking in time, side to side, caused the initial sway, but this in turn triggered another issue, a result of the bridge's radical design. With cables running alongside the bridge instead of suspended from above, they had to be extremely tight, and as the bridge swayed, they vibrated.
There was sufficient number of people to excite these cables, which are basically like guitar strings being plugged.
If you pluck a guitar string, it vibrates at a certain note. All structures are the same. If they are hit with a force, they vibrate at a certain frequency. That's called resonance.
Resonance can be extremely destructive. Although there was no structural risk to the Millennium Bridge, this same force was at the heart of the swaying. The vibration caused by the crowds of marching people settled into a rhythm. By pure coincidence, its resonance closely matched that of the bridge's structure. The two forces working together exaggerated the movement.
When masses of people walked down that bridge, they created a natural frequency, and that frequency matched the natural resonant frequency of the bridge itself. And those combined frequencies created a sway that was out of control.
Resonance has been a factor in bridge design for more than a century. Long ago, Army engineers realized that troops marching in step would shake bridges. But this lateral design had unforeseen consequences. Having identified the problem, the team was desperate to save its reputation and went to work on a fix.
What we did was, through that summer, we carried out a walking test where we walked employees from the companies involved in the design over the bridge, and we measured the effect of the pedestrians as they walked over the bridge, what it did to the bridge.
Guided by the tests, the team devised an ingenious and crucially almost invisible remedy: shock absorbers, also known as dampers.
We came up with a solution having carried out those tests, and that was to install dampers across the whole length of the bridge. And those dampers are like the shock absorbers on your car. They're a compressed cylinder of fluid, and a piston strokes through that fluid, and as it does so, energy is dissipated. And you can see some of them here, just beside the arm, beside the transverse arm, is one of the dampers. And these dampers just move very, very slightly to the very slight movements of the bridge that occur now. And as they move, they absorb the energy from the walkers, and that dissipates the energy and stops the movement from developing and becoming larger.
Adding the dampers was a relatively simple and effective solution to the problem, and it still maintained that design criteria, which was to leave the view of St. Paul's wide open.
In February 2002, we carried out a final crowd test where we organised for 2,000 people, the largest test of its kind done on a bridge, to be walked over the bridge and for the movements to be measured. And we did that. That's a very substantial number of people. We needed to have it it was organised by people who organise football crowds, and they walked the people over the bridge, all 2,000 of them, and the bridge behaved as predicted, and the movements were reduced.
Testing and fixing the bridge took a year and a half. In 2002, it reopened, steady and shake-free.
The south bank of the river now has the Globe, the Tate Modern, and with the bridge as well, that makes this area, which has now become incredibly busy, full of people, both commuters, people going to work, but also tourists and people just visiting. It's become a very, very busy area. It's really transformed.
The engineers must have been so horrified by the swaying of the bridge, but ultimately it led to a great solution, and sometimes failure teaches us so much.
The important thing is that they put their minds together and came up with a really simple solution that didn't impact the striking design.
Construction calamities come in all shapes and sizes, from the sudden to the slow, the secret or not. So long as we keep building, there will always be more blunders to fix. This time on our global roundup of incredible engineering calamities, an apartment block that resisted demolition.
What a disaster!
A once thriving mining town now lies abandoned.
It became clear that this was no place that people should be living.
An engineering mix-up derails a new bus route.
How did they manage to get this so wrong?
And a global fail that's knocking the wind out of green energy.
The tips of those blades are traveling at supersonic speeds, so friction becomes an issue.
With big builds, even the smallest mistake can be a huge disaster. From miscalculations to misunderstandings, these are the engineering catastrophes that only an expert can hope to fix. As engineers push the boundaries of materials and design,
we have a space station in orbit, but it's crippled.
Every measurement is checked and double-checked with millimeter precision. But sometimes older constructions hold surprises that no one saw coming.
If it did actually fail and flood this area, those people would have been washed away.
Like this catastrophe in England, with a building that refused to budge.
A demolition like this, you've got to get it right first time.
An engineering fail that became the talk of the town.
I think at that point, there were a lot of concerned residents.
In the mid-20th century, Britain's population was booming. In crowded cities, planners found a new solution to create residential space.
Instead of building more houses and building out, they built up.
Concrete apartment buildings sprung up across the nation. With their views across towns and cities, they proved a hit.
At the time, these were a modern solution to the post-war population boom.
But decades later, many of these giant constructions were becoming worn out, and it was closing time. As demolition expert James Bibby knows only too well, bringing these solid concrete towers down is no easy job.
We demolished buildings in major cities that were built in the 60s. These were typically built by concrete methods. They want concrete beams and concrete floors. It's been built with a high density concrete and it's heavily engineered. It's just hard as nails.
In 2016, two 50-year-old apartment blocks in the Seaforth area of Liverpool were earmarked for demolition: Churchill and Montgomery House. Journalist Elaine Wilcox followed the story.
So the story I was covering was an area where there was going to be some major redevelopment getting rid of the old 70s tower blocks and creating green space, new housing, new places for people to go. When we arrived, we were struck by just how close they were. These were enormous tower blocks, and they were surrounded by houses, very, very close.
The 15-story towers were surrounded by residential streets. Rather than a slow, piece-by-piece demolition, contractors opted to knock the towers down with a controlled explosion. Noisy and dusty, but quick.
When an explosive demolition works well, they're great. They can take down massive structures in no time at all.
With explosive demolition, charges are placed at strategic points within the building, from the central supports to the foundation.
On a concrete tower block, the stair core is typically the strongest part of the building, so we must ensure that we blow that stair core so that it fails. We'll blow 2 to 4 floors as well. So they will blow milliseconds apart, and then you'll blow the stair core with it.
The trick to a successful explosive demolition is getting the building to collapse in on itself rather than exploding outwards. So you put charges around the building and they then go off and weaken the concrete. And then what happens is the floors sort of concertina into each other until the whole thing is collapsed.
Although highly regulated, explosive demolition still comes with risks, including flying debris. So in Seaforth, the local area was evacuated. In theory, once the dust settled, residents would move back home.
Some people were gathered, they were waiting, they had their cameras at the ready. At the allotted time, big noise, big explosion, and the 2 tower blocks just stood there, nothing happened.
Things had clearly not gone to plan. But as they say, if you first don't succeed, you just try again.
A few hours later, the demolition crew gave it another go.
Suddenly, there was a real rumble, a lot of noise, and Churchill Tower, that was standing here, that came down. But then they looked at the other tower block, and that was still standing.
Churchill House was now a pile of rubble. But although weakened by the explosions, Montgomery House was still standing. Until the tower was demolished, hundreds of residents, including Jake Curtin, weren't going home that night.
I think what was scary was the fact that nobody actually knew what was going on at the time. They were telling us they were going to pull it down, they were telling us they were going to do another explosion. Everyone was concerned. You know, my house is right next to it. Is it going to crush it? What's going to happen?
Engineers had to work out what had gone wrong and come up with a plan to bring it down. One small problem: they couldn't go inside the building to inspect it.
After 2 failed attempts, the structure was actually weakened and it could have collapsed at any time. The demolition team couldn't have got any sleep.
The next morning, the tower block was still standing. Engineers came up with a very simple plan to bring it down.
Having already tried to demolish the building twice, it was now too unstable for people to go in and prime the place with more explosives. So what they had to do was put cables around the base of the building and just use giant heavy machinery to pull it over.
Everyone was hoping for better luck the third time around.
Oh, no way! What a disaster!
The wire had only managed to pull the corner of the tower down, and now the building was even more unstable.
You think that you've got these plans, they know exactly what they're doing, the professionals. Why can't they bring this blooming building down? It was unbelievable, and to sit here and watch it unfolding in front of me was something else. It was crazy. You think it would just be boom, done, and that was it. And I think that's what everybody else thought as well.
The contractors were in the eye of the storm here. We spoke to them. They eventually did some interviews, and you can tell they were trying to be reassuring, to reassure residents, but they looked in shock themselves. Their body language, their appearance, they didn't know what was happening.
As a health and safety report later concluded, the engineering team had properly prepared for the demolition, as proven when Churchill Tower came down. But they later discovered that both towers were reinforced in a way that wasn't on any official plans. They just got lucky with the first tower. Montgomery Tower, however, resisted the explosions thanks to some small, undetected metal pipes.
We understand the reason why it failed was because there was these huge concrete columns and they had these steel rods inside, and that's what kept the building standing despite the explosion, the explosion, the explosion.
Concrete is strong when it's compressed, but it's much weaker under tension. So in large buildings, concrete is normally reinforced with steel bars called rebar.
Montgomery Tower was held up by 12 concrete columns. Deep inside each were a number of 10-centimeter long steel pipes, each about 2 centimeters thick, filled with concrete.
It turns out that pipes just about this thick could have been responsible for the failures.
Information on the short sections of pipe was missing from the tower's official paperwork. So contractors had not factored it in when drawing up the demolition plans. Now, only one option remained. Call in a specialist piece of machinery called a high reach. These supersized, custom-built excavators are used worldwide to bring large buildings down, slowly but safely.
It is the largest piece of plant that a demolition contractor will use. It reaches up to, typically somewhere between 7 and 20 stories. Its nickname is the long arm. It's absolutely massive.
A high reach has a powerful diesel engine, which pumps hydraulic fluids to raise the massive arm. A separate hydraulic system powers the giant shears, giving them huge strength for cutting and crushing with extreme precision. The operator is protected by reinforced glass with a series of cameras to help guide the arm as the building is brought down chunk by chunk. In Seaforth, the day after the failure, the team call in the tallest high reach in Europe, Goliath. With Goliath in action, residents had to stay clear for another 3 days, until finally, Montgomery House was safely down.
A week later, took many days, the buildings were down, and it's the start of the regeneration and hopefully, something positive here in the future.
Construction disasters can strike out of the blue, without warning. But some have been going on for so long, you can't help but wonder how things got so bad. For this catastrophe, it's off to Oklahoma and a decades-long engineering nightmare.
Looking back, this is just a smash and grab on the landscape.
This place has been described as one of the dirtiest places in America.
The seeds of disaster were sown a century ago, but it was only decades later that the true danger to this town was fully revealed.
This place is not only completely desolate, it's deadly.
The Tri-State Mining District straddles the borders of Oklahoma, Kansas, and Missouri. For more than a century, it was one of the world's most productive iron and zinc mining regions. At its heart, the town of Pitcher, Oklahoma.
Pitcher was your typical American town, baseball, apple pie, and hot dogs.
Although it's now abandoned, a little over a decade ago, Pitcher was full of life. John Sparkman's family lived here for generations.
This was my home in Pitcher, Oklahoma at 437 South Connell Avenue, and I grew up here having Sunday dinners here, family gatherings, birthdays, all the things like that that a normal family would have.
Phyllis and Greg Cruzen grew up and raised their family here.
We didn't even lock our doors.
Yeah, and
Because if your neighbor needed you, they just came over and
yeah,
knocked, and sometimes knocked and came on in.
yeah. Lots of times they would just knock, or not even knock, and just walk in your door and say, hey, how's everybody doing in here tonight?
The boom began more than 100 years ago, when vast deposits of lead and zinc were discovered here. Journalist Wally Kennedy explains.
The mining in this area started in about 1918. And the reason why it came here is because this ground contained very high concentrations of lead and zinc ore compared to what existed in Missouri.
Lead and zinc were vital in every walk of life, from pots and pans to wartime ammunition. The metals are scattered within vast seams of less valuable but very solid rock called ore. Miners used dynamite to blast out the ore, creating a massive network of tunnels and chambers. Around Pitcher, these so-called rooms and pillars ran about 60 meters below ground. Miners had to extract 17 tons of ore to get just 1 ton of metal. Pumps worked constantly to remove groundwater, keeping the mines dry. When active, more than 160 million tons of ore were mined, producing less than 10 million tons of the valuable lead and zinc. The leftover waste, or mine tailings, were dumped in massive mounds around the town, known locally as chat piles.
We used to live on the south end of town, and people would come in and pull beside the road and want to know what type of mountains these were, what was the name of the mountain range. And we would laugh and just tell them, say, those aren't mountains, those are just chat piles.
The mines operated for 5 decades, producing metal worth billions of dollars. At its peak, more than 10,000 men worked the mines. The lead they produced was vital to America's war machine. But by the 1960s, Pitcher's mining boom had come to an end. The lead and zinc ore was all but gone. Operations were shut down, and the mining companies left town. That should have been the end of the story, but the decades of mining had set in motion a chain of disasters, which would only become apparent years later. As the mines closed, there was no longer a need to keep the tunnels dry. The water pumps were removed, and the vast underground network began to flood. Toxins made their way into the local waterways. Craig Creeman works with the Environmental Protection Agency to monitor the ongoing problem.
The mine waters are coming up. I think it's about almost 900 liters per minute, or 250 gallons a minute, that are coming out of these points of discharge. You know, they had millions and millions of gallons of water that took over 10 years, from about 1970 to almost 1980, to basically get itself up to the top of the mine workings. And that's what this was. It was mine-influenced water, upwelling, orange-colored water coming out of the ground.
Tar Creek, which is just half mile back to our west from here, was flowing orange because a lot of water was bubbling up out of the ground, out of the mines, and flooding the water system.
But contaminated water was only one lingering issue from the mining days. Something equally dangerous had been part of life in Pitcher for decades. More than 100 million tons of waste material towering over the town, the chat piles. Despite being processed, they still contain dangerous levels of both zinc and lead, which poses major health risks.
We've had lead around for years in pipes, in paint, in fuel. For a long time, people have known that it's been toxic, but it was just too useful to give up on.
5 decades later, with lead being the main threat, the EPA still monitors the toxicity of the chat.
You know, right away, zinc's 1,500 parts per million, which our remedial goal for zinc's 1,100. And lead's right at about 500, which is our remedial goal. But if you dig your heel into it, you can start seeing a lot of that finer stuff below it. So when I do that,
but already the lead's at 850 parts per million and zinc's 5,500.
Although the chat had been here for decades, the full risk from the lead only started to hit home in the 1970s.
Lead primarily is the big human risk driver because of its neurological effects it has, particularly in children. So here in Pitcher, as a lot of these kids were growing up and exposing themselves to this chat, and sometimes the kids would ingest it, stick their hands in their mouth. 5,000 parts per million lead, or even 500 parts per million lead, it's not good for children.
By the 80s, the impact of Pitcher's chat piles on local residents started to become increasingly apparent.
Many of the people who lived here had medical problems. Their children had learning disabilities or some sort of hypertension. Adults had high blood pressure, and there were just a vast number of illnesses.
In 1983, the EPA declared Pitcher part of the Tar Creek Superfund, official recognition that the levels of lead were dangerous to its residents. Cleanup efforts began, which continue to this day. But below ground, there was yet another threat to the town, an unfolding catastrophe caused by the decades of tunneling.
This ground is very unstable. It could cave in at any time.
The ground beneath Pitcher is riddled with more than 500 kilometers of mine tunnels and chambers, some 30 meters high. Sudden subsidence has been a problem since mining began in the early 20th century. In places, the entire surface disintegrated, forming sinkholes. But the extent of the problem was only officially investigated in 2004. The U.S. Army Corps of Engineers was called in to survey the area. 2 years later, they revealed that 86% of Pitcher's buildings were now at risk of collapse. Pitcher had long been a bustling mining town. But the decades of extracting lead and zinc was now destroying it. With contaminated water, hills of toxic waste, and unstable ground, the solution to this crisis was drastic. In 2006, the U.S. government offered to buy the homes of residents with children so they could relocate.
In the neighborhood that I lived in was just awesome. I mean, we knew everybody. We took care of each other's kids. My best friend lived behind me, and their kids tested positive for lead, and so they were one of the first to move out. And so it was kind of sad. It was like breaking up a big family.
Realizing the danger, other residents gradually abandoned the town. Pitcher's fate seemed sealed in 2008 when a devastating tornado hit with winds of 270 kilometers an hour. More than 100 buildings were destroyed, with 6 fatalities. By 2010, just 20 residents remained, refusing to leave their hometown. The EPA has officially declared the region uninhabitable. Efforts to mitigate contamination to water have been ongoing for nearly 4 decades.
So what you see here is the Mare Ranch passive treatment system. Throughout here, these different individual cells are passively treating. They don't need any kind of mechanicals, but they're just passively flowing under gravity, down to a point where it discharges out these cells. And here we're at the end of it, and it's clean water.
Above ground, contamination is also being cleared.
These chat piles are going to have to be removed, but it's going to take a long time for them to do that because there's so much here.
Thousands of tons of chat piles have been removed, used to build roads, sealing the toxins safely out of harm's way. But the decontamination will take decades.
While I hated to see the town go away, I'm glad that children will not grow up in this environment anymore.
With no clever engineering fix, all they can do is look to the federal government for help.
Over the next 20 years, the government's going to spend $178 million on this site, and it's going to be a long time before Pitcher is going to be safe again.
For me, personally, it became clear that this was no place that people should be living.
While the cleanup continues, Pitcher stands as a reminder that engineers and officials must learn from the mistakes of the past.
It's incredible to think that this whole thriving community is now gone.
What built the town, I guess, is also what tore it down at the end. You know, the lead mining built it, and what gave birth to it also killed it.
Engineering projects come in all shapes and sizes. Some cost billions, with no promise of making anything back. So if you think you're getting something for free, there's always a catch. Like this engineering fail that's hitting a global industry.
Wind turbines are meant to be the future of electricity.
In the drive for renewable energy, engineers underestimated Mother Nature.
We're talking about waves, salt water, strong wind energy. All of those combining is an issue.
This problem has got engineers in a spin.
In the 1980s, engineers were looking for alternatives to fossil fuels. One obvious solution was to tap into an age-old source of power.
We've been using wind power for centuries. This is just the modern version.
Nature is providing an unlimited free source of energy. All we have to do is harness it.
Harnessing the wind is, in theory, very easy.
Wind turbines are relatively simple. As the blades turn, they turn a generator, and that generator creates electricity.
With such basic principles, building the turbines should have been easy. But as engineers soon discovered, it took a complex mix of strength and aerodynamics.
The blades of a wind turbine may look simple, but they've been perfectly designed to harness as much power from the wind as possible.
First, to extract the maximum energy from the wind, the blades have to be at the right angle, known as pitch. Getting the pitch right is crucial, as Professor Lawrence Coates demonstrates.
Here we have a model wind turbine, the typical 3 blades. These are all flat. In a real turbine, you'd find as you go along the length, they'd twist to try and keep the angle of attack as close to optimum as possible. And what I'm aiming to show is the effect that the pitch of the blades, that's that orientation, can have on the actual power you get out. These are at 45 degrees. And let me just see what the voltage is. We're getting a reasonable amount of power out there.
Now the professor reduces the pitch from 45 degrees to 22.5, so the blade should catch more wind and generate more power.
So now that it's moving, the angle of attack is actually more close to optimum, and we're now getting significantly more power out.
In fact, reducing the pitch by 22 degrees doubles the power output. Optimal pitch also changes with airflow. The pitch of most wind turbines is adjusted automatically with wind speed, increasing or decreasing the angle to extract the maximum possible energy from the air. Working hard, exposed to the elements 24/7, the blades experience huge amounts of stress. Creating strong enough blades is demanding, even with high-tech materials, as turbine engineer Craig Siddons explains.
So most commonly, blades are made of glass fibre and epoxy solution. So what we see up the top here is the fibre, the glass fibre itself, that's not impregnated with epoxy. And this green colour here is the impregnated fibre. So this up here is obviously not impregnated. It's quite nasty to touch, so I had to put my gloves on to touch it. It can get into the skin, into your pores, and it's all together, it's quite nasty stuff. So the reason we use glass fibre epoxy is because for the strength it gives is for not much weight, so we can build blades that are very, very long and extract as much energy as possible from the wind.
3 decades ago, turbines began to spring up in remote, windy locations worldwide and started generating power, as energy consultant Simon Gray explains.
Behind me here today we have the Scroby Sands wind farm. This is one of the early wind farms, one of the first in fact to go offshore. So typically on the daylight today, as you can see, it's fairly windy. We're talking about this particular array here generating enough for about 40,000 homes. overall, if we average it out across the year, I would say offshore wind and onshore wind is generating some 15 to 20% of the UK's energy.
As materials have become lighter and stronger, turbines have grown larger.
So if you imagine a building the size of the Gherkin in London, these are about the size of the towers. And if you think about the diameter of the blades, about the same size or slightly larger than the London Eye.
A single rotation of the largest turbine can power a house for a day. But if they're not turning, they're worthless.
Wind turbines aren't cheap. To make them pay, engineers have to keep them working constantly. Any downtime is extremely costly.
But only decades after the first wind farms were built, engineers worldwide discovered they had underestimated the power of Mother Nature.
Engineers are still finding teething problems with their original designs, and some of those problems are potentially huge.
Most concerning, these giants all over the planet were showing unexpected signs of aging, caused by particles in the wind.
You might expect that giant turbine blades could easily cope with a bit of dust and rain, but being exposed 24/7, 365 days a year takes its toll.
Believe it or not, when engineers first installed wind turbines, they thought they'd be pretty much maintenance-free. But they were wrong.
For years, engineers thought wind turbines would be the best way to harness green power. But these beasts have been under attack from Mother Nature. Engineers worldwide are seeing a drop in the turbine's power output. Inspections revealed that in many cases, the front of the blade, the leading edge, was suffering catastrophic damage. To keep the power flowing around the world, a solution is needed, and fast.
Any damage to the blade's leading edge means that it doesn't cut the air so smoothly. And that means the blade doesn't turn as quickly. Slower blade means less electricity generated.
So the leading edge here is very sensitive in terms of aerodynamics. Just a small defect can cause a defect in the lift that goes right the way down the blade. So it can have a huge impact on performance of the blade.
The problem comes down to the speed at which the turbines spin. It might look slow, but size is deceptive.
The blades are spinning at up to 180 miles per hour. That's almost 290 kilometers per hour.
At that speed, anything that hits the blades could cause massive damage, something these turbines off the coast of England were witnessing firsthand.
Well, you've got to remember that the middle of the southern North Sea is a fairly hostile environment. Effectively, we have sea spray, we have salt water, we have wind. All of these combine to cause major erosion on all sorts of structure, whether it be oil and gas or whether it be offshore wind. And particularly, the leading edge of the blade is particularly prone to this, given that it has that proximity to salt water and wind energy.
We might call it thin air, but the sky is full of impurities, from dust to lumps of frozen water. A simple example helps demonstrate what has happened on a large scale.
Imagine that you're a grain of sand, drop of water, possibly even a small hailstone, and you're moving along with the flow. And you're approaching the very front, or so-called leading edge of this blade. And in order to go over the top or underneath, you have to have a force applied to move you. But there's no time for that because the turbine blade is hurtling towards you at 150 miles an hour. And so you hit it. So if it's only one hailstone, it's not going to make much difference. But there's hundreds of them. And after about 2 or 3 years, these may create a larger hole. The wind will catch that and start to delaminate the turbine blade.
With blades so precisely shaped, delamination, or splitting open of the material layers, causes massive interruptions to airflow and loss of power.
It's amazing that these tiny pieces of dirt can cause such huge problems for these giant machines.
Renewable energy is the future, so engineers are working hard on solutions, from long-term, tougher materials to short-term fixes.
The solution here is relatively simple. Either the blades are coated in a strong protective paint, or an ultra-durable tape is applied to the leading edge.
The tape works like a Band-Aid and prevents further damage or even catastrophic failure of the blade.
It's quite simple to put on. Simply adhese it to the surface, some adhesive down here, pull it across, and then let it cure for a very short time. So it's quite simple for a technician to come in, learn how to put it onto the wind turbine. So we're hoping to put this on fairly quickly onto a number of offshore wind turbines in the field.
Not only can the tape fix a damaged blade, it can prevent it in the first place.
The blades can be protected when they're being built. It means they don't have to be stopped as often for costly and difficult maintenance. In this case, prevention is definitely better than the cure.
Now we know that turbine erosion is a problem. Let's hope that engineers tackle it as soon as possible and keep clean green energy coming thick and fast.
Engineering mix-ups can happen anywhere, from the smallest village to the greatest city.
They said, look, don't let the kids out. It's a major emergency.
And on the giant transportation projects that link them all. It's amazing how often things go wrong. First, it's off to Scotland and a famous bridge that was struggling to cope with its workload.
Nobody puts these bridges up and expects to get only 50 years out of them.
The Forth Road Bridge opened in 1964. At 2.5 kilometers, the engineering marvel was the longest suspension bridge in Europe. It was built to carry 4 million vehicles a year, but after just a few decades, it was carrying 6 times more traffic.
People did feel unsafe.
The lifespan of the bridge was a serious concern.
In 2004, as a precaution, engineers inspected the main cables. What they found was worrying. The bridge had lost 10% of its strength due to corroded strands inside the cables. The combined problems couldn't be ignored, so engineers looked for a solution. The plan? To dehumidify the cables with warm air. The fix succeeded, but the volume of modern traffic was now too great. The radical solution was to build a brand new bridge. And in 2017, the epic Queen's Ferry Crossing opened. Now, the Forth Road Bridge carries only emergency vehicles and public transport, but at least it's still standing. Next, we head to Germany for a very different transportation fail.
This is a road to nowhere.
Germany is famous for its network of high-speed roads, known as autobahns. In 2005, a new stretch of autobahn was built to connect the north coast. The route was a success, but after just 12 years, a 40-meter-long section collapsed. This part of Germany is a vast peat bog, a notoriously unstable foundation. For much of the autobahn, engineers had driven huge piles through the peat into bedrock, building the road almost like a bridge. However, where it failed, they had tried an experimental system, using thousands of much smaller friction piles to support the road. In theory, these mini piles didn't have to be driven down to the bedrock, saving time and money. But in reality, the theory didn't work out so well. The peat was too moist, and the piles shifted out from under the road. A huge stretch of autobahn completely collapsed.
It's always good to see engineers thinking outside the box, but this time their experiment didn't pay off.
To rebuild the damaged section of autobahn, engineers are using a tried and tested solution. Large piles driven down to the bedrock will ensure a more successful road ahead. From roads to trains, and a transportation solution that gave one city a sinking feeling.
This is a nightmare scenario for a picture-perfect city.
Amsterdam is famous for its canals, culture, and architecture. But in 2008, some residents were shocked to find the ground sinking beneath their houses.
I heard just cracks, cracks,
It was like the building was crying for pain.
Investigations revealed that ongoing construction on the Amsterdam metro system was responsible. Amsterdam sits on soft, wet ground, with millions of piles supporting the city. So the metro engineers used an ingenious box system to tunnel without destabilizing the piles and the buildings above. In 2008, some of these subterranean boxes cracked, allowing water and sand to pour in, leaving voids beneath the houses.
If water and sand leak into the tunnel, there's only one way for those houses to go: down.
Engineers repaired the boxes and put in new piles to stabilize the historic houses for good. Finally, in the summer of 2018, Amsterdam's metro was fully functioning. Meanwhile, in the UK, another very different public transport system was heading off track.
How did they manage to get this so wrong?
Worldwide, many cities use an underground metro to move people around. It's quick and efficient. But building them is expensive and disruptive. So for some smaller cities, it's not a viable option. In Bristol, England, heavy traffic drove city planners to seek a cheaper, more practical way to move people around. However, a small but crucial engineering mix-up failed to ease the congestion. Journalist Paul Barltrop knows all about the city's traffic woes.
Bristol's always had a really bad traffic problem, not least because it's a fairly well-to-do city, high levels of car ownership, and a geography which makes it quite hard to get lots of roads and lots of cars flowing smoothly around. There are rivers, there are hills, there are narrow city streets, and that's caused a lot of congestion over the years.
Bristol's engineering solution is a guided bus route called Metrobus. It works with sections of curb or rails that are installed on the sides of existing routes. The buses are equipped with guide wheels that make contact with the track when the vehicle enters a guided section. These effectively steer the bus, like a tram on tires. In theory, with these segregated lanes, buses can run faster, more frequently, and more reliably than existing services. It's also much cheaper than building a metro or tram system. Transport engineer Bob Mingus explains.
Many cities just aren't dense enough in terms of the population to justify heavy rail or light rail systems. This is a system where you can have a trunk route of guided section and then buses fanning out into the countryside to visit villages or suburbs. So it's actually a much more flexible system, particularly in more low density situations that we tend to have in the UK.
Like the outskirts of Cambridge, where a guided bus system is already running successfully.
Cambridgeshire Guided Busway opened in August 2011. There had been scepticism before there'd be a bit of a white elephant, but within a few weeks we had to increase the service from buses every 10 minutes to buses every 7 minutes. It's tremendously helping Cambridge expand. It's helping people get to work, helping people get to college. Houses are being sold on the basis of the proximity to the guided busway, which shows people are prepared to pay that bit extra to be next to a rapid transit system.
But back in Bristol, on its multi-million-dollar Metrobus project, there was an engineering mix-up. The buses didn't fit.
What went wrong? If it was to technical standard, why didn't it fit?
In 2017, first tests ran on one of the most expensive stretches of the new track. They discovered that for 2.5 kilometers, the guide rails were too close together, meaning the buses couldn't drive through.
It's only, it's less than 3 kilometres worth of this, and it's only in certain places, but nonetheless, it's a bit of a mess.
There was only one fix for the problem.
There is going to have to be some relaying, some reworking of the guided busway, which is going to cost a lot of money and going to take a bit of time as well.
It took months and cost £200,000. But by late summer 2018, the guide tracks had been reinstalled at the correct width, and the route was up and running. The mix-up was a reminder for engineers that they should measure twice and cut just once. Construction calamities come in all shapes and sizes, from the destructive to the truly catastrophic, from the worldwide to the small scale. So long as we keep building, there will always be more engineering mistakes to fix. Coming up on our expedition of engineering disasters. A sinking skyscraper in downtown San Francisco.
I got so upset and nervous that I had to move out.
A biblical build that's failing to hold back the tide.
Disaster-wise, on a scale from 1 to 10, this was off the charts.
A breathtaking bridge becomes a crossing catastrophe.
Walking becomes very dangerous. You can fall down very easily.
And a German town in danger of going underground.
The building starts to break in the sinkhole. That was really terrifying.
With big builds, even the smallest mistake can be a huge disaster. From miscalculations to misunderstandings. These are the massive engineering mistakes that only an expert can hope to fix. Construction is all about measuring twice and cutting just once. But sometimes, despite the double checking, things don't quite go according to plan. Like this first construction calamity in San Francisco. And a luxury tower where residents were getting a distinct sinking feeling.
He rolled this marble 10 feet toward me. The marble slowed to a stop, turned around, and rolled back. We were flabbergasted.
Even though the earth is not flat, an apartment's floor should be. Something weird is clearly going on. San Francisco, the city famous for the Golden Gate Bridge, its streetcars and winding roads.
When you think of San Francisco, you might think of the birthplace of the tech revolution, its beaches, or its trendy neighborhoods, but this city also has some amazing feats of engineering.
Manhattan is about looking up. San Francisco is about looking out.
And one of the best places to see this spectacular view is the Millennium Tower. 58 stories of prime West Coast real estate. Basic apartments sold for around $2 million, with the penthouse commanding a cool $13 million. Former resident Frank Jernigan bought a 50th floor apartment in 2011.
There were so many things about it that were just over the top. I'd never seen a building like that before. The view from the 50th floor was absolutely spectacular. We could see all 4 tiers of the Bay Bridge all the way across the bay. It was like living in a fine hotel. Marble floors, marble walls. Everything was just top quality. Everything was just done to perfection.
Standing nearly 200 meters high, it was the tallest residential building west of the Mississippi.
When we moved in, I felt like this was our dream place, and we would be here for the rest of our lives.
But Frank Jernigan's dream soon turned to nightmares. Shortly after construction was completed, developers uncovered seismic problems with the super swanky skyscraper.
By the time the building was finished building, it had sunk over 8 inches, and it had been expected to sink only 4 to 6 inches over the entire life of the building. So they knew there was a problem.
In the decade after its 2008 completion, the sinking more than doubled.
Experts estimate that the tower has sunk 17 inches. That's more than 40 centimeters, and it's predicted that the tower will continue to sink 2 inches or 5 centimeters each year.
And this sinking skyscraper shows no signs of slowing down.
So, one of San Francisco's tallest residential buildings was sinking. The one place you'd want to get it right is here, in an active earthquake zone.
With the tower sinking a lot more than was initially predicted, experts wondered whether the foundation wasn't strong enough. The tower sits on a giant reinforced concrete slab, which rests on around 900 long steel rods called friction piles. However, the piles only go down around 25 meters, less than halfway to the solid bedrock 60 meters underground. But that alone shouldn't be a problem, as engineer Gerald Cawthon explains.
The pile is actually held up by the sand or the dirt around the outside of the pile. Now at first, it'll go down pretty easily. The pile driver starts to hit them, and as the pile driver hits them, it gets harder and harder to go down. Now it's getting harder. I'm not going as far every time I hit it. So why does it get harder to push it down in the ground? Well, that's what friction is all about. It is the sticking power between the soil around the pile and the steel pile itself is what is holding that pile up. Now it's virtually stopped.
Driving piles into the sand is like putting up a beach umbrella. In shallow sand, it wobbles, but the deeper you push it, the more stable it becomes. More sand equals more friction. The Millennium Tower is just this on a much bigger scale.
Dozens of other towers in the area have similar foundations without sinking. It seems the Millennium Tower has a much weightier problem. Mid-design, a main building material changed from steel to concrete. Concrete was cheaper than steel, but double the weight.
Somewhere down the line, someone decided to switch from steel to concrete.
So another possible factor was that with the change in materials, the building had become heavier than planned. And if a sinking skyscraper sounds bad, as horrified residents discovered in 2016, this tower wasn't just sinking, but tilting too. San Francisco, famous for its stunning bay views, but the residents of the Millennium Tower were more concerned by what was going on inside.
So we took out this marble, and I said, well, why don't I video it? And I just pulled out my phone, and I said, okay, roll the marble toward me. And he rolled it about 10 feet toward me. The marble slowed to a stop, turned around, and rolled back, picked up speed as it passed him, and then curved around toward the northwest, the direction of the lean. We were flabbergasted. We just couldn't believe that there was an actual lean that we could detect in that way.
We all know that skyscrapers aren't meant to lean. There is something clearly wrong here.
I got so upset and nervous that I had to move out. It's emotional for me even today because this was going to be our dream home for the rest of our lives. And so to finally face the day where we realized we had to leave, We went online, found an apartment that was furnished, packed our bags, and left in 24 hours.
The tilt is up to 36 centimeters off kilter, which may not sound like a lot, but in an active earthquake zone, any imbalance could prove disastrous. The root of the problem could go deeper than the foundation. The very ground beneath the tower isn't as solid as it looks. Geologist Dr. Ray Sullivan is on the streets of San Francisco to explain.
We're in an area of filled land. This was a marshland area. If you stood here in 1849, we would be surrounded by mudflats, ravines, creeks. This whole area had to be filled.
Around 170 years ago, the tower's location was swampland. As San Francisco grew, rock, sand, and trash were used to build out the land, creating a far from solid foundation.
We have here 2 or 3 storied structures. They're on filled land and therefore subject to a certain amount of settlement. And if you look to my right here, you can see that the door is 3 or 4 feet below us here. This is due to subsidence. If you look to the east of us, you can see the Millennium Tower, which is also on fill.
As unpredictable as the ground may be, that might not be the only reason the building is tilting and sinking. Some speculate that a nearby construction project is to blame. The Trans-Bay Transit Center broke ground soon after the tower was completed. The Millennium developers think that the removal of groundwater from the site may have caused the dramatic drop.
Construction sites across the globe use dewatering to make drier conditions for them to work in. The problem is this can upset the local water table, at least temporarily.
As soon as the work next door was over, the groundwater table came back to its previous level. And yet the building is continuing to settle up today, even though that work was done years ago. It's been 4 years since that work was completed, but the settling is completed. So the settling went on before there was any excavation. It went on after the construction was finished next door. I do not personally think that the next door work had anything to do with this.
While the cause of the problem is up for debate, the building's residents are focused on finding a solution.
Everybody has their opinion about what is going to happen in the future. Some people are confident that it will be fixed.
Is there any way they can stop the tower from sinking?
They've talked about freezing the ground. Freezing the ground would mean you'd keep the ground under that building as ice, frozen as ice in perpetuity. It would be forever. And so that is a very expensive thing to do.
With deep freeze seeming unlikely, experts search for other ways to stop the sinking.
Now, there have been people who've talked about lopping off 20 stories off the top. I think it may have been the New York Times that made that solution. Was that facetious? Maybe. But if none of this other works, they're going to have to do something.
These solutions range from wacky to downright ridiculous. Is there any way forward that might actually be workable?
The drilling rigs beside the tower hint at a possible answer. The best guess at the solution is the addition of longer piles, this time going down as far as the bedrock. It won't be quick or cheap, with estimated costs in the hundreds of millions of dollars.
Clearly, if we thought it was going to be fixed anytime soon, we would have stayed, but I'm afraid we lost faith in that.
It does seem like the Millennium Tower's problems are not going away anytime soon. But I hope, for the sakes of the residents, that they actually do come up with some kind of solution so they can start enjoying living in one of the greatest apartment blocks in the US.
With some construction catastrophes, the errors are blindingly obvious, even when they're hidden at the bottom of the sea. For this blunder, we head to Venice, Italy. where this ancient city is struggling to keep its head above water.
This engineering project gives me a sinking feeling.
It's an engineering catastrophe on an unprecedented level.
Disaster-wise, on a scale from 1 to 10, this was off the charts.
An underwater construction project that's struggling to stay afloat.
Unless something is done, Venice is in trouble.
Venice, Italy. This unique and iconic city was founded in the 5th century and lies on more than 100 islands in the Venetian lagoon. Environmental scientist Jane DeMosto has lived here for over 20 years.
Venice is a UNESCO World Heritage Site. Venice has an architectural style that you can't find anywhere else in the world.
Built centuries ago, Venice is an engineering marvel. The foundations of it were built using wooden piles in marsh and sand, yet it still stands today as one of the world's most iconic cities.
Venice was built on millions of closely spaced wooden poles, 18 meters in length, hammered through soft mud into the solid clay below. Protected from oxygen, the wood doesn't rot, and in fact, thanks to the mineral-rich waters, becomes petrified or hard like stone. The foundation might be solid, but there's no getting away from Venice's low-lying and wet location.
Venice is on the ocean, and with these huge tidal surges and rising sea levels, it's a recipe for disaster.
Between autumn and spring, Venice experiences abnormally high tides, known as the acqua alta. These tides are made worse by strong seasonal winds. The impact can be devastating, something residents like engineer Vincenzo Di Tella know all too well.
When there is this tide, the Venice is completely flooded. So it's not possible for the normal activity. It's only possible to go with a boat inside the river, but you cannot go on the street.
Tidal surges have long been a problem for Venice, but in 1966, it had the worst flood in recorded history, and the government finally decided something has to be done.
The Italian government pledged a solution, but it wasn't until the 1980s that the Mose project was conceived. Mose was named after the Old Testament prophet Moses, and like its namesake, the plan was to hold back the waters that were threatening to engulf Venice.
In the 1980s then, the Italian government began to prototype a tidal barrier that could rise when it was most needed when there were the largest tidal surges.
Mose would be an engineering project on a biblical scale.
They use that term still because of its reference to Moses, who parted the water, as though this engineering project is going to have the same kind of universal powers to defeat the physical forces of the world.
After decades of discussion, design, and prototyping, in 2003, the go-ahead to build the barrier was finally given. The aim of this ambitious project was to divide the Venetian lagoon from the Adriatic Sea by placing barriers across 3 inlets. A total of 78 mobile gates needed to be laid at the bottom of the seabed. Each one is 28 meters long, 20 meters wide, and weighs a colossal 300 tons.
Mose consists of a series of gates that lie flat on the seabed, and they're hinged at one end. And to activate them, air is pumped into the gates, and through the principle of buoyancy, the gates rise up, providing a barrier between the Venetian lagoon and the Adriatic Sea.
The design was revolutionary and would allow authorities to open and close the sea gates to cope with tidal surges of up to 2.7 meters. At least that was the plan. But to match the biblical scale of this project, the catalog of catastrophes has been almighty as well, becoming a joke amongst Venetians.
So what they didn't think about was that when the barrier's up, tidal forces can push sand and silt underneath the barrier, so it can't sink back down properly.
Engineers realized that when the gates were raised, sand would settle in the trenches. which meant that when the gates were shut, they couldn't close properly. The materials used in the construction of the barrier have already shown significant signs of wear.
Another really difficult problem is corrosion. The gates that were installed underwater are already showing huge signs of corrosion, and gates that haven't even been put in yet, that are on the land, are starting to rust. So this is going to render them much, much weaker and can lead to huge mechanical failures in the future.
The barriers are made out of these big metal panels, and the paint is being corroded. That's also something that, you know, is a well-known feature of salty water.
The gates are corroding, even the replacement gates are corroding. Clearly they chose materials that just couldn't withstand salt water and sea air.
To add insult to injury, a tiny Venetian resident is causing huge extra problems.
What they didn't also think about was the environment at the bottom of the sea. There's lots of mussels and all sorts of creatures down there, and they start to live on the brackets, on the hinges, meaning that sometimes these hinges are inoperable.
There was some issue with the hinges, and lo and behold, there were mussels growing on the hinges.
And the only way to deal with that is to have divers go down and literally scrape them off, which just seems ridiculous.
All these massive oversights have Venetians up in arms.
They're still trying to finish building that was planned in the 80s and was supposed to be finished in 2011. And they recently said that the 31st of December due date might not be possible.
With no end in sight, this project also comes with a hefty and ever-growing price tag. Latest estimates take the budget to a whopping 5 billion euros, 3 times the original estimate.
It's already cost billions and it's not even finished, and to maintain it is going to cost 80 million euros a year. Surely someone knew from the start that this was not a good idea.
The Venice flood barrier is this ancient city's only hope against rising sea levels. But with so many problems, it appears that the focus of this project has not been on the engineering. As the lagoon slowly rises, so does the cost to fix it, while confidence in this flawed flood defense is falling. Residents like journalist Alberto Vitucci think money that continues to be spent on the project could potentially help the city of Venice in other ways.
Because the Moses, the great work, cannot save, for instance, St. Mark Place, because Moses is only for high tides, not medium or regular tides. And San Marco is the lowest place in the city of Venice.
As it stands, the Mose project is set to proceed, but the reality of operating this barrier in the long term could be more trouble than it's worth.
A lot of money spent only for this work was a real disaster for Venice, because every year the city of Venice needs a lot of money for maintenance. Venice is a particular city. It lives in the water, but they thought only about Mose.
With the solution to the issues far from certain, it seems the Mose project has done a better job at dividing opinion than parting the sea.
This project has been going on for years, has been costing billions, and still has a lot of work left to go. But the tide is coming, and if Venice is to be saved, something must be done.
Many Venetians maybe thought that the Moses could stop the high number of tides. But now, looking at the works, the lates, the money, the problems, Venetians, I think they have enough of this project.
Let's hope the Italians come up with an engineering solution that will protect this iconic city.
Sometimes, the bigger the construction project, the greater the potential risk. And when it comes to groundbreaking builds, the last thing anyone needs is a monumental slip-up. For this next building catastrophe, we're off to northern Spain and a project known as the Zubizarreta, or White Bridge.
Walking becomes very dangerous. You can fall down very easily.
An ambitious design that's become a construction calamity.
It's so obvious. They should have guessed that would happen.
Sí, yo me resbalaba ahí y me cayó. Era, digamos, peligroso.
A stunning glass-floored spectacle that turned into a complete cover-up.
You can clearly see that floor is black. Something is wrong with that picture.
It's supposed to be a dazzling glass icon, but a basic blunder made a real mess of that.
Bilbao is northern Spain's tourist mecca.
I was in Bilbao for a week, and it was a really beautiful city. It's got this sense of art, these very dramatic big structures like the Zubizarreta.
Not so long ago, it was a very different story, according to local architect Bert Nisch.
Bilbao was a run-down industrial area in the 70s, 80s, a really polluted industrial city.
With heavy industry in decline, Bilbao needed reinventing and turned to culture with a trio of landmark projects.
There was a big reformation process starting. They made a big master plan. 1990, for example, the Guggenheim Museum, the competition was held. It was a large process, and well, this is what you have today, a very beautiful, wealthy city. When Bilbao get in all the media, then it was always like the city of arts, the city of design, and the first three projects that always have been mentioned were the Guggenheim Museum, of course, the metro system by Norman Foster, and a Calatrava Bridge, the Zubizarreta, which means in Basque, the White Bridge.
The 76-meter-long steel and glass Zubizarreta Bridge was key to Bilbao's transformation. Its sweeping white lines and sheer glass floor were designed to celebrate the port's nautical heritage and unite the city.
Bilbao was a city of two halves. On the one side of the river, the ancient center, and the other, industrial and run-down working-class neighborhoods. Designers hoped that connecting the two halves would reinvigorate the city.
Fermin Lopez worked for the company that financed the bridge.
Este puente ha sido una solución fantástica para conectar Bilbao Centro con uno de los barrios de Bilbao. Cuando no existía, la conexión era muy complicada.
The Zubizarreta opened in 1997, but this bridge designed to unite a city was in danger of bringing most of its residents to their knees. It was meant to be a dazzling display of cutting-edge design, but soon after it opened, this bridge hit troubled waters.
Era muy resbaladizo, con lo cual con mal tiempo, con lluvia, hielo, era peligroso.
He pasado mucho tiempo resbalándome y pasándomelo mal porque tenía miedo a caerme y he visto caerse a gente también.
O sea, yo entiendo que resbalaba mucha gente, se caía, yo cuando está mojado alguna vez me he resbalado, pero podrían haber puesto algo más disimulado, la verdad.
People were clearly struggling to get across the bridge without falling. Material scientist Gustavo Schwartz explains the problem.
Okay, here we are at the Zubizarreta Bridge, which has a lovely design, but one of the problems of the bridge is the floor. I mean, the floor is made basically of glass, and the problem with the glass is that it becomes very slippery when wet. Glass surface is not safe to walk on when wet.
From a design point of view, I can really see what they were going for. The glass tiles would look incredible, but it's not the best choice for a sloping floor, especially when you consider Bilbao's weather, when it rains for 4 months of the year.
The mystery isn't why the glass plates were failing, it's why the architect chose to put glass flooring to begin with. We know this is slippery.
The problem with glass is its lack of friction. Friction is the resistance between two surfaces. It's what keeps you upright on a path. Your shoe and the rough ground grip each other. A glass floor is much smoother and much harder to grip. Throw in a slope and rainwater, and you have one hazardous bridge. Gustavo uses a slip alert to measure how slippery the original glass bridge floor is.
So we have a small trolley here. So we are going to slide the trolley through the surface, okay? And we are going to check how far the trolley is going. I mean, the longer it rolls along, the more slippery the surface is.
The machine simulates a slip. The higher the reading, the more dangerous the surface. Anything over 180 indicates a high risk of falling.
Oh, this is really slippery. The trolley is giving us 205. This is a very high value. We are in the most dangerous region. And with this value, one of every two people is going to fall down.
That's crazy. This is a classic example of style over substance.
Da fe de que como monumento, como proyecto, es magnífico. La pena es que no se ha hecho el suelo adecuado para el clima de Bilbao.
In pushing the boundaries of design, the architect has sometimes found himself on the very limits of engineering possibility. From troublesome tiles on the Valencia Opera House to the budget and schedule-stretching World Trade Center station. There was even another slippery bridge over the Grand Canal in Venice.
Architects, yes, they've got to build something that looks good, but they've also got to build something that works.
It was clear the city couldn't leave the bridge as a waterslide.
The town hall was trying to solve these problems with a lot of different ideas to treat the glass with some acids or sanding or printing something on it or gluing something on it.
In the end, the solution was far from stylish.
There was no good solution for it. Yeah, though the bridge remains very slippery, and at the end they decided to put a plastic carpet on top.
In 2011, the decision was made to cover the entire surface with black mats. Local journalist Jose Marie Riveriego covered the story.
El ayuntamiento se vio con fuerza y esta idea vino por un antiguo colaborador del Ayuntamiento de Bilbao, el director de Bilbao Arte, Javier Riaño, y Riaño, que es artista, en un viaje en Nueva York, simplemente se fijó que en una tienda de Apple, cerca de Central Park, pues tenían puesto una alfombra de estas características en la entrada para evitar que la gente resbalara y se pudiera secar los zapatos y que no resbalara cuando había lluvia.
Despite their simplicity, Gustavo's gizmo reveals how much safer the mats are.
We put the trolley back here and see what happens. We got a value of 126. This is much safer than on the glass, definitely.
The mats are ugly and have to be replaced every 2 years. But at least the residents and tourists can stay on their feet when they cross the bridge.
So, it's a sensible solution, but not likely to win any design awards.
Por fuera sí, me parece muy bonito, pero la alfombra que le han puesto negra pues es horrorosa, la verdad.
Y bueno, aunque no es muy bonito, pero bueno, es una alfombra negra en vez de roja, negra.
Practical as the mats may be, glass manufacturing expert Nuria Galbe believes there's a much clearer option.
This non-slip glass is rated in the highest standards. It's a glass suited for heavy use. It's engraved by acid etching. It has a design that works in all directions, and it also is scratch resistant thanks to the acid etching processing.
If they had used this glass instead of covering with this mat, the bridge could
could show the brightness, the lightness, and the beauty of the bridge.
Using etched glass is a viable solution, and that would stop a lot of the slipperiness problem.
There is no denying that bridge is utterly beautiful, and I'm totally for pushing boundaries. But sometimes you do just have to sit back, hold your hands up, and go, yep, this time something has gone wrong.
Construction catastrophes can sometimes happen when engineers ignore what's staring them straight in the face. And occasionally, the disaster lies directly beneath their feet. For this next engineering escapade, we're off to Germany. In February 2016, this sleepy town's tranquility was shattered.
It was really scary and frightening.
Ich dachte, oh mein Gott. Oh, it was quite spectacular.
Residents woke up to a supersized sinkhole.
What on earth could have caused this massive hole?
The vast crater rocked this tranquil town. But it shouldn't have been completely surprising. The city of Nordhausen is more than 1,000 years old. It's a peaceful place, most of the time. Just ask local journalist Angelo Glashagel.
We are here in the very middle of Germany, at the edges of the Harz Mountains, in a very small, quiet town. But 2 years ago, we saw quite a buzz because of what happened just behind me.
In February 2016, these small town council buildings were disappearing into the ground before shocked workers' very eyes. Council Director Gunnar Reuter was one of the first on the scene.
Ich lag schön auf der Couch nach getaner Arbeit und dann wurden wir angerufen und sagen, Herr Reuter, kommen Sie ganz schnell hier zum Salzergraben. Hier drohen Fahrzeuge einzustürzen. Ja, habe meine Kollegin Jessica angerufen und wir sind dann sofort hier runter und da war schon ein Meer aus blauen Lichtern, alles Feuerwehrfahrzeuge, die Polizei war da, hat Amtshilfe angeboten.
It was a Friday evening and I got a call from my boss and he said, oh, come with me, there is something happening. So we went there in the evening and there were already a lot of people and there were a small little break down in the earth and the sinkhole was very small in the beginning. The earth opened very suddenly. It got bigger pretty fast and there was a lot of water and that makes a lot of sound.
It was quite a spectacle. We had, well, a small catastrophe on our hands.
A massive sinkhole was opening up between two buildings.
Throughout the evening, the sinkhole got bigger and bigger again. And then the building starts to break in the sinkhole. That was really terrifying.
Luckily, the offices were closed for the night.
We all were very glad that nobody had hurt. So nobody was there in the building because it was in the evening and the night.
When sinkholes happen, they happen fast, without warning. It must have been utterly terrifying to stand there and see this building collapse right into the earth.
There's clearly something going on beneath the ground.
Nordhausen, the sleepy town in Germany that in 2016 woke up to the nightmare of a supersized sinkhole. And as the dust settled, people wanted an explanation. The answer seemed obvious. The hills around Nordhausen are sinkhole central. Geologist Thomas Kammerer was well aware of the surrounding situation.
This part of Germany is very susceptible to sinkholes. We have more than 10,000 registered cases of sinkholes in this state. There are thousands of sinkholes of various sizes. Sometimes they are just inconspicuous small depressions, sometimes they are large craters.
With 10,000 sinkholes, this area must look like Swiss cheese. There's clearly something going on underground.
The problem is this rock anhydrite, which means without water, and it's thirsty like a sponge. When anhydrite contacts groundwater, it will absorb the water and turn into this, gypsum. Unfortunately, gypsum is soluble and will dissolve away, leaving a space underneath the ground.
The problem can be traced back to a seam of anhydrite beneath the hills around Nordhausen. As groundwater seeps into the anhydrite, it turns into gypsum, which then dissolves, forming caves. When the roofs get too thin, they collapse, creating the region's many sinkholes.
Now, this is a particularly good example because we can see both the sinkhole and we can look into the subsurface cave system that is responsible for its formation.
With sinkholes everywhere, one obvious solution is to build nowhere near them. Sven Schmidt's engineering team has the job of investigating patterns in the area.
Hier auf diesem relativ kleinen Fläche 12.000 Erdfälle schon registriert habe. In Nordhausen haben wir in den nördlichen Zechsteinsaum, in dem sehr viele Erdfälle auftreten. Und südlich davon, dort ist es so, dass nur sehr wenige Erdfälle auftreten. Und das sieht man auch hier bei dem Erdfall in Nordhausen, dass der eigentlich sehr alleine da in dem Flusstal und in der Region liegt.
Nothing like that has ever happened this close to the town before. We have seen similar things, but not this close to home.
It's normal that we have sinkholes in our area, but they are in the forest maybe, so nobody lived there, and so no houses are breaking down in the sinkhole.
Town planners know that the sinkholes in this area exist along a certain cluster, but the giant sinkhole under Nordhausen was not located anywhere near that, so presumably it's an anomaly, but not quite.
Just 6 years prior, there was another sinkhole at exactly almost the same spot, and it swallowed up a truck.
Wait, there had been a sinkhole in that exact spot in the past?
Was wir noch zur Erklärung vielleicht vortragen müssen, ist, dieses Gebäude und dieses Gebäude, die waren bis zum Jahr 2014 ein einheitliches Gebäude. Und im Jahr 2010 hat sich schon mal ein kleiner Erdfall aufgetan. Der war gab es einen kleinen Krater, 10 Meter. War ein LKW reingefallen, eine Bohrung gebracht von 40 Metern Tiefe. Dort haben wir auch keine Ursache von dem Erdfall gefunden oder für den Erdfall gefunden. Haben wir gesagt, okay, dann müssen wir hier wieder was tun.
And it was filled in, and it's a few years ago. And then our service company moved in here, and they used it as an office just a few weeks. And then the second sinkhole happened.
Predicting nature isn't easy, but if you're building in a sinkhole hotspot, surely building in the exact spot where a sinkhole has happened earlier is not a good sign.
It was very surprising because nobody expected that there will be a second sinkhole at the same place as the first sinkhole was.
With unstable ground making investigation dangerous, it's impossible to predict the cost of fixing the sinkhole, or even how to do it.
You can't really get to the hole with any large machines. That's too dangerous, so you can't really demolish it. So it's probably going to stand there and rot there for quite some time.
Any sort of groundwork takes masses of material, machines and muscle. And if you don't know how big the hole is, or if it's even safe to go near it, it's probably just best you leave it alone.
So there are no concrete plans to fill in the sinkhole because it's so huge that it would be very expensive to fill it in. We would need a lot of earth. And now nobody can use the buildings ever after again.
For now, engineers have no immediate answers to this natural disaster.
We are used to thinking that the Earth is, in our lifetime, a pretty static structure, but we can be faced with quite drastic changes on the surface and in our environment. The Nordhausen sinkhole made the whole structure unstable.
There is a lesson to be learned here. If you live in a sinkhole hotspot and you've already filled one in, just build in another place.
Construction calamities come in all shapes and sizes, from the shifty to the slippery, the useless to the wholly ridiculous. So long as we keep building, there will always be more mistakes to fix.